So she said, so she says, could you give the contribution in that paper? So yes, so I said, please share me, I will give my contribution. So I have to say to write the scientific article, it is very tedious job. It is not easy job. It is very complicated job. It is inherent of complexity. So what to do for get the scientific articles? So what type of procedure? So what type of the parameters in the scientific articles for ACS, RSC, elsewhere, Springer, Taylor Francis, Nature, then PLOS, then Bentham Science, MDPI. So these are the reputed publishers and they require the scientific article for the publication. So we will discuss one by one. So these are the outlines. First of all, in my presentation, I would like to cover these the parameters. How to write the scientific article. This is my first parameter. Then what do you mean by the citation and citation index? So this is very genuine parameters. What do you mean by the citation and citation index? What is the meaning of citation and what are type of what type of citation index? There is a science citation index. There is a science citation index expanded. There is a social science citation index. So there is a chemistry citation index. So there is a web of science. There are so many indexing out there, and that all are indexing uh, arranged by, organized by, hosted by the Clarivate. Earlier it was the Thomson Reuters. So we'll speak in later on. Then next is that is how Clarivate impact factor is estimated. Yes. So that is Thomson Reuters impact factor. Previously, it was called it was recognized as a Thomson Reuters impact factor, but the Thomson Reuters impact factor has had uh, sold his privacy to the Clarivate, and Clarivate that bite all the intellectual property from the Thomson Reuters, and nowadays it is calculated by the Clarivate. Clarivate is the database, that scientific database. It is the one of the biggest uh, company in the world, having more than 4,000 the employee. Next is that is Nobel. So whenever they're nominating for Nobel Prize, at that time they will ask how much your S10. Okay, it was sometime G index. So G index may be new for you. Okay, so I will also elaborate the what do you mean by G index. Then come to the does research indexing evaluate the journal quality? Yes, it is very good question. This question is that in your mind, is it research indexing that evaluate journal quality or quantitatively as well as qualitatively? Yes. And next to the new indexing is that a Q1, Q2, Q3, Q4. Nowadays in social media, you might be seeing that I publish Q1 paper, I publish Q2 paper, I publish Q3, but nobody say I publish Q4 straight. So this is the weakest quartile. Okay, so these are the outline of my talk, and we are going to discuss one by one. Now, question is arise. So, what is the research and what is the experiment? Okay, there is a quote written by the Richard Feynman. You know the Richard Feynman, ladies and gentlemen. Do you know the Richard Feynman? The Richard Feynman is one of the biggest a person who got the Nobel Prize in 1965 for the discovery of that the quantum electrothermodynamic. He is a man of physics who got Nobel Prize in 1965, and he is the father of nanoscience. So, at one quote is also written by Richard Feynman. There is a plenty of room at the bottom. There is a plenty room. There is a plenty of room at the bottom. He quoted in his meeting in 1959 in the Senate meeting of the America. So at that time, everybody laughed. How it is possible? There is a plenty room at the bottom. It means a single pin. There is a it means पूरी अगर छोटी सी पिन है उसी में पूरी दुनिया समझ जाएंगी तो लोग हंसते थे. सो एवरीबडी वाज लाफ. लोग इसके लिए भी हंसते थे कि चांद पे कैसे जाएंगे, आज चांद पे जा रहे हैं, मंगल पे जा रहे हैं. इट मीन्स so nowadays you know that अगर छोटा सा पेन ड्राइव है तो पूरी दुनिया उसमें समा जाती है, पूरी पूरी यानी इंफॉर्मेशन आ जाती है. सो इट इज now everywhere in botany, zoology, chemistry, material science, geological science, every science. So there is a nanomaterial, nanoscience for -9. So retirement. So it's correctly said that taste of our knowledge is experiment. So unless an experiment, you could not go, you could not empower the knowledge. But somebody says that you don't need to require the experiment. Not I am saying when I had attended the repression orientation in Punjab University, somebody expert says that no need to require. So you don't need a lab or expensive equipment to be a researcher. It is also correct. You need not you do not require the equipment, big equipment like 25 lakh. You do not require the same TAM. A TAM is more than 12 crore. Same is 5 crore. Then same TAM like that. And more microwave synthesizer more than 25 lakh. You just require magnetic stirrer, centrifuge, and Maple furnace for the synthesis of the nanoparticle. Now in my Nagpur University, there is a couple of people are synthesizing nanomaterials. Not in Nagpur University, Amravati University, Gondwana University, all over the world. One man from the Pune University, he got more than 5,000 citations for the banana mediated nanoparticles. So, and all over, because when I attained the conference in 2014 in Allahabad, Ahmedabad, not Ahmedabad, Allahabad. So at that time, that conference was organized by Ashutosh Tiwari. So at that time, I got idea of biosynthesis. So you don't need a lab or expensive equipment to be a researcher. Researcher maybe from humanities, maybe from the art faculty, maybe from the commerce faculties. They did not require the expensive. They do not have expensive equipment. So they also researcher. So researcher may be publish their review article in the form of book, in the form of edited book. Yes, there are so many ways to become the researcher. But but I am saying, apart from experiment and apart from do not require equipment. So this is my statement. A researcher is a simply answer of the curiosity, dedication, critical thinking, imagination, and rigorous reading. Now listen carefully. Research is a simple, this is my quote. Research is a simply answer of the curiosity. I every time whenever I am giving my deliberation in a national, international, as a resource person, as innovative speaker, I am giving this quote. And as well, I discuss with my professor that NBC. Is it correct? Vikram, yes, you are correct. Research is simply answer of the curiosity, a dedication, critical thinking, imagination, and rigorous reading. Because unless curiosity, reading, dedication, critical thinking, imagination, rigorous reading, you could not give the achievement. You could not touch the height of Himalaya. अगर हमको कुछ बनना है तो हमको क्यूरियोसिटी होना ही चाहिए. अगर हमको कुछ पेपर अगर हाईली इम्पैक्ट फैक्टर जर्नल में पब्लिश करना है तो हमको हमको रिसर्च की तरफ क्यूरियोसिटी होना चाहिए, डेडिकेशन होना चाहिए, क्रिटिकल थिंकिंग होना चाहिए, इमेजिनेशन होना चाहिए. हमको सपना देखना है, इमेजिन करना है कि मेरा इम्पैक्ट फैक्टर 685 इम्पैक्ट फैक्टर में आना चाहिए. आपको मालूम नहीं होगा, हाईएस्ट इम्पैक्ट फैक्टर इन द वर्ल्ड दैट published by journal Ville. Okay, so Ville is the highest publisher who that having the impact factor, the 685 impact factor. The name of impact factor is the that cancerous. Okay, the cancerous study. That totally done on cancerous and as medical study. So that is, and second most, then third most is that the Lancet and the Nature review on the microbiology. So there are various journals. But हमें मालूम है impact factor 10 है, 15 है, 20 है, 30 है, 40 है. But there are so many journals which have the highest impact factor. Okay, we will see it later on. So research is a simple answer of curiosity. So I will like to give the number of examples. What is meant by curiosity? What is meaning of dedication, critical thinking, and imagination, and rigorous studying. So can you explain? Can you imagine what is the curiosity? See your at your house. Sometimes if the new person coming at your home, if new baby, that kid, from morning to evening, he or she asking the number of questions. पापा वो क्या है, पापा ये क्या होता है, वो कल आए हुए उसका, हु वाज दैट गाय यस्टरडे ही केम, वो कौन है हमारा, वो कैसा है, क्या है, वो ऐसा है. So number of question here. So what is that? That is called the curiosity. So that is called as the curiosity. So curiosity for, but so what is the curiosity? So curiosity for the understanding. So see the example. I earlier rightly said that the kids and primary and high school students have the number of couple of curiosity. So why? Because they must understand वो कौन है, वो मेरा मामा है क्या, वो मेरा काका है क्या, मेरा वो चचेरा भाई है क्या, तो वो कौन है, ये क्या है, ये चीज क्या है. कभी कभी तो माने ये भी बोलते हैं कि हम चांद पे जा सकते हैं क्या, हम सन पे जा सकते हैं क्या. सो आई गॉट द एक्सपीरियंस. So this is a number of questions. So this is called as curiosity. But why is asked? Because the people, these kids don't know. They must understand. So curiosity for the understand. So research is also same. So research is about exploration, discovery, curiosity, and research is all about the questions. As we are the peoples of Indian, we reach at moon, a place where the none of country were reached at that a different site. आज हम मून पे गए हुए हैं. इसका मतलब आज तो हमने दुनिया पे हम इंडिया का नाम छाया है. So because of the research simple, not this is not the biggest बातें करने से या उसमें that is called as can say, okay na. So this is because of the research, because of nanoparticle, because of the space research. Okay, so this is the curiosity is the one of the parameter of the research. Make us critical thinking. So let us decide. So once you are doing the research in your lab, you must critical thinking while you are writing the paper. ऐसा नहीं कि आपने पेपर लिख लिया, आपने सेंटेंस लिख लिया. कभी कभी तो मुझे एक पैराग्राफ लिखने के लिए पूरा दिन चला जाता है. कभी कभी मुझे एक सेंटेंस लिखने के लिए पूरा एक दिन लगता है. इसी उसी सेंटेंस को मुझे 2 दिन 3 दिन में उसको रिवाइज करता हूँ. सो क्रिटिकल थिंकिंग इज वेरी वेरी इंपॉर्टेंट टू दैट that strengthen the sentence and paragraph and each and everything. So critical, sometimes the question will be arise from the reviewers, even in your review article. Most of the review article, the reviewers are always asked, revise this image, revise this figure, revise this table critically. Yeah, critical discuss this table 1, table 2, table 3, and image 1, image 2, image 3. So critical thinking is very, very powerful parameter from the research. Right? So I will not go in detail in the in critical thinking. The next, the scientific and brainstorming. You know that for doing the PhD, we must require a supervisor, co-supervisor, mentor for BSc. Now NAP, in NAP for BSc student, MSc student, there is a mentorship. So when you are writing the paper, you need the suggestion from your seniors, from your colleague, from your mentor, from your supervisor. Unless and until scientific brainstorming discussion, your introduction portion, your abstract portion, your conclusion portion, your result and discussion portion could not be strengthened. So scientific discussion and brainstorming, it will strengthen the sentences, strengthen the paragraph, strengthen the it means that with compilations, it will be easy when you are discuss with your elder peoples, when you are erudite peoples. Okay, so scientific and brainstorming discussion is also even more collaboration with the expertise, collaboration with highest impact factor people, the highly cited people. So that will give you, suggest you a scientific writing of the paper. Similarly, imagination. I'm not saying imagination is the highest form of the research. The Nobel laureate person, that is Albert Einstein, he got Nobel Prize in 1921. So it is so whenever there is a science program, we always remind this Albert Einstein. So Albert Einstein is popularly known. Okay, मुझे एक स्टोरी मालूम है कि जब अल्बर्ट आइंस्टाइन और एक जो क्या बोलते कॉमेडियन, सो जो साथ में एक जा रहे थे तो बोल रहे थे कि सो अल्बर्ट आइंस्टाइन बोल रहे थे कि आप यू आर वेरी, नहीं, सो दैट कॉमेडियन मैन वर्स कॉमेडियन मैन मैन कह रहे थे कि आइंस्टाइन को आप तो दुनिया में छा रहे हो कि आप एवरीबडी आर देयर इज अ साइंस एंड देयर व्हेनेवर देयर इज अ साइंस प्रोग्राम द पीपल्स आर हैंगिंग योर फोटो इन एग्जीबिशंस, so displaying your photo in an exhibition. So Einstein said that you also one day you will also one day glorious, yeah, it means you will also shine and shine in your world. तो साहब अब वो बंदा उसके बाद you know that the Charlie Chaplin. Ab Charlie Chaplin, you know, the without talking and without, that means without gesture, without talking, without only acting. So he's very popular at that time. So imagination is the highest form. अब वो चार्ली चैपलिन का जो मैंने आपने बताया तो वो कैसे इमेजिन करता हूँ, यानी विदाउट टॉकिंग, विदाउट, यानी बोलने से एक्टिंग करके लोगों को हंसाना रुलाना. So that is very important. So imagination is the highest form of research. So the who Albert Einstein say. So whenever writing your paper, whenever you writing and discussing and your research work, laboratory work, table work, you must imagine it. You must imagine what will happen. So what will do. जैसे हम फिल्म देखते, फिल्म के बाद इसके बाद क्या होगा तो हम पहले इमेजिन करते हैं. वैसा ही रिसर्च का है. पहला पैराग्राफ दूसरे पैराग्राफ से मैच होना चाहिए, दूसरा पैराग्राफ तीसरा पैराग्राफ से मैच होना चाहिए, पहला सेंटेंस दूसरा सेंटेंस तीसरा सेंटेंस, एक सेंटेंस अपने आप मैच होना यानी लिंक होना है. दैट इज कॉल्ड एज, instead of match it should be link one another. Okay, so it should be link one another. So the next, the queen of material science, the Marie Curie, the mother of modern science, a mother physical science, physics. The hard work does not necessary, okay, for the success. However, no success is possible without hard work. Absolutely correct. What I said earlier, I said that you require dedication, you require hard work, you require imagination. So these are very, very important. But you know that the Marie Curie work her laboratory experiment in 10 by 10 room, 10 square feet. Okay, and bad to say that she died. So because of that poisonings that lead that lead and polonium. Okay, sir, polonium and radium, that elements, that very radioactive elements. Okay, so she was very, very hard worker and she got 3-time Nobel Prize. First with her husband, second with her daughter, and third with another collaborator. She got a 3 times Nobel Prize. Okay, I'd like to tell you the Nobel Prize. I got the idea of Nobel Prize. Why Indian people say why we are so much away from the Nobel Prize? Do you have any question? Do we have any answer? No, because we are not concentrating on the research. We are just copying and pasting. We are giving the citation. We are giving the citation. We are not concentrated on your idea. We are not exposing our wrong work. Now we are exposing. हम अगर हमारा कुछ एक्सपेरिमेंट रॉन्ग है तो उसको मॉडिफाइड करते हैं, उसको पॉलिश करते हैं. अरे जैसा है उस फिगर को आप उसको डिस्कस करिए, जैसे वैसे करिए. So we got the achievement. Okay, so in our world, the topmost Nobel Prize किसको है? So topmost Nobel Prize USA को है. So USA got the Nobel Prize 413. Then UK, United Kingdom, United Kingdom 300, 113. Then Germany 110. Then France 91. Then Germany, after Germany, UK, USA, UK, then Germany, then France, then Sweden. Sweden have only 30 Nobel Prize. Are a Nobel Prize giving the Stockholm from Sweden. And India is not in 10. India's number is 19. We have only 12 Nobel Prize. Out of 12 Nobel Prize, only 5 Nobel Prize a person who is native place of India. However, seven people, the native, the citizen from other country. First Nobel Prize 1930 for literature, Rabindranath Tagore, and second Nobel Prize for our then C.V. Raman. Okay, so 1930. So this is, we are from so many back. So we must try for the good research. Okay, so next, rigorous reading. I already said that. So rigorous reading and review of literature. You must read, and so many papers, so many journals. You will find a couple of paper, couple of journal in a same stream, same faculty. कोई कोई बोलते हैं कि ह्यूमैनिटी पीपल बोलते हैं कि ह्यूमैनिटी आर्ट आर्ट के और कॉमर्स के लोग बोलते हैं कि हमारे हमारे जर्नल ही नहीं होते एससीएस स्कोपस। अरे किसने कहा? किसने कहा? मैंने तभी मैं उनको आंसर देता हूँ, किसने कहा बताओ? ओनली हिंदी एंड मराठी, उसका भी होगा ऐसा इंडियन साइटेशन इंडेक्स, हिंदी और मराठी। अदरवाइज ऑल जर्नल हैव रेपुटेड publisher, Springer, then elsewhere, then Ville, okay, then United Kingdom, that that University Press, okay, UK Press, there are IOP, there are so many publishers for human literature, that humanity and the commerce peoples. Okay, so then now come to the main points. Okay, how to write scientific research article? Now keep in mind, so these are the parameters to write the scientific articles. आप आर्टिकल लिखिए, आप मेरे ख्याल से सब केमिस्ट्री के लोग हैं, all the participants from the chemistry people, you must know that, and you know that our for to publish our chemistry data in, so first priority is ACS, then RSC, then Ville, elsewhere, Springer, okay, then Nature. So okay, so I sorry, Nature, ACS, RSC, Ville, elsewhere, then Springer Nature, okay, then okay, so there are so many publishers, then MDPI, then Bentham, but NBPI is a predatory journal, predatory publisher. It requires you have to pay money. Predatory, then Frontier is for biomedical, Frontier is predatory. Then Taylor Francis, Bentham Science, D. Grutter, okay, Dow Press. Oh, then there are many publishers, which we can, then Hinvi, okay. So there are so many publishers which can require this writing parameters. Okay, so this is the standard format of RT. So this is the standard format of ACS, RSC, Nature, and the Springer Nature, elsewhere, and Ville. So first of all, ladies and gentlemen, first of all, you have to give your title of the article. Okay, so I will elaborate later in okay, in okay. So title of the article, the next author's name and affiliation, corresponding author, who will be the correspond for communication with the editor, co-editor, associate editor. Then after accepting the paper, you will receive the mail from publishing publishing editor, yeah, editorial board. Okay, then after publishing, you will get so many mails will be corresponding to the corresponding authors. Then TOC. So TOC is the one of, it is not a new, but TOC is RSC and ACS, elsewhere, Springer Nature, even Nature require the TOC. TOC means the graphical abstract, table of content. जैसा कोई पिक्चर आता है, मूवी आता है, जैसा आप शोले की बात करिए, है ना, तो गब्बर की बात करिए, ऐसे बहुत सारी मूवी आए थे, तो एक ट्रेलर आता है, तो ट्रेलर में पूरे शब्द नहीं लिखते, पूरी मूवी नहीं दिखाते, 3 हीरो रहेंगे, 3 मूर्ति, है ना, जैसे केवल 3 मूवी रहेंगे, people and means जो hero heroine whatever that. So this is the one type of that TOC. तो आपके आपके आर्टिकल का हीरो हीरोइन कौन है ना, इसमें तो ग्राफिकल एब्स्ट्रैक्ट, इसमें आपका मेन कौन है, नैनो पार्टिकल है कि एप्लीकेशन है. अब you can also focus on application, you can also focus on synthesis, you can also focus on your the text, yeah, okay, whatever that. Then abstract and keywords, you must write the abstract in 250 words. So there is the guideline for the abstract writing, 100 to 150, 200, 250, like that. So different journal have different capacity of the words. Then keywords, you should need 5 to 6 keywords, and keyword should be eye catching, it should be interesting, so that people will be see, oh, this keyword is for my is new for me. So he will sometime reviewer will give you a point, a suggestion, give eye catching keywords. Okay, but in my reviewing, whenever I review, I always giving the suggestion to the authors for eye catching keywords. Then introduction is very important, because reviewer always reading abstract, introduction, and conclusion. These three parts are very, very important. Then next come to the materials and methods. These material methods, you do not polish your matter. जैसा है वैसा ही आपको लिखना है. So do not polish your materials and methods. जैसा आपने जितना हॉर्स लिया है, जितना आपने टाइम दिया है, जो आपने सैंपल लिया है, जो आपने साल्ट लिया है, what are you have taken your salt, then solvent, and how many times, and muffling, centrifuge, calcination, whatever that, जो हो वही मेंशन करना है. Do not polish it. Then कहाँ से आपने सैंपल किया, कहाँ से आपने कैरेक्टराइजेशन किया, you just mention the outsourcing analysis, okay, whatever that. Then conclusion, it is the biggest, it is the most of the reviewer will asking because journal policy is that, journal की पॉलिसी ये भी होती है, वो क्वेश्चन भी पूछते हैं. So while your submission, while you are asking reviewer question, whenever the journal or editor asks some question to the reviewer, the conclusion is the part of title and the result discussion. Then we have to give the answer. It means reviewer have to give the answer. Yes. Other your and conclusion is not matched with the title and result discussion, then sometimes it is got more chance to the rejection. Other contribution, and here, yes, so this is very, very important nowadays. Since 5 years, every journal asking for the contribution, and a contribution means क्या? So that scientific contribution. उसने कुछ ये नहीं है, किसी ने सामान परचेस दिया, केमिकल परचेस दिया, किसी ने 10,000 रुपए दिए, किसी ने 1 लाख रुपए दिए, किसी ने 10 लाख रुपए दिए या 5 लाख. यू विल फाइंड द नंबर ऑफ पीपल्स. इसमें भी अभी फ्रॉड केस चल रहा है ना. सो इसमें अपने को वो नहीं लिखना है. वन आई आस्क समबडी अदर, सो व्हाट इज योर कंट्रीब्यूशन, पीपल्स आर सेइंग उसने मुझे परचेस करके दिया है केमिकल. नो. So this is not a scientific contribution. This is not scientific contribution. You must say, I have given plan and I have written introduction in plan. I have given that chemical, but that chemicals contribution, it means that synthesis contribution, writing contribution, then edition contribution. I will give the number of parameters. What is the contribution of that authors? Just so there is a that contribution means original writer writing, then supervision, then as well as scientific writing. Okay, then it means imagination. Okay, so there are number of author contributions. Okay, then conflict of interest. So the conflict of interest you have to give the, ऐसा नहीं पेपर पब्लिश होने के बाद आप जर्नल को बोलेंगे ये हमारा पेपर है, हमको आप पैसा दो, या हमको आप डिमांड करेंगे उसको नहीं. सो उसी के पहले जर्नल, एवरी ऑल द जर्नल्स आर टेकिंग conflict of interest from you. वो पहले से आपकी लिखवा के लेते कि आपको लिख के देना है. वी डू नॉट हैव द कंफ्लिक्ट ऑफ इंटरेस्ट फॉर फाइनेंशियल एंड एल्सवेयर. डाटा अवेलेबिलिटी, ये भी बहुत इंपॉर्टेंट है. नाउअडेज आरएससी एंड एसीएस एंड ऑल दोस रेप्यूटेड पब्लिशर, they are taking from you data availability statements. Data availability statements means then we have to give all the data are included in the manuscript. अगर आपने गलती से लिखा data included in the supplementary file and your paper is then your paper is accepted, एक्सेप्ट होने के बाद आपने तो लिख लिया कि डाटा इज आल्सो इंक्लूडेड इन सप्लीमेंट्री. पब्लिश होने के एक्सेप्ट होने के बाद डाटा मांगेंगे आपको सप्लीमेंट्री का. देन यू विल एट दैट टाइम यू विल, देन आप फंस जाएंगे आप। तो इसलिए डाटा अवेलेबल स्टेटमेंट में सब लिख के देना है कि कौन सा डाटा आपने मैन्युस्क्रिप्ट में है। अगर आपका डाटा मैन्युस्क्रिप्ट में, देन यू हैव टू राइट डाउन जस्ट ऑल डाटा इन मैन्युस्क्रिप्ट। देन एक्नॉलेजमेंट, इसमें आपको लिखना है, मैंने जो बोला है कि आपने किसी से केमिकल लिया, आपने किसी से लैब यूज किया, आपने किसी की लैब यूज किया, लैब यूज किया, आप को किसी के फाइनेंशियली सपोर्ट किया, all those things, those are not authors, first author, corresponding author, co-authors. They can be acknowledged in the acknowledgements. Then funding means, funding वो नहीं जिसने आपको हेल्प किया, जिसने आपको पैसा दिया, वो नहीं। फंडिंग मीन्स who receive you grants, grant means कौन, grant from your institute, grant from your university, grant from your state body, state agency, grant from your national agency, grant from your elsewhere, Springer, Nature, international agency. Then now come to the title of the articles. So title of ladies and gentlemen, so title of article, it is very important. I several time asserted you. The title of article is very important. I several time asserted you because that title will gives the whole scenario. आपने कभी देखा होगा, आपने क्या, because you are the PhD holder, most of the people PhD holder, net set gate people are participant. आपने देखा होगा ये मूवी में, पिक्चरों में, आप न्यूज़पेपर में, हितवाड़ा में पूरे टाइटल आई कैचिंग होता है। तो हमारा ही पेपर का रिव्यू आर्टिकल का, रिपोर्ट्स का, कम्युनिकेशन का, रेगुलर आर्टिकल का टाइटल आई कैचिंग होना चाहिए। सो टाइटल शुड बी डिस्क्रिप्टिव, एक्यूरेट, अप्रोप्रिएट, इंटरेस्टिंग बहुत इंपॉर्टेंट है। शुड नॉट बी मिसलीडिंग मीन्स उसका गलत तरीके से यूज नहीं होना चाहिए, गलत तरीके से टाइटल नहीं होना चाहिए। देखिए आप देखिए जो रिसेंटली वन ऑफ माय पेपर which got higher citation by INSPIR metal oxide nanoparticle roadmap to potential application. This is the advanced material today, having impact factor at that time when it was published, impact factor it was 10, and its citation is 195, not sorry 195, 205 I think, and second footlight degradation of dyes by nanomaterials. So that eye-catching citation, it will give the positive wave. Okay. The next title need to be simple and direct. It not be complicated. It should be simple शब्दों में। रिवर को भी समझ, sometime river will be a different field. By the I can say by mistakenly कोई एक्सपर्ट आपके सब्जेक्ट का नहीं हो सकता है। Subject means in chemistry there are so many fields where expertise, organic, inorganic, analytical, green chemistry, phytochemistry, then medicinal, there are. तो अगर रिव्यू किया है तो he is not expertise, so he will decide on the basis of your title. It should be interesting and informative. Title should be interesting and informative. Okay, again and again I am repeating, interesting. It should be concise, precise, include main theme of the papers. Okay, it should be concise, precise, include main theme of the paper. Means पूरा जो पेपर है, मैंने पहले कई बार आपको many times asserted, मैंने आपको मूवी का उदाहरण दिया, मैंने आपको न्यूज पेपर का याद करके दिया। इंक्लूड द मेन थीम ऑफ द पेपर। अगर किसी को कोई न्यूज रहती है तो बराबर वो टाइटल देते हैं, कई मूवी है ना, तो बराबर हम टाइटल देते हैं। तो वैसा ही हमारा टाइटल हमारे पूरे एक्सपेरिमेंटल से मैच होना चाहिए। इट शुड नॉट बी लॉन्ग, यस इट इज वेरी इंपॉर्टेंट। हमारा टाइटल 2 लाइन का होना चाहिए, 1 लाइन का होगा तो बहुत अच्छी बात है। मैं मेरे टाइटल तो 2 लाइन के ऊपर जाने नहीं देता हूँ, एक आधी बार ही। अगर ज्यादा अगर हमारे पास मेरे कोलैबोरेटर अगर ज्यादा है, मेरे पेपर में देखे होंगे बहुत सारे कोलैबोरेटर रहते हैं, तो मैं सबसे मैं कंट्रीब्यूशन कर रहा था, पेपर भेजता हूँ। एक पेपर को कम से कम मुझे 4 महीने लगते हैं ना, 4-5 महीने लगते हैं। अब हमारे पार्टिसिपेंट में एक उठाने सर भी है यहाँ पे पार्टिसिपेंट, उनका वो पेपर मुझे भेजते अपना, तो मुझे 2 महीने लगते हैं। चैप्टर भेजते तो मुझे 1-2 3 महीने लगता है। कभी पढ़ता हूँ, फिर दूसरे दिन पढ़ता हूँ, दूसरे महीने पढ़ता हूँ, तो टाइम लगता है। तो पेपर दैट शुड बी, इट मीन्स पढ़ने के लिए, करने के लिए बहुत टाइम लगता है। ओके, सो इट शुड नॉट बी लॉन्ग, टू लॉन्ग या टू शॉर्ट, है ना, ज्यादा लंबा नहीं होना चाहिए. इट शुड बी आई कैचिंग. इट शुड अवॉइड विमिसिकल या इमूजिंग वर्ड. अमेजिंग वर्ड मीन्स अमुज करने वाला वर्ड नहीं होना चाहिए इसमें. विमिसिकल मीन्स नॉट पॉलिश. डोंट पॉलिश, डोंट मैजिक. वी आर नॉट मैजिशियन, वी आर नॉट पॉलिटिशियन. So that it should be a simple words. It should not be amazing. It should be not amazing, amusing. Okay, not puzzling. It should avoid non-standard. Yeah, this is very very important. It should not. It should avoid non-standard abbreviation. Don't give non-standard abbreviation in your title unless and until defined. Okay. Author should adhere to the word count and specify the target journal. जर्नल का भी गाइडलाइन होता है. सो जर्नल आल्सो हैव द एवरी जर्नल हैव गाइडलाइन फॉर द टाइटल. Okay, so it should have 20 words, 10 words, 15 words. Okay, so this is about the title of article. Then next come to the abstract. हमारे मराठी में इसको कहते हैं, एब्स्ट्रैक्ट को कहते हैं अमृत. अब अमृत तो आपको मालूम है, अमृत तो यहाँ मिलता नहीं है. अमृत तो हमको हिवा विंटर में मिलता है, जो पेरू है ना. अगर अमृत अगर पीना है तो हमको ऊपर जाना पड़ेगा. So that is Amrut. It means abstract is very, very important. So this is the main point of your paper. As abstract summary is a preview of, I will not go in details because I have to complete the talk in within a 2 hours. Okay. So abstract summary is preview of what's to come. ओके, तो हमारा जो पेपर है, हमारा जो पेपर है, आर्टिकल है, उसमें इंट्रोडक्शन है, देन मटेरियल मेथड्स है, रिजल्ट डिस्कशन है, टेबल है, इमेज है, कंक्लूजन है ना. तो ये सब चीजें हमें एब्स्ट्रैक्ट में सब लिखने हैं. ओके, इट मीन्स पूरा सारांश यहाँ पे हमको आना है. ओके, ये चीजें हमारी होने वाली है. सो दिस टू बी हैव फन शुड बी लिटिल लेस टेक्निकल दैन आर्टिकल इटसेल्फ. ओके, तो इट शुड बी इन टेक्निकल वर्ड, साइंटिफिक वर्ड, वर्नाकुलर लैंग्वेज. इसलिए एक शब्द है, सो दैट इज कॉल्ड एज वर्नाकुलर लैंग्वेज. योर एब्स्ट्रैक्ट शुड बी इन द वर्नाकुलर लैंग्वेज. हमको फोकैलॉजी नहीं मारना है, हमको ज्यादा डिस्कस नहीं देना है, हमको सिर्फ कम से कम शब्द में. इसलिए हर जर्नल का लिमिटेशन होता है 100, 100, 150, 200, 250 या 300. उसके ऊपर तो होता ही नहीं है. ओके, शुड बी 1 पैराग्राफ. ओके, नॉट 2 पैराग्राफ, 3 पैराग्राफ. मैंने तो देखा है 2-2 पैराग्राफ लिखते हैं एब्स्ट्रैक्ट, ऐसे भी है. सॉरी, मीन्स 2-2 पेज लिखते हैं. सो इट इज नॉट टू बी हैपन. ओके, इट शुड बी इन 1 पैराग्राफ विच समराइज इन द प्रॉब्लम. व्हाट शुड बी समराइज. अभी एब्स्ट्रैक्ट में देखिए, व्हाट शुड बी समराइज. प्रॉब्लम्स, आपके स्टडी का प्रॉब्लम क्या है, मेथड्स, रिजल्ट्स एंड कंक्लूजन. ओके, समटाइम problem need not to summarize in your abstract. Abhi recently my paper is come to in the chemical papers which are under double R2 revision. So in my abstract we do not return the problem in abstract. Generally problem we are writing in the introduction. Generally, dear participants, generally problem I used to be written in the introduction, not to be written in the abstract. But as per the reviewers, you have to mention the as per the reviewer requirement, you have to mention the problem in the abstract. Okay, then this is the abstract. I will not go in. Okay, then most important thing is that no abbreviation or no citation in the abstract. Keep in mind, this is very very important. No need to cite, abbreviation without definition. Abbreviation without definition or citation in the abstract. This is very very important. Okay, so this is my abstract, one of the paper published in the ACS Omega, and this is the graphical abstract. Okay, so graphical abstract. So these are the graphical abstract. This is the graphical abstract in the nanoscale. Nanoscale is also one of the reputed journal of RSC. Okay, this is the RSC Advanced. This is RSC Advanced. Impact factor is 6. Okay, and this is the graphical abstract means मैंने आपको कहीं पहले बताया है. जैसे जैसा हमारा मूवी रिलीज होता है, पेपर में आती है, तो पेपर में 10 फोटो नहीं रहते, एक ही फोटो रहता है. तो यू हैव टू दैट न्यूज में तो एक फोटो रहता है, बट पेपर के जो रिलीज होता है, सॉरी मूवी, उसमें पूरे हीरो को कंबाइन किया जाता है. तो वैसा ही हमारे ग्राफिकल एब्स्ट्रैक्ट में यू हैव टू मेंशन, यू हैव टू graphical abstract and scheme is totally different. जमीन आसमान का फर्क है. The graphical abstract mean table of content. Table of content means what? हमारा कंटेंट क्या है. जैसा हम थीसिस लिखते हैं तो कंटेंट लिखते हैं, जैसा हमारा कुछ बुक है उसका कंटेंट रहता है. So this is the table of content of your paper. So this is called as, in one way, called as a graphical abstract. Okay, so nowadays the reputed publisher always keeping the graphical abstract in the front. Whenever you see the title, there will be, you find graphical abstract. Yes, it is called as a TOC. This is also another TOC of one of my paper. It is published in 2022 in the SS Omega. Okay, then next come to the introduction. So introduction is also a very important. So this is pivotal of the work. Work. Why I am saying the pivotal of parameters? Because the most of the reviewer, you are reading your introduction, because in introduction you have to summarize what things you have to summarize. You have to give the problem of your work. जैसा मैंने पहले बोला है आपको कि एब्स्ट्रैक्ट में प्रॉब्लम नहीं डालना है, रिवर बोलता है तो डालिए, या अदरवाइज एक सेंटेंस में डालिए प्रॉब्लम. बट इन इंट्रोडक्शन यू हैव टू फोकस ऑन योर प्रॉब्लम. व्हाट इज द लैकुना इन योर वर्ल्ड. आपको आपका जो वर्क है उसके पहले आप हाईलाइट करिए व्हाट इज द लैकुना इन द सोसाइटी. व्हाट इज द लैकुना इन द सोसाइटी ऑन द पर्टिकुलर वर्क, या पर्टिकुलर दैट टाइटल, है ना, कि जो आपका काम है उस काम में हमारे दुनिया में या सोसाइटी में कि क्या लैकुना है, वो आप लैकुना बताइए, वो प्रॉब्लम बताइए. देन कम टू योर मिनिमम देन कम टू योर वर्क. ओके, समराइज द रिलेवेंट लिटरेचर सो दैट reader will understand why this is an interest to expose the work. Highlight the problem of the present work. Okay, so this is main important. Highlight, just you have to highlight in one sentence, one paragraph on your project. जब आप डीएसटी के लिए प्रोजेक्ट डालते हो, जैसा मैंने डीएसटी के लिए मैंने प्रोजेक्ट डाला था. सो व्हेन I got first project in DST ACRB and then CSIR and CSRR DAE for minor grant for the conference. But then I got three to four times rejection from NRF and ACRB2 for because there are several reasons for funding, for that lack constraint of the funding, and sometimes some different reason. Okay, that is different. But a problem is very main for the introduction. Then highlight why author's work is more important. Then come to the next. Okay, after problem, then come to the next. Highlight why author work is more important. Why your work is superior, previous your lacuna, previous your problem. तुम्हारा जो प्रॉब्लम है उसके ऊपर आपका वर्क का क्या कंट्रीब्यूशन है, क्या तुम्हारा अचीवमेंट है, क्या तुम्हारा यानी लैकुना तो है, पेपर में लैकुना है, यानी कन्वेंशनल मेथड है, उस लैकुना है. तो फिर आपने क्या अचीवमेंट किया, आपने क्या तीर मारा, आपका क्या ग्लोरी है, आपका क्या अचीवमेंट है, तो वो आपको हाईलाइट करना है. सो दैट रिवर विल बी it means happy, it will be glad, so it will be impressed, we will impress. End with the sentence stating present work. Then come to the, then after that highlight the highlights why author work is more important. Then just focus on your work. Then emphasize on your review of literature of that particular work. अगर आपने प्लांट पे है तो उस प्लांट के बारे में बोलिए, कितने पेपर पब्लिश हुए हैं, कौन से देश में है, कहाँ हुआ है. अगर प्लांट है तो प्लांट का पूरा डिटेल बताइए, उसका जीनस क्या है, उसका स्पेसीज क्या है, उसका जियोग्राफिकल एरिया बताइए, कौन से देश में पाया जाता है, कौन से स्टेट में पाया जाता है, ईच एंड एवरीथिंग. देन एट द एंड यू हैव टू कंप्लीट योर पैराग्राफ एंड विद द सेंटेंस स्टेटिंग प्रेजेंट वर्क. यानी आप सेंटेंस, देन आप अपने लास्ट सेंटेंस में ये कर सकते हो, इन द प्रेजेंट वर्क वी आर पब्लिशिंग जिंक ऑक्साइड RGO nanoparticle using the Bombex Mori, using the bacterial cell line या plant cell line for the uses of different biological या photocatalytic degradation. तो ये आपका लास्ट सेंटेंस रहेगा, आपका लास्ट. देन कम टू द नेक्स्ट. 1 to 4 पैराग्राफ शुड बी इनफ. यानी ये याद रखना है कि आपका पैराग्राफ ज्यादा नहीं होना चाहिए, 1.5 पेज का होना चाहिए. योर पैराग्राफ शुड बी 3 to 4 पैराग्राफ, not 5 to 6 पैराग्राफ. योर पैराग्राफ शुड बी 4 पैराग्राफ. ओके, not 5 to 6 paragraph. Okay, you have to complete your paragraph within a 2 page, yeah, 1.5 page. Then next come to the So this is the paragraph of one of my reputed paper, SS paper. So this is the paragraph of a published paper. Then next come to the material and methods. बहुत सारे हम देखते हैं जब ये लास्ट टाइम हमारे आई आई मस्ट थैंक्स टू दी हमारे यूनिवर्सिटी में इन 2022 ऑनरेबल वाइस चांसलर चौधरी सर, लेट वाइस चांसलर चौधरी सर, और देन बोकारे सर एज वेल एज डॉक्टर मनाली शिवसागर मैडम, उनकी यानी अभी उन्होंने अभी यूनिवर्सिटी में हमारा प्रोजेक्ट चालू है, प्रोजेक्ट आते हैं, बट इट वाज आल्सो फाइन दैट कि प्रोजेक्ट में लोग डिजाइन करते ही नहीं है, मटेरियल मेथड्स या स्कीम देते ही नहीं, डायरेक्ट लिखते हैं, तो लोगों के बहुत सारे प्रोजेक्ट रिजेक्ट होते हैं। अरे बाबा, यूनिवर्सिटी यू आर गिविंग स्पॉन्सर इन 3 लाख फॉर वन प्रोजेक्ट, अब बाकी यूनिवर्सिटी का पता नहीं है प्रोजेक्ट मिलना नहीं, आई डोंट नो इट, पर बहुत सारी यूनिवर्सिटी में प्रोजेक्ट देता है, पुणे यूनिवर्सिटी में भी प्रोजेक्ट देता है, ऐसे पुणे है, लखनऊ है, बहुत सारी यूनिवर्सिटी में है, ओके। बट व्हेन यू आर डिजाइन योर प्रोजेक्ट, यू मस्ट डिजाइन द स्कीम। अगले रिव्यूअर को कैसा समझ में आएगा कि आपका वर्क क्या है? आप डिजाइन करते समय आपको ये नहीं करना है कि पर्टिकुलर वही, यू जनरल यू द डिजाइन। तो इन पेपर में भी वैसा है, पेपर में भी आपको ये ऐसी स्कीम बनाना है। सो दिस इज द दिस इज नॉट टेंटेटिव, दिस इज एग्जैक्ट, दिस इज नॉट प्लॉजिबल। ये आपने प्लान लिया है, आपने ऐसा किया है, इतना घंटा लगा है, इतना, या आपने सेंट्रीफ्यूज किया है, मपलिंग किया है, कैल्साइन किया है, और बाद में ये मिला है। So this is the material and methods to film. Just you have to highlight eye-catching diagram in the material and scheme. No need to highlight each and everything. Okay. Then result and discussion. So this is the very important in the your paper. Results. बहुत सारे लोग रिजल्ट एंड डिस्कशन में डाटा मैनिपुलेट करते हैं, ठीक है। डाटा मैनिपुलेट नहीं करना है, जैसा है वैसा लिखना है। मैनिपुलेट करेंगे तो पकड़े जाएंगे, ठीक है ना। तो मैनिपुलेट नहीं कर, जैसा है वैसा लिखे, जैसा डाटा है उसका वैसा लिखे, ठीक है। आपका डाटा कभी कभी गलत हो सकता है, बिकॉज यू आर नॉट एक्सपर्टाइज, कभी कभी डाटा आपका रह जाता है, कभी कभी डाटा आपका आप उसको इंटरप्रेट नहीं करते हो, माइनस सिली मिस्टेक है ना। डाटा आप इंटरप्रेट नहीं करते हो, कहीं इमेज आप, बट इमेज फिगर टेबल को साइड करना है, वो आपको जब पेपर आपका एक्सेप्ट होता है, पेपर एक्सेप्ट होने के बाद, सो आफ्टर गेटिंग एक्सेप्ट इन योर पेपर, एडिटर बोर्ड आपको गिव यू नंबर ऑफ क्वेश्चन, आपने इमेज नंबर 1 साइट नहीं किया है, टेबल नंबर 1 साइट नहीं किया है, सो दीज आर सिली मिस्टेक। बट कोई आपका जो इमेज को बराबर इंटरप्रेट नहीं करना, बहुत सारे में यू विल फाइंड, आई विल गिव यू 1000% कि देयर आर कपल ऑफ thousands of paper, the same term, FTR, bait, not explained very well. Okay, तो but ऐसा होता है, but you keep in mind, so for that require your supervisor and expert for the particular interpretation of the material. Okay, so result और result discussion में आपको ज्यादा citation देना नहीं है। ज्यादा citation किसको देना है? अगर आपको लग रहा है your work is your novel, your work is your new, okay na, if your work is new, your sentence is new, then you have, then for the support you have to give the citation. अगर आपको लग रहा है कि ये तो बहुत बड़ा अचीवमेंट है, बहुत बड़ा हमारा रिजल्ट आया है, फॉर दैट सपोर्ट यू हैव टू गिव द साइटेशन। अदरवाइज फॉर हर सेंटेंस को, हर पैराग्राफ को सेंटेंस साइटेशन देने की जरूरत नहीं है। अगर आपने साइटेशन दिया, इसका मतलब क्या है? इसका मतलब योर वर्क इज नॉट नोवेल, योर रिजल्ट डिस्कशन इज नॉट नोवेल, ये आपका रिजल्ट डिस्कशन नहीं है, आपने इसका मतलब दूसरे से लेके लिया है। सेम टू सेम सेंटेंस हम दूसरे का नहीं ले सकते। you will come in plagiarism, you will come in similarity, okay, and similarity हम पेपर सबमिट करते हैं तो we want now only 15% similarity of paper, unless and until 15% similarity your editor will not accept your paper, and on the editorial basis your paper will be rejected back. At the editor, I am not talking about the under review, at the editorial base, reviewer editor will be back. Okay, so result and discussion, highlight the significant results, but don't just repeat, बार बार वही मत करिए, डोंट रिपीट इट। सो दैट इज कॉल्ड एज, ओके, सो दैट इज कॉल्ड एज रिडक्टेंट, यानी पूर्वपंची, वही बातें मत करिए, दैट इज कॉल्ड एज रिडक्टेंट। अनले यूजलेस बातें आप बार बार मत करिए। टू द डाटा सपोर्ट द हाइपोथेसिस, अब तो जो मैंने कहा है आपका जो अचीवमेंट है, सो दिस इज द हाइपोथेसिस, गिव योर जस्टिफिकेशन फॉर हाइपोथेसिस, गिव द सपोर्ट। So result and discussion means this is you are going to be create you are going to be create your new hypothesis, your new achievement, your new line. एंड देन अगर आप न्यू हाइपोथेसिस देंगे, लोग बोलते हैं कि मेरे मेरे पेपर को साइटेशन ही नहीं मिला है। देखो दुनिया में बहुत सारे लोग हैं, उसके 200 पेपर है साइटेशन नहीं है, उसके 100 पेपर है साइटेशन नहीं है, उसके 50 पेपर है साइटेशन नहीं है। मैंने कल परसों मैंने आपकी तैयारी करने के लिए मैंने कल देखा एक ऐसा आदमी है, मेरे ख्याल से वो भिलाई का है, नहीं बिट्स पिलानी आई थिंक, वो मैथमेटिक्स का है। यू कैन फाइंड उसका साइटेशन 18,000 या 20,000 है, और उसके कम से कम 15 ही पेपर है, नहीं 8 का 9 पेपर है। 9 पेपर फॉर 9 पेपर गॉट साइटेशन 18,000 just search. No, I imagine because 2-3 paper got citation 4,000 3,000 for 9, है ना। तो साइटेशन किसको मिलता है? इफ यू राइट द हाइपोथेसिस गुड, यू राइट योर सेंटेंस यू गुड। जो मैंने आपको बताया है आप स्टार्टिंग में एडवांस मटेरियल एंड साइंस इंजीनियरिंग सी, दैट वाज माय फर्स्ट पेपर 2018 when I was in Stockholm for conference. When I was in Stockholm in Sweden, and next day I was in Finland. So in I was in Finland, I got a revision for that paper. That paper was of Ajay Purvares, and that was my first paper in biosynthesis. Now that paper got 195 citation. सो एंड वो पेपर मैंने इतना लिखा कि कम से कम उसको यानी एक एक सेंटेंस को मैंने ध्यान दिया है। सो यू गिव द योर क्रेडिबिलिटी, यू गिव योर दैट इज मींस यू जस्ट you give the mud over, mal over, and meditation when you're writing the sentence. Okay, so that is I have to say. You know, then our result consistent with what the other investigator supported. मैंने आपको पहले ही कहा, अगर आपका एक आधा सेंटेंस आपको लग रहा है इसको मुझे साइटेशन देना है, तब आपको सपोर्ट देना है ना। यू गिव द कंसिस्टेंट विद योर अदर इन्वेस्टिगेटर। अदरवाइज कि इट मीन सपोर्ट देना है, आपको लग रहा है कि ये डाटा मेरा बराबर नहीं है, बट अगर आपको बराबर करना है तब आपको इसको देना है सपोर्ट। ओके, इफ द रिजल्ट्स वेर अनएक्सपेक्टेड, ट्राई टू एक्सप्लेन व्हाई। देखो, इफ द रिजल्ट्स वेर अनएक्सपेक्टेड, ट्राई टू एक्सप्लेन व्हाई। उसको पॉलिश मत करिए, उसको अनएक्सपेक्टेड उसको एक्सप्लेन करो क्यों ऐसा हो रहा है, सर्च मारो, रीड करो। इज देयर अनदर वे टू इंटरप्रेट योर रिजल्ट? बट जैसा का वैसा मत करो और उसको साइटेशन मत दो। ओके, तो अनएक्सपेक्टेड रिजल्ट गेट नोबेल प्राइज, अनएक्सपेक्टेड रिजल्ट गिव द हाईएस्ट अचीवमेंट, अनएक्सपेक्टेड रिजल्ट गेट द हायर साइटेशन। समझ में आया? तो अनएक्सपेक्टेड रिजल्ट्स यू हैव टू एक्सप्लेन। डोंट लूज योर कॉन्फिडेंस, डोंट demoralize. You explain where you well that your that sentence. Do not give more citation. मैंने already कहा है, do not give more citation, give only specific citation. जहां लगता है वही साइटेशन दीजिए रिजल्ट डिस्कशन में, अदरवाइज ज्यादा साइटेशन नहीं देना है। आपको ज्यादा साइटेशन कहा देना है इंट्रोडक्शन में, प्रॉब्लम में, वहां आप जितना साइटेशन देना उतना साइटेशन यानी 25 30 40, ज्यादा नहीं देना है। ज्यादा भी साइटेशन नहीं देना है। रेगुलर आर्टिकल का साइटेशन होता है सिर्फ 50-60 दे सकते हो, 60-70 रन से, बट 50 स्टैंडर्ड एज पर कौन कहता है? मैं नहीं कहता हूं, कोप कहता है। व्हाट इज कोप? COP। व्हाट इज कोप? अ कमिटी फॉर पब्लिक इथिक्स। ये यूनिवर्सल गाइडलाइन है ना, जैसा SCI एक्सपांडेड, डबल SCI है ना, वेब ऑफ साइंस, क्लैरिवेट्स, ये है वैसा ही ये कोप है। कोप कहता है यानी रेगुलर आर्टिकल तो 50, रिव्यू आर्टिकल है तो आपको मोर देन 100, आप 200 दे सकते हो, 300 दे सकते हो साइटेशन। ओके, एंड विद द वन सेंटेंस समरी ऑफ द कंक्लूजन, जैसा आपने एब्स्ट्रैक्ट में लिखा वैसा ही यहाँ पे भी देना है। सो एंड विद द वन सेंटेंस समरी ऑफ द कंक्लूजन एम्फसाइजिंग व्हाई इट इज रिलेवेंट। बाद में आपको लास्ट पैराग्राफ लिखना है, व्हाट इज योर नोवेलिटी, व्हाट इज योर इनोवेशन, व्हाट इज योर नोवेलिटी, व्हाई इट इज नोवेल, why not it is a general, why not it is simple, why your work is novel, what is achievement. Just you have to mention, just you have to give the achievement. Okay, just you have to give the that highlight your sentence in the last paragraph. Okay, so this is about result. पेपर में आपका बहुत ही इंपॉर्टेंट है रिजल्ट एंड डिस्कशन. ओके, बट बट रेफरी को आपको इंप्रेस करना है, इंट्रोडक्शन बहुत इंपॉर्टेंट है, एंड देन कंक्लूजन. बट आपको अगर रिव्यूअर अच्छी तरह से पूरा रिजल्ट देखता है, मैं तो पूरे, मैंने जितने भी मैंने पेपर किए 300 से ज्यादा मैंने पेपर किए, मैंने रिव्यू मैं पूरा पढ़ता हूँ, और उसको इतना मैंने कम से कम 15 से 20 पॉइंट देता हूँ. दो 1 से 1.5 पेज में क्या बोलते हैं कमेंट देता हूँ. ये मेरा ये है. ओके, यानी मैं हर टाइम 15 के ऊपर मेरी कमेंट रहती है हर पेपर में. तो ऐसे समय में बहुत सारे रिव्यूअर आपको रिजल्ट डिस्कशन में भी आपको देते हैं. ठीक है, ये एक मेरा पेपर था, जस्ट द पेपर वाज नाउ, अभी आज सुबह हमारे डॉक्टर सुदीप मुंडल सर, ही इज माय कोलैबोरेटर, ही इज माय कलीग. जस्ट अर्ली मॉर्निंग आई गॉट acceptance from nanoscale advances. Nanoscale advances, this is my second paper. Nanoscale advances got acceptance from this paper. उसका दो पेज का, दो नहीं 4 पेज का कमेंट था, और 20 पेज का आंसर लिखा. एक मेरा केमिकल पेपर है, अभी जस्ट आ रहा है, 6 पेज के कमेंट आए, 32 पेज की रिपोर्ट बने हमने, 32 पेज की रिपोर्ट. ओके, सो दिस इज अबाउट द एक्सप्लेनेशन ऑफ दिस. ओके, सो द नेक्स्ट, so this is about result and discussion. Now see the how I write, जो मैं जिसका मैंने आपको बताया था कि ऐसा रिजल्ट डिस्कशन करना. Now see in the figure, in the earlier figure, the figure is scale 100 nanometer. first figure is 100 nanometer, second figure is 20 nanometer. देखो अभी मैं नैनो में आ रहा हूँ. 100 के अगर ऊपर जाता है हम उसको नैनो नहीं बोलेंगे. कोई भी अगर इमेज का अगर 100 ऊपर जाता है, पहले होता है 200, अर्लियर इट वाज 200, बट नाउ बड़े इट वाज, अगर 100 के रेंज में है तो इट इज नैनोमीटर, नैनो स्केल मटेरियल. देन कम टू द 20, देन कम टू द 10, देन कम टू द 5. मैंने वो मटेरियल को देखो मैंने कैसा आपको इंटरप्रेट किया और कैसा लाया है. सो मटेरियल इज 10 नैनोमीटर. 10 nanometer means it is just like a dot, quantum dot. So what is the quantum dot? A quantum dot will give the fluorescence. The quantum dot will give the size in 1 to 9, 1 to 9 या 10 nanometer scale. So that is called a quantum dot. Quantum dot, it may be carbon dot, it may be silicon dot, it may be copper dot. So this is quantum dot. It is a different property from the nanomaterial, different nanomaterial. So this is about the result and discussion of my previous publication. Yes, then at last, this conclusion of the last means the last of your paper, not last of your talk. Okay, so conclusion, this is the very, very, very important. So this is the final piece, this is the masterpiece. जैसा बोलते हैं ना मास्टरपीस, कोई अगर चित्रकार ने अगर चित्र निकाला तो उसको बोलेंगे मास्टरपीस, है ना. अभी तो हमें भी मालूम है, अभी जियोनार्डो लिंची ऐसा कुछ है जो, है ना, जो क्या नाम है, उसने जो पिक्चर निकाला था उसको मास्टरपीस बोलते हैं, है ना. लियोनार्डो विंची, है ना, वो जो निकाला था उसको मास्टरपीस बोलते हैं. सो मास्टरपीस मीन्स दैट इज अ गुड अचीवमेंट. So this conclusion means you have to wrap your idea in 50 words. जैसा होता है ना क्रिकेट में लास्ट ओवर, है ना, तो सो जस्ट लाइक यूर दिस इज द लास्ट ओवर और आपको मैच जितानी है. जैसा अभी अर्जेंटीना ने किसके साथ अभी मैच जीती है कल परसों, इजिप्ट के साथ. इजिप्ट में पहले 2 गोल मार दिए, लग रहा था जंग है. ओके, देन इजिप्ट फिर अर्जेंटीना ने मैच जीत लिया है. ओके, तो बिकॉज आप जानते हो कौन है हीरो वहां पे. ओके, सो दिस इज द मास्टरपीस, है ना. सो दिस इज द मास्टरपीस ऑफ योर पेपर कंक्लूजन. जस्ट यू हैव टू wrap your idea from where, not your abstract, not your introduction और abstract को गोली मारो. You are from result and discussion. अब यहाँ पे रिजल्ट एंड डिस्कशन, यहाँ पे तुम्हारा हीरो है. रिजल्ट एंड डिस्कशन से आपको आइडिया लेनी है, आइडिया ग्रैब करना है, ग्रैप्स करना है. सो फ्रॉम योर रिजल्ट एंड डिस्कशन से आपको आइडिया यहाँ पे लेना है. ओके, फ्रॉम योर मटेरियल, फ्रॉम टेम स्टडी वी रिवील दैट मटेरियल गॉट 9 nanometer. From base study it reveal that microporous, mesoporous, macroporous. From your same got the from same study we got the nano that nanosphere, microsphere, homosphere, then cube-like structure. So these words you have to use. That means that not common word, that is unique word you have to use. Okay, it is the final piece of writing of the articles. मैंने तो पहले से कहा है. So this is a masterpiece of your paper. Wrap your idea and leave the reader with strong final impression. इससे आपको रीडर को जो है, रीडर को आपको इंप्रेसिव आपको यहाँ पे आपको वर्डिंग करना है. Summarize your overall findings. Summarize your overall finding means you do not summarize your overall finding from abstract and introduction. I am repeating again and again. Don't wrap your idea from abstract and introduction. Okay, you wrap your idea from result and discussion. मैंने आपको पहले कहा था कि कंक्लूजन, इंट्रोडक्शन और सॉरी एब्स्ट्रैक्ट, इंट्रोडक्शन और कंक्लूजन बहुत इंपॉर्टेंट है. बट मैंने ये नहीं कहा था कि रिजल्ट एंड डिस्कशन बहुत बेकार है. रिजल्ट एंड डिस्कशन आपको कंक्लूजन का बहुत सपोर्ट करता है. ओके, समराइज योर ओवरऑल फाइंडिंग्स फ्रॉम द रिजल्ट एंड डिस्कशन. फाइंड आउट आउटपुट ऑफ द वर्क. कनेक्ट सिग्निफिकेशन ऑफ द वर्क. यस, और ये भी बहुत इंपॉर्टेंट है. यू हैव टू कनेक्ट योर कंक्लूजन विथ योर टाइटल एंड योर रिजल्ट एंड डिस्कशन. ये क्वेश्चन ही हर जर्नल में क्वेश्चन रहता है, रिव्यूअर को पूछा जाता है. when reviewer is submitting review report, at that time the reviewer always asking this question, that is the conclusion part is support with the result and discussion या title. अगर उसने ना बोला your paper will reject. Then next, also suggest possible future research. It means, last line you have to give the in conclusion. So what is your future plan, या future study of your material? Okay, so this is the very, very important. Okay, so this is about conclusion. Then apart from the your paper, so many things have to be asked while your submission. Nowadays, since last 5 to 6 years, these things has to be asking for the authors. Acknowledgement. Okay, so acknowledgements, you have to acknowledge those person. मैंने पहले ही कहा है, किसी ने पेपर के लिए पैसा दिया है इसमें मेंशन करो, पेपर में नहीं. पेपर में नाम किसका देना है? जिसने साइंटिफिक कंट्रीब्यूशन है, पेपर को रिव्यू किया, पेपर का इंट्रोडक्शन लिखा, रिजल्ट डिस्कशन लिखा, इमेज. एक पेपर में 300 नाम हो सकते हैं. आर यू लिसनिंग? एक पेपर में 300 नाम हो सकते हैं. यू कैन add your 300 author. You see in Nature, see your in Lancet paper, see in your clinician of journal of clinician, that having impact factor 685. There you will find number of authors. तो उसका contribution होना है, हर एक का contribution देना है. So you can mention in acknowledgement. Then author contribution यहाँ पे देना है. अदर कंट्रीब्यूशन नाउ सी, मैंने पहले आपको कहा है कि तो व्हाट इन मोड कॉन्सेप्चुअलाइजेशन, यानी उसका कॉन्सेप्ट देते समय किसने बोला क्या, अरे ऐसा अपने को करना है, ये अपने को पेपर पब्लिश करना है, आई विल गिव यू प्लान. क्योंकि प्लान तो मुझे, बिकॉज माय कोलैबोरेटर इज डॉक्टर सुभाष सोमकुमार. आई एम ऑलवेज सेइंग इन माय टॉक, इन माय नेशनल इंट्रो टॉक, डॉक्टर सुभाष सोमकुमार इज very, very well, it means erudite professor and taxonomist and botanist. मैंने कई बार उसके जैसा मैंने कम आदमी देखा है नहीं. अरे प्लान ढूंढने के लिए गाड़ी हमको रुकाना पड़ती थी, वो कलेक्ट करके लाता था. मैं उसकी अतिशयोक्ति नहीं दिखाता हूँ, बट ही रियल रिसर्चर. मेरे स्टूडेंट भी उसको कहते हैं कि सही बनना पड़ेगा उसको. और उसमें अपने न्यूज़पेपर में देखा हूँ उसके पेपर पब्लिश, उसके प्लांट कोई स्पेसीज पब्लिश हो. आज और सुबह 2-3 न्यूज़पेपर में आया है. तो ये जो प्लांट हम कलेक्ट करते हैं, उस प्लांट का आइडेंटिफिकेशन हम नहीं कर पाते. उसका जीनस क्या है, उसका स्पेसीज क्या है, वी डू नॉट हैव आइडिया. उसके बाद उसमें फाइटोकेमिकल क्या है हम पता करेंगे, बट उसका हर्बेरियम बनाना, उसको नंबर देना, वो हम नहीं करते. सो दिस उस प्लांट का काम वही कर सकता है जो एक्सपर्ट है. तो ये हो गया. देन माइक्रोबियल एक्टिविटी हो गया, एंटी फंगल हो गया, एंटी बैक्टीरियल हो गया, वायरस स्टडी हो गई, देन ओबेसिटी, एंटी ओबेसिटी हो गई. ऐसे बहुत सारी है. उसमें बहुत सारे आप नाम लिख सकते हो, बट उसमें आपको डालना है डाटा क्यूरेशन, फार्मर एनालिसिस, देन एनालिसिस करते समय आपने क्या क्या इंटरप्रेट किया, फार्मर एनालिसिस मीन्स दैट इज योर एनालिसिस करते समय आपको किस किसने आपको हेल्प किया, सपोर्ट किया और इंटरप्रेट किया। मेथोडोलॉजी, मेथोडोलॉजी करते समय आपको किसने आपको हेल्प किया। रिसोर्सेस, रिसोर्सेस मीन्स व्हाट, रिसोर्सेस मीन्स यू हैव टू गिव द नंबर ऑफ रिसोर्स, प्लांट कलेक्शन, फील्ड वर्क, है ना, number of sources, visualization study, supervision, super means your supervisor, mentor, writing original draft, बहुत सारे इसमें सभी का लगेगा कंट्रीब्यूशन, ठीक है, बट स्टूडेंट मेन होता है इसमें। राइटिंग, रिव्यूइंग, एडिटिंग, इसमें बड़े बड़े लोग होंगे जो एक्सपर्टाइज है ना, तो रिव्यूइंग, एडिट करना, रिवीजन आएंगे तो एडिट करना, रिव्यू करना। देन कम टू द कंप्लीट ऑफ इंटरेस्ट, देन कंप्लीट ऑफ इंटरेस्ट, एवरी जर्नल आस्किंग द कंप्लीट ऑफ इंटरेस्ट। ऐसा नहीं हो जाए पेपर पब्लिश होने के बाद उसको आप क्लेम कर सकते हो, अगर आपने ये कंप्लीट ये स्टेटमेंट नहीं दिया तो यू कैन क्लेम योर, यू कैन क्लेम टू जर्नल कि ये मेरा पेपर है, आप मुझे रॉयल्टी दो या फाइनेंशियल पैसा दो। तो इसीलिए वो पहले से लिख के ले लेते हैं, हमको लिख के देना पड़ता है, ऑथर डिक्लेयर नो कंप्लीट ऑफ इंटरेस्ट, फाइनेंशियल या अदरवाइज जो भी है, तो ये लिख के देना। देन डाटा अवेलेबिलिटी स्टेटमेंट, डाटा अवेलेबिलिटी स्टेटमेंट इज वेरी वेरी इंपॉर्टेंट, कि ये आरएससी वाला लेता ही है। क्यों लेता है, क्योंकि जब whenever you are going, whenever you are submitting your paper, just you have to give the statement all the data included in the manuscript। अगर आपके पास सप्लीमेंट्री नहीं है, just you have to mention कि all the data are included in the original manuscript। अगर आपके पास manuscript supplementary है, then you have to write down the data supporting this article have been included as a part of supplementary information। अगर आपने गलती से लिख दिया कि डाटा सपोर्टिंग दिस आर्टिकल हैव बीन इंक्लूडेड एज अ पार्ट ऑफ सप्लीमेंट्री इंफॉर्मेशन, फिर बाद में पता चला कि आपके सप्लीमेंट्री में डाला ही नहीं है, सिर्फ ओरिजिनल में है, तो फंस गए। देन यू विल गेट, देन यू विल बी इन ट्रबल। ट्रबल तो नहीं होगा, यू विल गेट द पब्लिकेशन, बट देन आपको झेलना पड़ेगा, बार बार मेल आएगा, सबमिट करो, फिर आपको मेल करना पड़ेगा, सॉरी सॉरी सॉरी, तो ऐसा होता है। ओके, सो दीज आर दी स्टेटमेंट अदर फ्रॉम योर abstract, introduction, result discussion and conclusion। okay, so अब उसके बाद मेन इंपॉर्टेंट, आपने पेपर लिख लिया, अब पेपर लिख लिया आपने, पेपर लिखने के, अब पेपर लिखने के उसके बाद में जाएंगे हमने, तो पेपर के हो गया, देन उसका रेफरेंसिंग, पेपर पूरा तुम्हारा तैयार हो गया, कंक्लूज भी नहीं हो गया, देन यू हैव टू अरेंज द रेफरेंसेस। सो रेफरेंस अरेंज, so there are many types of referencing, that is APA। so APA means association of psychological, American Association of Psychological, American Psychological Association, then APA style, then MLA, so that MLA, then MHRA, Harvard, Vancouver, Oxford and Chicago। so these are the styles, ठीक है, humanity, okay, then medical science, okay, and the pharmaceutical science, there are different referencing, okay, but APA, MLA, MHRA, Harvard, Vancouver, Oxford and Chicago, these are very popular। APA, MLA, Harvard, Vancouver and Chicago, these are always using Elsevier, Springer, then Nature, okay, and reputed publisher। Then these are the reference styles, okay, okay, I have arranged, these are reference style, but your reference should be in single format, okay, it should be in single format। so this is the this reference, I have arranged this reference, that MLA styles, okay, in MLA styles, okay, that first author, then name of article, then volume, then year, then page number। ओके, एमएलए आप उसमें एपीए में जाइए तो ईयर पहले आएगा, शिकागो में जाइए ईयर आपको आफ्टर ऑथर में आएगा, ऐसा डिफरेंट अलग अलग है। तो आप बट वेन यू आर यूजिंग द रेफरेंस स्टाइल, रेफरेंस स्टाइल शुड बी सिमिलर। ओके, देन अब आपने पेपर अपने पूरा लिख लिया, सो यू फुल्ली रिटर्न योर पेपर। नाउ द क्वेश्चन इज अराइज इन योर माइंड, वेयर शुड आई पब्लिश माय डाटा, वेयर शुड आई पब्लिश। So these are the okay, so these are the indexing. Okay, so these are indexing as well as a publisher. These are reputed publisher. I already stated you that the Nature, Springer Nature, ACS, RSC, Elsewhere, Ville, PLOS, Frontier, Taylor and Francis, IOP, ICE, Institute of Civil Engineering, then Institute of Engineering Electronics, okay, then CRC Press, Cell Press, Dow Press, MDPI, BMC, Oxford University Press, Bentham Science, Degruter is also good, but he's a predator. Hinwi is also predator. Bentham Science predator. MDB predator. Frontier predator. PLOS predator. APA. APA means American Physical Association. American Physics Association. Then Iowa Institute of Water Association. Then SAGE, etc. These are, apart from this, there are several publishers. Okay, so these are reputed publisher. Why these are reputed publisher? Why it is reputed publisher? Because these are indexing in SCI and Scopus. These journal have Thomson impact factor. Okay, sorry, don't say Thomson. It is a Clarivate impact factors. Okay, so next, again we have to see where should I publish my data. So while choosing your journal, you must see foreign paper always seeing the while publication their data, they must seeing the whether journal is SCI. देखो जर्नल को इम्पैक्ट फैक्टर कब मिलता है, स्कोपस अगर इंडेक्सिंग मिलता है तो उसको इम्पैक्ट फैक्टर नहीं आता है. स्कोपस इज द एल्सवेयर कॉन्सेप्ट. अगर आपको मालूम नहीं पता है एल्सवेयर, साइन डायरेक्ट और स्कोपस में क्या फर्क है, किसी को मालूम है स्कोपस, साइन डायरेक्ट और स्कोप फर्क, बाद में आप पूछना मुझे लास्ट में, ठीक है. अगर आपको क्वेश्चन पता है तो अच्छी बात है, नहीं पता है तो यू कैन आस्क. साइंस साइटेशन इंडेक्स, these are the publishing, that is citation indexing, SCIE, then double SCI, double SCI, that is for social science. Scopus, Web of Science, emerging source citation index. Oh, emerging source citation index is old, okay, but nowadays it is not using because it is delisted because of some reason. I will tell later on. Then site score. Okay, site score is the concept of elsewhere. Site score is impact. Site score is also calculated impact factor, but that impact factor is called as site score impact factor, not Clarivate impact factor. Site score impact factor is different and Clarivate impact factor is different. Then Google Scholar is a simple indexing, cross-ref, that getting DOI. A cross-ref is very, very important. DOI number is very important for the paper. DOI is nothing but आधार नंबर ऑफ पेपर. जैसा हमारा आधार है वैसा ही पेपर का आधार है DOI, डिजिटल ऑब्जेक्ट आइडेंटिफायर. रिसर्च गेट, केमिकल एप्टा, कैश, पबमेड, journal citation. Journal citation report is very, very citation report. On the basis of journal citation report, it gives the impact factor, and it was that established by the ISI. ISI means what? Institute of Scientific Information, by Eugene Garfield in 1968. Okay, then Clarivate impact factor, SGR is also very important indicator. It will give the Q1, Q2, Q3 indicators. That is quartile 1, 2, 3, 4. Nowadays Q1, Q2, Q3 is very, very popular. Okay, that SGR means SciMago journal rank. It gives the Q1, Q2, Q3 on the specific subject. So question is arise, where should I publish my data? देखो मैं कई बार आपको कह रहा हूँ कि मैं पेपर अपना कहाँ सबमिट करूँ, एनएसएस में करूँ कि आरएस, यानी कौन से पब्लिशर में करूँ, कौन से इंडेक्स में करूँ, कौन से साइटेशन इंडेक्स में करूँ, या Q1 में करूँ या Q2 में करूँ. So what is Q1, Q2? Q1, Q2 give the journal quality and quantitative. Q1 give the rank of journal. Q1, Q2, Q3 give the rank of journal, whether journal is in Q1 or Q2. So what do you mean by Q1? So Q1 means the journal, those journal are included, those journal in Q1. So what do you mean by Q1? So Q1 is best. Q1 means best of 25 journal in the specific subject. In specific subject means chemistry, physics, botany, zoology, chemical science stream, biological science, material science, space science. So that is there are various branches, there are various types. So that is called as Q1, and it will classify it in the different ways in what way, faculty as well as subject as well as stream. Okay, so Q1, so under top 25%. Q2 next 25 means 26 to 50%. Next Q3 51 to 75%, and Q4 means that is listed bottom at the 100, it means 25%. सबसे last week journal, and that is generally that is this Q4 is this young budding researcher. जब छोटा अगर नया रिसर्चर है तो सबसे पहले वो छोटे मोटे जर्नल में सबमिट करता. So this is basically for the young researcher. Okay, so journal quartile ranking is a method used to classify journal based on their impact and citation metrics. This quartile enable both author and reader to assess journal. आप बोल सकते हो, you give your credibility that कि मैंने Q1 पेपर में छापा है, मैंने SCI स्कोपस में छापा है. आपको SCI स्कोपस पेपर छापने के लिए कई 10 साल लगते हैं. मुझे तो अनेक कई पेपर, मुझे कई जर्नल ऐसे है, कई बार मैंने पेपर सबमिट किया, आई गॉट रिजेक्शन. 15 साल के बाद 18 साल के बाद मुझे एक्सेप्टेंस मिला है. तो इतने सो Q1 Q1 में छापना और SCI स्कोपस में छापना, इट इज वेरी क्रेडिटेबल. The Q1, Q2, it categorized journal into 4 quartiles: Q1, Q2, Q3, and Q4. Q1 being to the top 25%, Q2 that then next 25%, Q3 next 25%, and Q4 at the bottom lines. Q1, Q2, Q3 are the best on the academic impact. अब ये classifies कैसे करते हैं? How it classifies? That is based on impact factor. Academic impact, there are simply on the base, not even on the base of impact factor. It is based on the how many citation metrics. It means SCI, Web of Science, then expanded, then CAS, then JCR, Clarivat. बहुत सारे indexing है. Scopus and journal citation report. Okay, Scopus site score, then Clarivat site score, JCR site score, like that. Scopus uses different metrics called site score. Okay, to calculate quartile, which can vary slightly from JCR ranking. So this is already I stated, top 1, top 25, 25 to 25. Okay, so these are for the various peoples or various expertise, there are various researchers on the basis of their categories. Now, then question is arise, where should I publish my data in the journal? That is, कौन से जर्नल में पेपर मैं अपना करूं, है ना? तो बहुत सारे लोगों को पता ही नहीं रहता कि कहाँ करूं, कहाँ पे करूं. ओके, और मेरा खुद का नॉमिनेशन या अचीवमेंट किस पे बेस पे है? सो बिकॉज ऑफ मेरा क्रेडिबिलिटी, मेरा नॉमिनेशन कौन से बेस? सो ऑन द बेस ऑफ एच इंडेक्स. जिसका ज्यादा एच इंडेक्स got more citation, that is due to the research impact. Now see, more H index based on the citation, more citation based on the research impact. Those are C. So what is the citation? How can we define citation? Ladies and gentlemen, हम किसको citation बोलेंगे? Just small over, mediate, just small over, brood over and mediate. हम किसको cite बोलेंगे? क्या citation हम किसी को देंगे क्या? किसको citation बोलेंगे? So citation means just see. These people always cite in the social media. As Modi Sahab, Honorable Prime Minister of India, Rahul Gandhi ji, then China's president, और Iran and America war, then Israel and Ukraine war. These 4 guys are more popular than man, who that scientist, okay, that missile man. Then लता मंगेशकर, अमिताभ बच्चन का रोल कोई नहीं कर पाता, ना आप कर सकते ना मैं कर सकता, वो लता मंगेशकर कोई नहीं बन सकती, मिसाइल मैन कोई नहीं बन सकता. सभी को डांस करना आता है, पर माइकल जैक्सन नहीं बन सकते हो आप, आइंस्टाइन नहीं बन सकते हो आप, कैलाश सत्यार्थी नहीं बन सकते हो. नोबेल प्राइज 2014 में मिला था, दैट इज लेटेस्ट, सेकंड लेटेस्ट, और 2023 में अभी मिला है इकोनॉमिक्स के लिए. और रिचेस्ट मैन नहीं बन सकते हम, बन सकते एक दिन, बट उसके लिए बहुत डेडिकेशन करना पड़ेगा, है ना? दीज आर द आइकॉन्स ऑफ द वर्ल्ड. और नेशनल मंडेला, है ना? सो ही ऑलवेज साइड, एंड दीज आर द एक्नॉलेजमेंट फॉर द एवरी टॉक, इनवाइटेड टॉक, रिसोर्स टॉक, एंड सो मेनी टॉक्स. बिल गेट्स, रतन जी टाटा, सचिन तेंदुलकर नहीं बन सकते, बट अभी लोग बन रहे हैं. कोई रिकॉर्ड तोड़ा है, बट सचिन तेंदुलकर. Or my favorite, John Cena, he never tap down, never tap down. ओके, जब भी जैन सिन्हा की मैच लगती है मैं देखता हूँ, है ना? तो दीज आर द आइकॉन्स. अब इसके अलावा बहुत सारे लोग हैं, मैंने कुछ कुछ लिया है, सॉरी टू से. बहुत सारे आइकॉन है, बहुत सारे पॉपुलर पीपल है इन
हेलो
वर्ल्ड.
प्रोफेसर
बहुत सारे
चौधरी
लोग
सर.
हैं, बहुत सारे लोग हैं.
Professor Chaudhary sir, sorry to
जी.
interrupt you sir.
यस.
So actually we have to move for the next session. Can we conclude sir?
Yes, okay. Within 5 minutes I will complete.
Yeah,
Okay.
yeah, sir.
Okay. So these are so many icons who are cited. Okay. So these are the citations. So reference, published and unpublished sources. So it means you have to give the published work, unpublished works. That is called citation. Then you have to avoid the plagiarism. Then citation should supply detail to identify the unique. So these are the citation we have published in our work. Now see in the blue color. So this is called citation, and these are the reference of citations. Then what is impact factor? So impact factor is nothing but, now see, the citation ratio in two preceding years. So total number of citation ratio, अगर हम 2026 का बोलते हैं तो 2026 का citation 2026 के पेपर को नहीं मिलेगा. We will get to citation 2025. So 25 impact factor किसका निकालेंगे? 24 का और 23 का. Okay, so total paper published 2024 and 2023, and total number of total paper published 2024 and 23. It means citation ratio in 24 and 23 paper published divided by total number of published 24 and 23. So that is called as impact factors. And these are a highly cited journal in the world. The Cancer Journal of Clinician. Many times I have asserted. Cancer Journal of for Clinician, impact factors 685. The Nature Review Molecular Cell Biology, that 118. The Lancet, third number 109. Nature Review Microbiology, and this Nature Review Clinical Microbiology. Okay, so then next, what is H index? हम बोलते हैं H index क्या है, H index क्या है? So before that, my H index is 35, but मैंने खुद का मैंने कल मेरा G index निकाला. अब H index सबको मालूम होगा, but G index is totally different. अब मेरा H index 35 है, बट मेरा G index 59 है, 60 नहीं है. मैंने 60 करने गया पर हो ही नहीं रहा है, 59 है. तो मैंने गूगल को पूछा, मैंने AI को पूछा, कुड यू आइडेंटिफाई G index ऑफ रतिराम कुमार जी चौधरी? तो वो कहता है रतिराम कुमार जी चौधरी H index is more than 35, but we could not determine right now because Ratiram Chaudhary published so many publications. Ratiram Chaudhary published 125 publications, but here his H index is 35, but his G index is 35, but his probably H index is 35 more than 35 in G index. So how it is G index is calculated? So this is the H index. Everybody knows how H index is, H index is calculated. I know that most of the people know how H index is. G index is that अगर दो आतर है, दोनों आतर का H इंडेक्स अगर सेम है, अब एक आतर है, एक बंदा है, एक रतिराम चौधरी है, एक दूसरा है सुनील चौधरी, दोनों भाई हैं, दोनों का एक बंदे का साइटेशन टोटल साइटेशन है 102, दूसरे भाई का साइटेशन है 63. अब दोनों का एच इंडेक्स सेम है, मतलब ऐसा कैसे हो सकता है? अब दोनों तो भाई है, दोनों भाई है, बट एक का तो काम ज्यादा है. अब मैं बड़ा भाई हूँ, मेरा भाई छोटा भाई है. मैं यंगर ब्रदर इज इंग्लिश प्रोफेसर, मैं केमिस्ट्री प्रोफेसर हूँ. अब मेरा एच इंडेक्स 60, मेरे पब्लिकेशन 125 है. अब मेरे भाई के 20-25 होंगे. ठीक है, अब तो समझाने के लिए आपको बता रहा हूँ. अब दोनों का एच इंडेक्स सेम है 6. अब ये तो 9 सा भी है, दोनों का एच इंडेक्स सेम है और टोटल साइटेशन ज्यादा है. So that G index is nothing but, that is the unique largest number such that top G article received together at least G square citation. It means अगर उसके 10 दोनों के 10 पेपर है तो 10 पेपर मीन्स 10 मीन्स 10 to power 2, तो 100 होना चाहिए. दूसरा अगर दूसरा है अथर, उसके भी 10 पेपर है तो उसका भी 100 होना चाहिए था, बट उसका टोटल साइटेशन हुआ 63. तो इसका मतलब उसका जी इंडेक्स कम है, उसका 100 नहीं है, उसका जी इंडेक्स 63 है, मेरा जी इंडेक्स 100 है. तो इसका मतलब तो author 1 having the G index 10 and author 2 G index is 6. So this is about the difference between H index and G index. So these are some books which are published during my tenure of 2020, 2014 to 2026. These are some publication from elsewhere: Springer Nature, MRF, Cell Press, Ville, and Stanford University. So once again, thank you so much, my collaborators, my different collaborators. I have not listed a few more collaborators from the different countries. These are my collaborators from my college and my university, other university, and some abroad. And as well, I thank once again. I thank you so much, Professor Kodabe Madam and Santa Gadge Baba, Amravati University, Amravati, for giving me opportunity to interact with young budding researchers and participant of the refresher course chemistry. Thank you so much. Thank you. A unique query you can discuss.
Thank you, sir. Thank you so much for such a wonderful session. Participant, if having any queries, we will take 1 or 2 questions and then we'll continue for the next session. Is there any questions? Sir, I think there are no questions. So if you could permit, shall we conclude, sir?
Yes, yes, yes. Thank you so much. Yes.
So now may I request Dr. Vijay Kumar ji to please propose vote of thanks. Dr. Vijay Kumar ji, I think it's your turn. Whose turn this is for the proposed vote of thanks?
Sir, this is
Yeah,
Rakhi
please.
Bankar.
Yeah, ma'am, please.
Yeah, this is good afternoon, one and all present here, respected organizing committee members, esteemed resource person, and your participants. So, on behalf of all the participants of this online refresher course in chemistry organized by Santa Gadge Baba Amravati University, Amravati, under Malviya Mission Teacher Training Program, I take great pleasure in proposing a vote of thanks. First, I express my sincere gratitude to Dr. Ratiram Saudhary sir, our resource person, for sharing such a valuable insights. Your expertise, clarity of thoughts, and practical examples have truly enriched our understanding of the topic, writing scientific research articles and research indexing. We thank you, sir, for addressing our questions and encouraging the interactive discussions very patiently and meticulously. We appreciate your effort that you took to make the complex concept and complicated concept into simple and relevant way, which will definitely help us in our professional as well as in our academic and research growth. Thanks once again to all of you. Thank you to the organizing team members for giving me this opportunity to propose a vote of thanks. Thank you for all your cooperation. Over to you, Ankit sir.
Thank you, ma'am. Thank you, Professor Ratiram sir. And with the kind consent of Professor Ratiram sir, I would like to declare that this particular session will be over here. Thank you so much, sir.
Yes, sir. Thank you.
So, participants, I think we should move for the next session. Hello, Professor Ghorpade sir.
Yes, good afternoon, sir.
Sir, very good afternoon, sir. Very good afternoon. If you could permit, shall we start with the session, sir?
Yes, sure.
First of all, I extremely sorry because we have taken already 15 minutes from your allotted time.
No, so it's okay because the link was there, no, with her, and the conclusion was very important. So don't worry, sir. It's
Thank
okay.
you, sir. Thank you, sir. So, first of all, I extend my warm welcome to Professor Prashant Ghorpade, sir, once again to this refresher course and with the same session because on the highly demand session is there. Therefore, the Prashant Ghorpade, sir, is right now here to enlighten us on a very important and a very, very important and the basic topic, sir. So, on behalf of all the esteemed gathering, I extend my warm welcome once again and request you to please start with your session, sir, please.
Okay, thank you for that, sir. Okay, so welcome back. The basic principles of NMR spectroscopy, we left somewhere, having the del values, right? So a bit of recap, I'll go. We have started with this light, different electromagnetic spectrum, wavelength, then frequency and everything. Then we approach to the absorption line spectrum, wherein it's the absorption of one single line can be plotted against all are present, only one is absent. So that is absorption spectrum. Then emission spectrum. Once the excited molecules comes down to the ground state, it emits certain radiation. That if that radiations are detected, that becomes a emission line spectrum. Then we had a discussion on X-ray, ultraviolet, infrared. What are different energy transitions related to this? So in here we can see this is X-ray, that is bond breaking and X-ray diffraction we can say about it. Ultraviolet visible, electronic, infrared vibrational, that is microwave rotational, and radio frequencies, nuclear and electronic spin. Then we did assume what is nucleus and how spinning nucleus is it behaves like tiny magnets, right? And then different spin states for various nuclei. For example, hydrogen, it has plus half and minus half. For 13C, plus half and minus half, right? So we do have done all these exercises. Spin quantum numbers for different elements. We have done this. Spin quantum number for 1H is half, 13C is half. These are two important in organic chemistry. So we have both 13C and 1H with the same spin quantum number, and allowed spin states are two, plus half and minus half. For 1H also plus half and minus half. Others are there, but we are less bothered about all these nuclei because we more concentrate on 13C and 1H. Then we have seen the nuclei when there is no external magnetic field, they are randomly oriented and they are degenerate energy levels. There is no energy separation between them. But once you apply a magnetic field, the nuclei align themselves or oppose themselves. These are the two, plus half and minus half, two allowed spin states. They align or oppose. And due to this external magnetic field, they have different energies. Plus half bit stable because it is aligned, and minus half bit unstable at higher energy level because it is opposing to the external magnetic field. And we know that the energy difference, it is the function of B naught. More B naught, that is external magnetic field, more is the energy difference between lower and higher energies of this plus half and minus half steps. Then the excitation process, electromagnetic radiation, if the energy matches, the plus half goes to minus half, it jumps to minus half. Okay, then yes, frequency depends upon the strength of external magnetic field and identity of nucleus, whether it is hydrogen nucleus, whether it is 13C nucleus, and external both. It depends upon both these. And field strength, if it is 4.7 Tesla to 7.0 Tesla, radio frequency 200 megahertz is needed for 1H and 50 megahertz needed for 13C. So it depends upon the nucleus as well as the external magnetic field. Then we considered how NMR is obtained. The sample is dissolved in suitable solvent like CdCl3 and placed into the instrument, and we scan it for several times, and then we get the output. And the output is a spectrum where we nomenclate it as downfilled and upfilled. There is 0 where the signal of TMS is there. So tetramethylsilane, we have considered that also. This is experimental part we have seen. Then these are the various operating frequencies, and these are the excess nuclei, which is beneficial for the strong signal. More the excess nuclei in lower energy state, means plus half, will get the good signals or clear signals in the NMR spectrum. Then local diamagnetic shielding we have seen because of the electrons present in the bonds and lone pairs of the environment which is near to the proton or near to the carbon, right? And these electrons, bonded electrons, they circulate in such a way that it opposes in the center and aligns in the periphery. So what happens? The proton or the nucleus which is resonating experience less applied field, because applied field is V naught, it cancels by induced magnetic field. So some of the applied field is cancelled by induced. The experienced magnetic field is lesser than what we are expecting, and this is called a shielding effect. And electrons, they shield the nucleus because in external magnetic field electrons start circulating in such a manner that it opposes in the center and aligns in the periphery. Then we have seen this cloud of electrons. There is a nucleus in the center, and it opposes the external magnetic field V naught, this circulation of electrons. And with the right hand thumb rule, we apply a right hand thumb rule to the circulation of electrons. Electrons circulate in such a way that at the center of the nucleus, the lines of forces are opposing to the lines of forces of B naught, and cancellation of magnetic field takes place. And this nucleus is said to be shielded. Okay, then how del values can be calculated? These are the formulas. This is operational frequency, 100 megahertz or 60 megahertz, and we know that the fraction remains same. So the formula takes a shape of del is equals to shift in Hz from TMS. This is shift in Hz in particular any instrument. It may be 100 or it may be 60, whatever it may be, the shift in Hertz divided by spectrophotometer frequency in megahertz. So say for example, it is 8 Hertz, shift is 8 Hertz in 100 megahertz. So 8 divided by 100, that becomes the del value. And we call it chemical shift. Okay, this is a scale. This is a del scale, and TMS, that is tetramethylsilane, absorbs at any value. It is considered as 0, and from here the other signals are shifted. So that is called as shifting of the signal. And on del scale, it is from 0 to 12 to 13 in case of 1H NMR, and it goes to 250 in 13C. The negative side of this scale can be shown for more shielded electrons, more shielded protons as compared to TMS. Am I audible to everyone?
Yes, sir.
Okay, okay. So this is all we have done. This is a recap. Yes, this was the slide where we have seen all the hydrogens are equivalent chemically and magnetically. We have taken examples also. We have done exercise over this, and then we have gone for trans and cis. These are the hydrogens or protons which absorb at different values because they have different environment. So this has 3 different signals, for one for this hydrogen, one for trans, and one for cis hydrogen. And in this way, we have example of magnetically different protons. Then in case of benzene ring, also we have seen how chemically equivalent and magnetically equivalent protons are there. Here, these protons are chemically equivalent, but they are magnetically non-equivalent and having different signals. Okay, fine. this was the last slide that we have seen that day, right? Hello?
Yes, sir. Yes, sir.
Okay. This is very simple compound. CH3COO, this is ester, right? There is aromatic ring. There are aromatic protons, CH2 and CH3. There are three signals, right? We can see 1, 2, and 3. 0 is here. It is out of the sight. So this is zoom version of the spectrum. So we can see that at around 2.05, we have a signal. There is another signal at 5.1 or 5.5 maybe. Sorry, 5.05, and then in 7.3. So there are three signals, and it has shown something, this thing, 55.5 divisions, 22 divisions, and 32.5 divisions. This is the area under peak, or it can be, we say it is integration of the peak. Now, NMR gives us, variable information, variety of information. In that, first thing, it gives us how many different protons are present, depending upon the signals. So three signals, three different protons. Magnetically, uh, different protons, or chemically different protons. Three signals means three different protons. Then in each signal, how many protons are present? It is, fortunately, it can be compared with the peak height. This is a peak height, or area under peak. This peak height can be calculated from area under peak, and this area under peak corresponds to the hydrogens present on that carbon. So particularly this proton, when we are observing the signal, there are two. So 22 corresponds to 2, 32.5 corresponds to CH3, 55.5 corresponds to the 5 aromatic protons. So more the number of protons, the peak height would be more. Okay, or area under peak will be larger for higher number of protons for the same signal. The signals oscillating at same time, they are giving you same Del value, and the height, peak height, corresponds to the number of protons here. Okay, this is the chemical shift regions for different protons. We'll have a look. And in here, direction of scan is shown from this side to this side. So the scanning starts from higher end to TMS, right? So if we go from 12, the higher end of the Del values, you can see the carboxylic acid absorbed between 12 to 10.5 or 10.2 or 10, it may be. It varies with the environment of the molecule. Okay, so always remember, at higher end, this carboxylic acid group is absorbed. And aldehydes, 9 to 11. 9 to 11, it is shown up to 10, but sometimes it goes to 10.5 up to 11. So there is little overlap between these two regions, but still we can identify what the aldehyde group and carboxylic acid proton absorption signals in NMR. How to do it, we'll consider it later. But we are just seeing what are the different chemical shifts for different protons. Then the region comes, very important, aromatic region. It starts from 6.5 to about 8.5. So in this region, if you find a signal that corresponds to the protons which are directly attached to aromatic ring. This is highly deshielded, and all the deshielded protons are coming towards left hand side, and shielded zone is towards right hand side and towards zero signal. Now, after aromatic region, which is spread from 6.5 to 8.5, we are having the vinylic protons, which are directly attached to double bonds. These protons absorb between 4.5 to 7. So little overlapping is also here because of the different reasons. We can have, definitely we can identify whether it is aromatic or vinylic proton. But some overlapping could be there. Then we have these highly electronegative element, fluorine, chlorine, bromine, iodine, oxygen, NO2. These are electron withdrawing groups, and that's why the CH2 absorbs between 3 to 4.9, 4.8 around this region. All these absorb. Then the range for OH and NH, it's overlapping from 0 to, it could be 5 or 6. Okay, so OH, NH, and these are the protons which absorb all over this, depending upon the environment. And the signal is not, normal signal. It is it's like a speed breaker in the spectrum. You can see, OH and NH, and it is substitutes with deuterium. So we also call these protons exchangeable protons. So they get exchanged and the signal vanish when you add D2O. We have discussed that day, right? And then the protons which are attached to a carbon, which is in turn attached to aromatic or amine or sulfur or acetylenic and aldehydic aldehydic groups, these absorb between 1.5 to 3. This is the range for them. And then, methyl, methylene, and methine protons, they absorb between 0 to 2. This is the range. Okay. So we'll again revise all these del values with specific signals. Here, protons on CH3, all three absorb at one value, and the range is 0.7 to 1.2. Whilst methylene protons absorb at 1.2 to 1.4, and methine absorbs at 1.4 to 1.7. Can you give me some reason for this?
Inductive effect of the alkyl groups.
Electron releasing effect, right?
Yes, releasing effect.
Okay. Okay, here
Electronegativity, electron withdrawing effect of the halogens.
yes, more the electronegative atom, the electrons from carbon bromine or carbon iodine, carbon chlorine bond, they are attracted towards the elements, iodine, bromine, and chlorine. And due to that, these carbons, they are now del positive, right? So in turns, they take the electrons towards themselves. More the electronegative element, higher would be the pulling of the electrons. So hydrogen becomes more bare or more deshielded, and hence the higher values. Okay, more deshielding, the signal would shift towards the higher end of the spectrum. Okay, so that is electronegative effect. Then again, we can compare all different kind of protons. This is one example where this proton presents on the carbon, which is in turns present to the double bond. So the value is higher than expected, 1.6 to 2.6. Okay, because of the electronegative effect of double bond, as well as it can be the hyperconjugation effect, right? These electrons can be shifted here, so this becomes more bare and all. Logically, we can say that this proton absorb higher value because of presence of the double bond with alternate single bond over here. Similarly, the protons which are attached to carbonyl, carbonyl group, and then CH3 or CH2 or CH, it is 2.1 to 2.4. When hydrogen is attached to ester or carboxylic acid, then it is 2.1 to 2.5. Similar to this, but little to higher side because of the more electronegative effect of carboxylic than ketonic or aldehyde group. Then cyanide is attached to the carbon. The proton will absorb at higher value again, 2.1 to 3, depending upon the rest of the structure. What is structure over here? On that basis, there is a range 2.1 to 3.0. And then this is benzylic proton, right? Benzylic proton is around 2.3 to 2.7. Acetylenic proton 1.7 to 2.7. Now here this value is lower than expected. Why? We will see in next few slides. Okay. This is, we have learned electronegativity, how electronegativity affects del value. Okay. So fluorine has 4, so del value 4.26. Oxygen 0.5, so chemical shift 3.4, and chlorine 3.1, so 3.05 del value are corresponding to the higher the electronegative element attached to the carbon to which these protons are attached, they absorb at the higher chemical shift values. Okay, again we are considering bromine, iodine, then hydrogen. In case if you consider CH4, then it would be 2.1 for hydrogen, the electronegativity, and the value of del is 0.23, very near to 0. So this is substitution effect. More number of electronegative atoms attached, higher would be the value. See here, 1 bromine 3.3. Okay, then 1 chlorine 3.5, 05, 2 chlorines 5.3. Now it is merged with the vinylic protons, right? 1 more chlorine, it goes to aromatic region. So CHCl3, that is as del value for that is 7.27, and so on. Yes. Okay. Can somebody explain me this trend?
उसको भी उठा लेते हैं.
Hybridization affects SP, SP2, SP3. SP3 has more less character, and there will be more left negativity.
Yes, percentage.
Okay.
Percentage character.
Okay. Okay, correct. Then
But here,
what effect is there of S character on del value?
More the S character, more the del value.
More the S character,
More del value.
higher will be the del value.
Yes.
I think that. Okay. Anybody else can explain this?
More character, more
For the strain ring, the bonds are bent bonds, which actually
Okay.
shield the hydrogens, and it obstructs the magnetic field. That's why
Correct.
the del value is in the shielded zone for the strain ring.
Okay,
And
fine.
for 3 degree, 2 degree, and 1 degree, this is observed according to the normal trend.
Okay.
So for the tertiary
sir, 3 degree is more shaded.
tertiary hydrogen will be in the deshielded position. because it is outside the periphery of the bulky CCH3 group. That's why it is experiencing more magnetic field. That's why it is in the dishielded region.
So also
Good explanation.
tertiary one has three alkyl groups. So there are three. It has the electron releasing effect of the three groups. So it will cause more shielding, sir.
More sending, if it
No,
is
no,
causing
it is
more
it is
sending, it
it
should
is
be
in the
towards,
dishielded
yes, it is in the deshielded one. It should be
region
towards zero, right?
because the bulky as the bulkiness is increasing, the hydrogen is becoming out of the periphery of the electronic magnetic zone.
Okay, steric hindrance.
That's why
He's saying about steric hindrance. If steric hydrance increases,
yeah,
the
and
carbon hydrogen bond
yeah,
will be, little longer, and due to that,
right.
the hydrogen becomes bare, and due to
Hydrogen,
that,
yeah,
the
hydrogen is
uh,
experiencing more magnetic field. It is
more,
in
yes,
the
yes,
dishielded
yes,
zone, and for the strained ring, the bonds are bent, which are
yes, yes.
which are shielding the hydrogen's electronic field. That's why the
Okay,
hydrogens are in this shielded region for strained ring.
okay, agreed for this tertiary, secondary, and primary. What about strained rings like this one?
For this
Why
strained ring,
hydrogen is shielded here?
look at this bond, this
Sir,
CC
because it
bonds.
has more hydronegativity. Escalator is more. Percent escalator is
Yes,
more at that
yes,
carbon.
yes, yes. Yes, here the character of hybridization can explain this. Here he is saying
Yes,
that yes character in this carbon hydrogen bond is
decreasing.
more. No, higher yes
No,
character, because these bonds are banana shaped
no.
bonds,
Yeah,
and
banana shaped bonds.
if they has to be banana, their p character should be higher, and if p character over here is higher, the s character would be higher towards hydrogen, and they will be closer to the nucleus because of the s character, higher electron density over hydrogen, and so it is shielded, and
Yeah.
that's why they are
Yeah,
towards the
actually, this in this strained rings, the sp3 character is little bit shifted to sp5 character.
yes, sir. That is the explanation. And we can again have some, thought on hyperconjugation with this primary, secondary, tertiary. Tertiary hydrogen may have higher hyperconjugation, so that the H plus character, or the deshielding of this proton is more as compared to primary one. We know that
Sir,
no
can I add
hyperconjugation.
something?
Yes, sure, sir.
So I forget the journal, but somewhere I find a theoretical paper around 2010 years back or 12 years back. So there is a special electron distribution for the cyclopropane and cyclobutane, which makes
Okay,
it
sir.
cyclopropane ring around 0.2, and cyclobutane, the CH is much deshielded, like a deshielded in comparison to a normal CH in a acyclic compounds. So they found the
Okay.
CH of cyclobutane around say 1.1, around that,
Yes,
due
yes,
to
yes.
the electron distribution.
Okay, because cyclobutane is folded, and it is like what do you say, that envelope, or no, not envelope. It is folded. It is just four carbons. It has the shape of when you fold a square, right? At the two corners, it becomes the two carbons of cyclobutane at one plane, and two other are at other plane. So due to that, somewhat as bond angle is towards 109.45 towards the standard tetrahedral angle. So electron distribution is little bit regular in cyclobutane as compared to this cyclopropane. That's why it is little
Because the less
deshielded than.
strained are more close to the normal angle.
Yes, it goes to the normal angle.
Thank you.
Okay, that is good insight. Thank you, sir. Okay, then yes, of course, acidic hydrogens, they are more bare, and they absorb at the extreme left end of the spectrum, that is del 12 or del value 10 to 12, because of the acidic character. These two electrons can be shifted between C double bond C, and this proton becomes more and more deshielded, so that higher del value. This is the typical ranges for acidic protons. Like acids, we have extreme left end, that is deshielded zone. Phenols 4 to 7. Alcohols, they are spread over high range. Okay, and it depends upon the R group and the environment also. In what solvent it is placed, hydrogen bonding and all. Intramolecular, intermolecular hydrogen bonding plays very important role in the del value of particular alcohols. Diluted alcohols, pure alcohols, we have different del values for each situation. Amines also having the protons attached to nitrogen 0.5 to 5. So same, alcohols and amines, they are situated in the same region. Amides, again 5 to 8. Enols, because this hydrogen is acidic, it is above 15. So it absorbs at if a situation is there, many a times it is keto-enol tautomerism. But if the compound is stable in enolic form, then that compound particularly gives good signal around 15. So that is one of the important characteristic of compounds which are stuck into enol forms. Okay. Again, it is hydrogen bonding. Free dilute solution 0.5 to 1, and hydrogen bonded concentrated solution. Why the change is there in del ppm? Can we discuss this?
Electronegative oxygen withdraws electron from the oxygen, causing deshielding.
Okay, that is fine. But we are talking about
Because of
dilute
hydrogen.
Dilute solution of alcohol and concentrated alcohol. If I take NMR of the same alcohol, concentrated and dilute, I have different del values. Why this is so? The answer lies in hydrogen bonding, right? If I dilute the solution, these ROH molecules are away from each other. They have intermolecular distance will be increased because of the dilution, and due to that there is weakening of hydrogen bond. And once the hydrogen bond weakens, this hydrogen is near to oxygen, and now it is shielded. So we'll get del values between 0.5 to 1. But when I increase the concentration of alcohol, the alcohol molecules, they come closer to each other in concentrated solution, and the hydrogen then gets hydrogen bonded with the oxygen. And due to this, what happens? This original oxygen and hydrogen bond length increases. An increase in the hydrogen bond length, oxygen hydrogen bond length, this hydrogen becomes bare, deshielded, and that's why it absorbs that higher del value. So we have also reasoning for this in this way. And we are having hydrogens situated at heteroatoms. If they are situated at heteroatoms, we can have a specific test that is called as exchangeable hydrogen test. We can add the deuterated solvents, right? And this deuterated solvent will replace the hydrogen from heteroatoms, and due to that, the signal for these hydrogens, it is absent in the spectrum. One spectrum is scanned without these solvents, deuterated solvents. The another spectrum, we add deuterated solvent like D2O or any other solvent, and then scan the spectrum. After that, we realized that one of the signal which was due to OH has now vanished in the spectrum, or it is absent in the spectrum. That concludes the signal specifically present in the first spectrum was because of the heteroatom attached to hydrogen. So carboxylic acid, phenols, alcohols, amines, amides in that case, they are replaceable with deuterium when you added D2 to it. And due to this exchange, this proton does not get absorbed in NMR spectrum. Okay. sp and sp2 hydrogens, what happens to these? sp hydrogens, they are present in acetylenes, right? And sp2 in vinylic situations. See this deshielding of sp2 proton in 1H NMR, right? Okay, सबसे पहले मैं बता देता हूं कि ये जो है this hydrogen, it is not there. This is the mistake in the image. This image is created using ChatGPT. So this is the hydrogen. This hydrogen should not be there. This hydrogen should not be there. So that is the mistake in this image. This I have taken this for understanding. It's showing us, you know, circulation of pi bonded electrons, right? Usually we see the local diamagnetic shielding. The electrons around the nucleus, they start circulating in external magnetic field, causing little local diamagnetic shielding, and the nucleus gets, you know, shielded depending upon the cloud of electrons present around it. जैसे जैसे इलेक्ट्रोनेगेटिव एलिमेंट्स उस क्लाउड को अपनी तरफ खींच लेते हैं, प्रोटॉन्स बेयर हो जाता है और वो डिशील्डेड जोन की तरफ चला जाता है. नाउ व्हाट इफ the pi bond is present in the in between the two carbons, and to it, if proton is present, what happens to this hydrogen? Will it be shielded? Will it be deshielded? The answer lies in the anisotropic effect. The anisotropic effect is the effect of circulating electrons on the del value in the NMR spectrum because of pi bond circulation of pi bonded electron. Local magnetic shielding was due to sigma bonded electrons. So sigma bonded electrons can be, you know, attracted towards the higher electronegative atom, and shielding, deshielding happens with the protons present on here. But what happens with the pi bonded molecules? Here is the example: carbon double bond carbon. Now, when these alkenes are placed in external magnetic field, the pi cloud of pi bonded electrons, it starts circulating, and in this manner, so that it opposes, or it opposes in the center. The lines of magnetic forces, they are opposing to the external magnetic field here, and it completes in this fashion so that it is aligned on the periphery. So in periphery, the magnetic lines of forces are aligned with the B naught. Now the protons which are present in this area where the circulating electron magnetic lines of forces aligned with the B naught will experience higher external magnetic field than provided. जितना दिया गया है B naught, उससे भी ज्यादा इसको external magnetic field महसूस होगा, and due to that, what will happen? The energy gap between plus half and minus half will rise, and due to that, the higher del value would be required to resonate this kind of protons. So del value for such protons would be higher. We say this is a deshielded protons, and this zone is said to be deshielding zone or deshielded zone. This is shielding zone where lines of forces are opposing the external magnetic field. Rest of the area or rest of the environment is said to be deshielded, and in vinylic protons are present in deshielded zone, and that's why these protons absorb near 4.5 to 6.5 ppm, right? Local if there was only local diamagnetic shielding, then these hydrogens would absorb at the del value nearing towards 2, 1 to 2, between 1 to 2, del 1 to 2, but they are absorbed at del 4.5 to 6.5. This is due to anisotropic effect of the double bond. Okay, you can see this area in this lines of forces are opposing, but in here they are aligned to the external magnetic field. That is called as B induced magnetic field. Induced magnetic field is aligned with B naught in the area. Am I clear with this? So higher energy is required. Pi electrons create an induced magnetic field that adds to the external magnetic field at sp2 proton, and these sp2 protons, they feel deshielding and they are down fluid shift in between del 4.5 to 6.5. Am I clear with this?
Yes.
Okay, thank you. Okay, this is what? Benzene, right? Benzene also have pi bonded electron, and it has 6 pi bonded electrons. It is a cloud above and below the ring. And how it behaves in external magnetic field. When benzene placed in external magnetic field, the molecules arrange themselves in such a way that the pi bonded clouds start circulating, and the induced magnetic field is generated. In here also, in the central part of the ring, it is opposing to the external magnetic field. Lines of forces, you could see the lines of forces, they are completing in this fashion. So generally, when it is a bar magnet, lines of forces start from north pole to south pole, right? Lines of forces in bar magnet, they travel from north pole to south pole, right? That is the observation. Do they travel from south pole to north pole somewhere? कहीं पे वो साउथ पोल की तरफ से नॉर्थ पोल की तरफ जाती, आपको पता है कहीं जाती है क्या ऐसे?
सेंटर में सर।
दैट इज मैं तो बार मैग्नेट के बारे में बात कर रहा था। ये तो ठीक है, ये सिचुएशन है बेंजीन का, बट बार मैग्नेट में आपने एक्सपेरिमेंट किया होगा 12th में या 11th में, हम लोग सभी करते हैं। नॉर्थ पोल से लेके वो कंपास लेके वो हम ड्रॉ करते हैं, तो नॉर्थ पोल टू साउथ पोल की तरफ वो सारे लाइंस ऑफ फोर्सेज जाते हैं। इसी तरह हम लोग उसको ड्रॉ किए थे अगर बार मैग्नेट यहाँ पे है तो नॉर्थ टू साउथ ये तो पता है, लेकिन साउथ टू नॉर्थ भी होता है लाइंस ऑफ फोर्सेस, बट दे आर इनसाइड द मैग्नेट। इनसाइड द बार मैग्नेट लाइंस ऑफ फोर्सेस आर south pole to north pole. Similarly, over here, if we consider the lines of forces in the center, they are, south to north. So these are opposing to the B naught, opposing to the external magnetic field. But what happens, you see here, lines of forces are aligned here, and we are concerned about the protons only. Protons are placed in the region where lines of forces are opposing B naught. So B naught plus induced magnetic field. और यहाँ पे तो अभी वहां पे 2 ही इलेक्ट्रॉन्स थे जो सर्कुलेट हो रहे थे, यहाँ तो 6 है, तो हायर मैग्नेटिक फील्ड यहाँ पे ऐड होगा, और ये प्रोटॉन्स और भी डिशील्ड होंगे, जितने की डबल बॉन्ड H के वाइनेलिक के थे उससे ये फिनाइल प्रोटॉन्स ज्यादा डिशील्ड होंगे because of the circulating of these 6 pi electrons, the cloud of electrons above and below the benzene ring, and that is called as diamagnetic anisotropy in benzene. Deshields the protons the value goes to 6.5, del value 6.5 to 8.5, depending upon the other environment. See here, this is the direction of circulation, so that with right hand thumb rule, you can find the North Pole downwards. So lines of forces are like this. And this is the region where hydrogens are present. 6 hydrogens, all 6 are symmetric, and all 6 are in de-shielded zone or de-shielded region, right? This is the shielding. In some cases, what if I replace this hydrogen by carbon, again carbon, again carbon, again carbon, and if I got carbon over here above the benzene ring, this carbon having protons, these protons would be shielded, and they can be absorbed near zero or below zero because of this shielded region. Okay. We have ANSA compounds and the benzene rings, para carbons. If we replace both the hydrogens, and if we have structure like this, the protons present somewhere here are more shielded, and the del value of these hydrogens, if some other compound is there, okay. In benzene, all the 6 protons are in de-shielded zone, and the del value, it's 6.5 to 8.5. What happens with anisotropy of acetylene? What happens? Acetylene, there is a triple bond, right? So there are 4 electrons in pi bond. These 4 electrons, they start circulating around the bond. And we know in every situation, molecules, they try to be stable. When external magnetic field is applied, acetylene arrange itself in such a way that these pi electrons circulate around the bond. And in the middle, it has got the lines of forces opposed, and in periphery, lines of forces aligned to the B naught. And these protons, acetylylic protons, being linear in the structure, they happens to fall in the shielded zone. Now, if they are shielded, del value should be like that only. So these protons are upfilled. They are absorbed at near zero. So we have seen the value of acetylic protons. See this benzene? This cone is shielded zone, and all the remaining environment is de-shielded. So inside the cone, shielding is there. Protons are present, de-shielded. So 6.5 to 8.5 or 8. In here, again, this is shielding zone for vinylic protons, and vinylic protons are 4.0 to 6.5. Yes, one more compound, aldehyde, one more functional group, aldehyde, right? Aldehyde has, this is the shielding zone, and the proton, aldehydic proton, it is outside the shielding zone. So the proton on carbon of the carbonyl absorbs at 9.0 to 10.0. 9 से 10 के बीच में aldehyde का proton पाया जाता है, because it is present in the environment, de-shielded environment, as well as it is attached to the carbon, which is directly attached to electronegative oxygen. That's why this proton is highly de-shielded, absorbs at del 9 to 10. Okay. And acetylylic proton, you can see this region is shielded, and this is de-shielding zone. So protons, this is the only example in all the 4 where protons are in shielded zone, and that's why the del value is upfilled 1.7 to 2.7. So this is diamagnetic anisotropy present in different functional groups. Am I clear with this?
Sir, in case of aldehyde group, Is it actually the effect of magnetic anisotropy or the electronegativity of the oxygen? It makes its
It's
del
both.
value very high.
It is both.
Both.
It is combination of both anisotropy as well as the deshielding. It combines together, and that's why it's absorbed at higher value. Carboxylic acid, in carboxylic acid, the proton is acidic. That's why it is bare proton, right? But that is not the case in case of aldehydes. Aldehydes, this hydrogen is not acidic and bare, but due to anisotropy as well as electronegative effect, in both they combine together to give you del 9 to 10. So both the effects are combined here. Okay. Again, these are the different regions of del values of different compounds. This is 13C values for different carbons. Similar kind of theoretical assumptions and statements and rules applies to 13C. जैसे 1H में होता है वैसे ही 13C में ही भी होता है. Del value जो shielding, deshielding depends upon the environment, electromagnetic effect, your electronegativity, hydrogen bonding. So many basic concepts are altogether applied, and the spectrum can be explained with the help of all these particular concepts. So in 13C, the carbons shown in red, they are absorbed in these regions. Now there is, it's not thumb rule, but many a times it matches, like say for example you are having a carbon on which hydrogen is there, right? And that hydrogen has given some del value, say for example 2. The carbon, if we observe the carbon 13C NMR of that carbon, and the value of del value of that carbon would be multiplied by 20. So it would be del 40 for that carbon. Okay. This is not thumb rule, but many a times it matches like that. कहने का मतलब ये है कि कोई मिथाइल ग्रुप है जिसके हाइड्रोजन एब्सॉर्ब हुए हैं 2.0 पे, तो उसका जो कार्बन है 13C में एब्सॉर्ब होगा 40 पे. So any del value multiplied by 20 becomes your range of that particular carbon. Similarly, if we consider 6.5 to 8 and to 2, so 150 would be aromatic region. See this aromatic region, it's written 150. So 6.5 to 8.5 for proton, and it is 100 to 150 for aromatic carbons. Okay, समझे आप लोग?
It is an approximation only, sir.
हाँ, it's approximation. Okay, this is a simple spectrum. It looks like methanol. This is OH, and this is methyl. Now, again, one more, addition to the information by NMR. NMR से हमें अभी तक पता चला कि कितने डिफरेंट प्रोटॉन्स हमारे कंपाउंड में है. उसके बाद पता चला कि हम पीक हाइट से पता चला कि करस्पॉन्डिंग सिग्नल में कितने प्रोटॉन हो सकते हैं. अगर हमने टोटल ऐड कर दिया डिवाइडेड बाय नंबर ऑफ प्रोटॉन्स कर दिया, तो हमें अप्रोक्सीमेशन मिल जाता है कि इस सिग्नल में कितने प्रोटॉन्स है. फॉर एग्जांपल, इसमें 3 हाइड्रोजन्स प्रेजेंट है, इसमें एक ही हाइड्रोजन प्रेजेंट है. ये किससे पता चला? पीक हाइट से या एरिया अंडर पीक से हमें पता चला कि यहाँ पे 1:3 होगा. ये एरिया 1 है तो ये 3 है. सो 1:3 अगर है, इसका मतलब यहाँ पे 3 प्रोटॉन्स है और यहाँ पे 1 प्रोटॉन ने एब्सॉर्प्शन दिया है. दिस इज सेकेंड इंफॉर्मेशन दैट वी ड्रॉ फ्रॉम NMR. नाउ, third information can be drawn from NMR is that on the basis of spin splitting. What is this spin splitting? अभी हमने देख लिया कि एक न्यूक्लियस है जो रेजोनेट हो रहा है किसी वैल्यू पे, वहां पे एक्सटर्नल मैग्नेटिक फील्ड में रख दिया उसे, और इलेक्ट्रोमैग्नेटिक रेडिएशंस उसके ऊपर बम्बार्ड कर रहे हैं हम लोग, एंड दिस पर्टिकुलर न्यूक्लियस इज रेजोनेंस, ये बिजी हो गया है, ओके। लेकिन उसके बाजू में अगर दूसरा हाइड्रोजन है, दूसरा प्रोटॉन है, एंड इफ दैट प्रोटॉन इज रेस्टिंग मीन्स वो एनर्जी एब्सॉर्प्शन नहीं दे रहा है। अगर वो एनर्जी एब्सॉर्प्शन नहीं दे रहा है तो आइदर वो दैट एक्सटर्नल मैग्नेटिक फील्ड से अलाइंड होगा या तो अपोज्ड होगा। अगर वो अलाइंड है तो इट इज एडिंग बिट टुवर्ड्स द बी नॉट एक्सटर्नल मैग्नेटिक फील्ड एक्सपीरियंस बाय द रेजोनेटिंग प्रोटॉन। अभी मान के चलते हैं हम लोग, यहाँ पे दो कार्बन है, दोनों के ऊपर दो अलग अलग हाइड्रोजन है, एंड ये इन्वायरमेंट अलग है, ये इन्वायरमेंट अलग है, ऐसे अगर हमने कंसिडर कर लिया तो ये प्रोटॉन अगर मैं रेजोनेट कर रहा हूँ कोई फ्रीक्वेंसी देके, इसको मैं हायर एनर्जी पे भेज रहा हूँ, फिर वापस आ रहा है, फिर भेज रहा हूँ, तो इसको बिजी कर दिया मैंने इलेक्ट्रोमैग्नेटिक रेडिएशन डाल के, ठीक है, स्कैनिंग कर रहा हूं मैं इसका, तो ये तो रेस्टिंग में है। अगर ये रेस्टिंग में है ये तो अलाइंड हो सकता है, दूसरे मॉलिक्यूल में अपोज्ड हो सकता है। सो प्रोबेबिलिटी ऑफ हैविंग अलाइंड एंड अपोज्ड इज 50-50 फॉर दिस सिचुएशन। तो अगर अलाइंड है तो इसका खुद का मैग्नेटिक फील्ड इसमें ऐड हो जाएगा, अगर ये अपोज्ड है तो एक्सटर्नल मैग्नेटिक फील्ड को ये अपोज कर रहा है तो इसका एक्सपीरियंस मैग्नेटिक फील्ड का कम होगा। सो अगर अपोज्ड है तो लेस डेल वैल्यू में आएगा, अगर अलाइंड है तो ये वाला जो रेजोनेट हो रहा है ये हायर वैल्यू में आएगा, एंड दैट इज कॉल्ड एज, ये जो इफेक्ट है बहुत कम होता है, शिफ्टिंग ऑफ द सिग्नल इज वेरी लिटिल, and due to that it doesn't have different signals but the same signal splitted into two. That is called as spin splitting. इसमें कोई दिक्कत है आपको समझने में, या आई एम सक्सेसफुल इन explaining this?
Sir, it is okay.
Okay, thank you. Going on next, you can see that अगर ये सेंटर में वो एब्सॉर्ब होने वाला था तो एक सिचुएशन में अलाइंड होने की वजह से वो हायर वैल्यू पे चला गया सिग्नल, एंड तो प्रोबेबिलिटी विल बी 50-50, विल गेट दिस डबलेट, दिस इज कॉल्ड एज डबलेट। ये सिचुएशंस बताई गई है यहाँ पे। दिस इज रेजोनेटिंग प्रोटॉन, sorry, this is resonating proton. In one case it is aligned, in other case it is opposed. This is resonating, so overall field experienced by this proton would be different in two scenarios. Probability is 50-50, so there is splitting of the signal. So this would be the actual del value of the signal, but now half of the protons they are absorbed here, half of the protons are absorbed here, so the signal is splitted into two, and this is called as doublet. Okay, there are HA and HB. You will have two doublets, one doublet of HA because of B, and other doublet of B which is because of A. So doublet of doublet will be a situation. Okay, it's a very simple exercise. थोड़ा आपका concentration भी fresh रहेगा, mind fresh हो जाएगा। Splitting pattern हम बता सकते हैं इसका? इसका हाँ, इसका डबलेट मिलेगा, इसके लिए ट्रिपलेट मिलेगा। हाँ, यस, ट्रिपलेट मिलेगा।
वन ट्रिपलेट और वन डबलेट।
हाँ, वन ट्रिपलेट एंड वन डबलेट। दिस इज द स्पेक्ट्रम, एक्चुअल स्पेक्ट्रम ऑफ दैट मॉलिक्यूल। दिस इज डबलेट एंड दिस इज ट्रिपलेट। दिख रहा है नहीं दिख रहा है, मुझे तो क्लियर नहीं दिख रहा है, बट यू कैन मेक इट आउट। ये ट्रिपलेट है और ये डबलेट है। इंटीग्रल 2, इंटीग्रल 1, तो एक ही प्रोटॉन यहाँ पे रेजोनेट हो रहा है, यहाँ पे दो प्रोटॉन रेजोनेट हो रहे हैं, ठीक है, दो प्रोटॉन्स रेजोनेट हो रहे हैं। इसका डबलेट है और इसका triplet। चलिए आगे। ओके, दिस इज quartet for CH2, right? And triplet for CH3. Clear? Next slide.
Yes, sir.
This is the spectrum. This is taken from some book. तो इसीलिए ये जो क्रॉस हेयर्स में उसमें से डिलीट नहीं कर पाया, लेकिन वी कैन मेक आउट दिस इज ट्रिपलेट और दिस इज कॉर्टेट। कॉर्टेट कैसे दिखता है देखिए यहाँ पे, और ये ट्रिपलेट है। ओके, इसमें कितने सिग्नल्स रहेंगे?
Two signals.
दो सिग्नल्स।
Two signals.
दो रहेंगे।
दो और स्प्लिटिंग पैटर्न
A doublet and multiplet.
मल्टीप्लेट।
सर सिंगलेट एंड दोनों सिंगलेट सर। मल्टीप्लेट।
6 equivalent neighboring protons will give you septet.
Multiplet
And
or singlet.
multiplet, you can call it multiplet because it seems like multiplet only. Septet clearly दिखता नहीं है, वो multiplet ही दिख जाता है। और ये 6 प्रोटॉन्स के लिए डबलेट हो जाएगा। See this doublet for 6 protons, right? And this is septet. ये मल्टीप्लेट ही दिखेगा, देखो 1 2 3 4 5 6 और 7। इसको थोड़ा वो जो एमनोवा वगैरह आता है उसमें आप जूम करके देख सकते हो कि सेप्टेट है, अगर रॉ फाइल आपके पास है तो।
Can I add one point here?
Yes sir.
Actually, in high resolution spectrum, septet is clearly visible. So
Yes,
basically,
yes,
NMR greater than septet is called as multiplet.
Yes, septet above
Sep-
quintet it is called as multiplet.
Yeah, septet is not always considered as multiplet.
Okay sir.
It is.
Agreed sir. Okay, if x and y are not equivalent, the situation becomes doublet of doublet. Okay, in this is doublet, triplet, doublet, quartet. These are the different situations, right? If a proton is not coupled, singlet would be, and at the mean position the signal stands. And if it is coupled, there would be shifting of two situations, and the distance between these two is called as coupling constant. ये constant होता है। constant क्यों कहते हैं इसको? Because this shifting or splitting is same in all the operating frequencies of the instruments. 100 मेगाहर्ट्ज में भी सेम रहेगा, 500 मेगाहर्ट्ज में भी सेम रहेगा स्प्लिटिंग, और 600 मेगाहर्ट्ज में भी सेम रहेगा। इसलिए जे वैल्यू जो है वो कांस्टेंट रहता है किसी भी इंस्ट्रूमेंट में। दैट्स व्हाई इट इज कॉल्ड एज कपलिंग कांस्टेंट। ओके, सो अगर, और ये भी है, एक और इंफॉर्मेशन हमें मिल जाता है यहाँ पे, अगर ये प्रोटॉन रेजोनेट कर रहा है और ये कपल कर रहा है, तो इसका सिग्नल अगर मान के चलते हैं जे वैल्यू 1.5 से स्प्लिट हुआ है, जे वैल्यू 1.5 से स्प्लिट हुआ, जब ये रेजोनेट होगा और ये कपल करेगा तो इसका भी स्प्लिटिंग उतना ही होगा जितना कि इसका हुआ था। मतलब इसका भी स्प्लिटिंग जो है वो 1.5 जे से ही रहेगा। सो दोनों एक दूसरे को कपल कर रहे हैं तो जे वैल्यू सेम रहेगा। Am I clear? So these are the different situations. डबलेट कैसे फॉर्म होता है, ट्रिपलेट कैसे फॉर्म होता है, क्वार्टेट कैसे फॉर्म होता है, ठीक है। कभी कभी the neighboring protons, they are different. I mean, their environment is different. So एक जो प्रोटॉन है वो दो अलग अलग हाइड्रोजन के साथ अगर कपल होता है तो सिचुएशन बिकम्स मोर कॉम्प्लिकेटेड. से फॉर एग्जांपल दिस H इज इन रेजोनेंस. अगर ये किसी के साथ कपल नहीं हो रहा है तो सिंगलेट मिलेगा. ये अगर इसके साथ HA के साथ कपल हो रहा है तो इसका डबलेट मिल जाएगा. बट अगर ऐसा प्रोटॉन है जो दो नेबर के साथ है और ये दो नेबर्स इक्विवेलेंट नहीं है, मैग्नेटिकली डिफरेंट है, तो मैग्नेटिकली डिफरेंट वुड couple with this proton with the different J values, and due to that you will have 4 different splitted signal, and that is called as doublet of doublet. पहले एक सिग्नल है जो ये डबलेट में कन्वर्ट करेगा और वो दो जो डबलेट हो चुका है उसको फिर HA फिर स्प्लिट करेगा तो टोटल 4 बन जाएंगे. उसे हम डबलेट ऑफ डबलेट कहेंगे. ये क्वार्टेट नहीं होता है, ये होता है डबलेट ऑफ डबलेट. ओके, डबलेट ऑफ डबलेट कहते हैं. ये समझ में आया? am I audible?
Yes, sir.
Do you need more explanation on this? It's fine, or shall I repeat it?
Fine, sir.
Okay, thank you. So simple है. ये जो है ना, ये रेजोनेटिंग में है, ये दोनों रेस्टिंग है. अगर मान के चलते हैं H के साथ 2 से कपल कर रहा है और 2 वैल्यू से, 2 J वैल्यू से कपल कर रहा है, और B जो है व्हाट इज दैट J वैल्यू? इट्स हर्ट्ज. शिफ्टिंग ऑफ सिग्नल, ये भी शिफ्टिंग ऑफ सिग्नल है. तो शिफ्टिंग ऑफ सिग्नल इज इन हर्ट्ज में होता है वो. ठीक है, तो मान के चलते 2 हर्ट्ज से HA कर रहा है और 1 हर्ट्ज से HB कर रहा है, एक ही हर्ट्ज से कर रहा है. अगर HA एंड HB सेम है तो दोनों के दोनों सेम वैल्यू से कपल करेंगे. पर यहाँ पे HB भी अलग है, HA भी अलग है, और दोनों के दोनों इसके नेबर है, तो दोनों भी इसको स्प्लिट करेंगे. अगर दोनों स्प्लिट कर रहे हैं तो मान के चलते पहले HA ने स्प्लिट कर दिया तो एक वैल्यू उसने 2 वैल्यू से स्प्लिट करा, फिर HB करेगा एक वैल्यू से, तो हर सिग्नल फिर से 2 में डिवाइड होगा और वो एक वैल्यू छोटे वैल्यू से हो जाएगा. तो हो जाएगा, ये हो जाएगा डबलेट ऑफ डबलेट. अगर थर्ड भी आ जाता है, इसमें थर्ड भी आ जाता है जो इसको कपल कर रहा है और कपलिंग कांस्टेंट कम है उसका, तो और इसमें स्प्लिटिंग हो सकता है हर सिग्नल का. तो 4 के कितने हुए अभी? 8. सो इट बिकम्स डबलेट ऑफ डबलेट ऑफ डबलेट. This situation can be there at higher resolution and magnetically different protons, chemically similar protons. This situation can be there. Okay. This is doublet, triplet, quartet. If similar protons they couple, they will have same J values like this. The distance between these two lines and these 2 lines will be same. Okay, this is about peak intensities. अगर 2 प्रोटॉन्स है तो पीक इंटेंसिटी 3 प्रोटॉन से कम होगी. वही हमने जो बताया लास्ट टाइम. Okay, this is the scenario. Why ये क्यों होता है ये वाला? ये छोटा है, फिर ये बड़ा आया, फिर बड़ा आया, छोटा है. यहाँ पे एक है, ये दूसरा है, ये तीसरा है. ऐसे क्यों है? अगर ये जानना चाहते हैं हम लोग तो हमें देखना पड़ेगा कि प्रोबेबिलिटी क्या होती है. ओके. रेस्टिंग प्रोटॉन कितने हैं? 3. अगर CH2 CH3 ये है, CH2 के बाजू में क्या है? CH3. अगर CH2 का सिग्नल हम लेते हैं तो उसका बनेगा क्वार्टेट। क्या बनेगा? क्वार्टेट। क्यों बनेगा क्वार्टेट? क्योंकि यहां पे देखिए सिग्नल से हमारे पास जो सिग्नल था, एक यहां पे सेंटर में सिग्नल था, अभी 3 प्रोटॉन्स है जो रेस्टिंग है। या तो ये 3 प्रोटॉन्स ऑल अलाइंड है या ऑल अपोज्ड है। अगर ऑल अलाइंड सिचुएशन है तो यहां पे सिग्नल आएगा, ऑल अपोज्ड है तो यहां पे सिग्नल आएगा। अभी इसमें से 2 अलाइंड है, एक अपोज्ड है, ये वाला सिचुएशन। मतलब 1 2 3 में थर्ड अपोज्ड है, सेकंड अपोज्ड है, फर्स्ट अपोज्ड है, तो प्रोबेबिलिटी बन जाती है कि 3 सिचुएशन ऐसी है जिसमें एक अपोज्ड 2 अलाइंड है, और 3 सिचुएशन ऐसी बन जाती है कि जिसमें 2 अपोज्ड है, एक अलाइंड है। तो जितनी प्रोबेबिलिटी ज्यादा उतना उसका हाइट ज्यादा। सो दिस रेशियो ऑफ पीक हाइट्स बिकम्स 1:2, 3:2, 3:1 इन क्वार्टेट। क्वार्टेट में रहता है 1:2, 3:2, 3:1 डिपेंडिंग अपॉन प्रोबेबिलिटी। दिस इज प्रोबेबिलिटी हाइट्स। ओके, सो अगर एक सिचुएशन ऐसा आता है तीनों के तीनों अलाइंड है, तो एक ही सिचुएशन ऐसा आएगा जहां पे तीनों अपोज्ड है। लेकिन 2 अपोज्ड, एक अलाइन, और 2 अलाइन एक अपोज्ड में हो जाएगा प्रोबेबिलिटी चेंज, एंड दैट्स व्हाई इट बिकम्स 1:2, 3:2, 3:1। अगर हम लोग दूसरा सिचुएशन लेते हैं जिसमें 2 ही प्रोटॉन्स है जो नेबर्स है, रेस्टिंग है, तो ये दोनों में क्या होगा? आइदर 2 अलाइन, 2 अपोज, या तो फिर एक अलाइन, एक अपोज। ऐसे 2 सिचुएशंस, और ये एक सिचुएशन, ये वाला एक सिचुएशन। सो 1:2, 2:1, ये ए, इसका हाइट 1 है तो ये डबल हाइट रहेगा, फिर सिंगल हाइट रहेगा। सो you can have this like this: 1:2, 2:1. This is if this is quartet, this is
Triplet.
triplet. So triplet में 1:2, 2:1, quartet में 1:2, 2:2, sorry 1:2, 3:2, 3:1। अगर सिचुएशन ऐसे है कि can I draw something? I will try. Yes. अगर सिचुएशन ऐसे है कि 1 2 3, सॉरी 4 लाइन है, कंसिडर करिए 4 लाइन है। ये 4 लाइंस सेम हाइट से है, तो क्या ये क्वार्टेट कहा जाएगा इसे?
No, sir.
वाई?
Doublet of doublet, sir.
हाँ, that will be called as doublet of doublet and not quartet. Quartet is because of the similar protons, and doublet of doublet is because of the different protons, splitting because of the different protons. Okay, Pascal triangle is something which will give you peak intensities of the splitting patterns, and it is very easy. No, it is mathematical mnemonic device. See this. सिंगलेट है तो एक ही सिग्नल रहेगा, उसकी हाइट एक ही रहेगी। अगर डबलेट है तो इक्वल रहेंगे, ये इक्वल सिचुएशन रहेगा। कुछ तो हो रहा है इसमें, ये ऑटोमेटिकली कुछ हो रहा है, मुझे नहीं पता। ये डबलेट है। अगर ट्रिपलेट है तो 1:2, 2:1। क्वार्टेट है तो 1:2, 2। इसको ड्रॉ कैसे करते हैं पता है आपको? ये ध्यान में नहीं रखना पड़ता, ये अपने आप हम लोग इसको कर सकते हैं। लिखने के लिए यहाँ पे एक लिख दिया, फिर यहाँ पे एक, यहाँ पे एक लिख दिया। अब लाइंस ड्रॉ करो आप, यहां से यहां जाते समय एक यहां आ जाएगा ये, और यहां से यहां आते समय ये दोनों ऐड होके आएंगे 2, और यहाँ पे ये एक आ जाएगा। फिर यहां से मैं ड्रॉ करता हूं ये, और ये आएगा ऐसे, ये आएगा ऐसे, ये आएगा ऐसे, ये आएगा ऐसे। एक जैसा था वैसे लिखा, ये एक जैसा था वैसा लिखा। ये एक और ये 2 मिलके बनेंगे 3, ये 2 एक मिलके बनेगा 3, और ये एक। सो क्वार्टेट बनेगा 1:2, 3:2, 3:1। ये निमोनिक है, ये कोई प्रूवन ये नहीं है, ये ध्यान में रखने के लिए है। फिर आएगा ये कि एक जैसे के वैसा आपने लिख दिया। फिर यहां से मैं जब यहां आता हूं तो 3 और 1 4, 3 और 3 6, राइट, और 3 और एक 4 और ये 1। सो क्विंटेट में 1s2 4s2 6s2 4s1 ये पीक हाइट बन जाएगा क्विंटेट में। 1s2 4s2 6s2 4s1, सो एक क्विंटेट बनता है। सेक्सटेट में 1s2 5s2 10s2 वैसे ही करना है, एक 4 और एक 5 5 4 और 6 10 4 और 6 10 6 और 4 10 4 और एक 5 और ये एक जैसे के तैसा। सो 1s2 5s2 ये समझ में आया आपको निमोनिक? तो आप सेप्टेट तक क्या कहीं तक भी जा सकते हो और आपको पीक इंटेंसिटीज आपको मिल जाएंगी। ठीक है, these are the different situations. I'll just skip some slides. Okay, so J values have important meaning while interpreting NMR spectrum. How much time do I have?
15
Hello?
minutes. 15 minutes more.
15 minutes more. Oh, thank you, sir. So I have some more slides. I have to hurry up. Yes, these are the different situations wherein J values are shown over here. देखिए, ये एक दूसरे के नेबर्स नहीं है और एक दूसरे को कपल नहीं करते हैं, इसलिए क्या आएगा? जे वैल्यू 0, इसमें कोई स्प्लिटिंग नहीं हुआ है। ओके, अगर CH2CH3 ये सिचुएशन है तो इसमें कितना आएगा जे वैल्यू? 6 to 8 हर्ट्ज ये वैल्यू आएगा, 6 to 8 हर्ट्ज। ये सिचुएशन में 5 to 7। अगर ये सिचुएशन है, x and y are different and dihedral angle is there, so 2 to 12. Okay, depending upon the dihedral angle of H to H, it would be 2 to 12 J in hertz. aldehydic प्रोटॉन के साथ कम होता है क्योंकि वो पैरेलल नहीं होता है इसके साथ, इसलिए 0.5 to 3। जो प्रोटॉन्स एक दूसरे को पैरेलल होते हैं या जेमिनल होते हैं उसमें J वैल्यू ज्यादा होता है। फॉर एग्जाम्पल हियर, इफ दीज टू प्रोटॉन्स आर मैग्नेटिकली डिफरेंट, एक ही कार्बन के ऊपर है लेकिन वो मैग्नेटिकली डिफरेंट है बिकॉज ऑफ सम स्टेरिक कॉम्प्लेक्सिटीज, और यहाँ पे कोई अलग से ग्रुप है जो इस प्रोटॉन को अलग इन्वायरमेंट दे रहा है, और यहाँ पे और ये स्ट्रक्चर रिजिड है। ये स्ट्रक्चर क्या है? रिजिड है। ड्यू टू रिजिडिटी ये प्रोटॉन अलग बिहेव कर रहा है, ये प्रोटॉन मैग्नेटिकली अलग बिहेव कर रहा है, इनका सिग्नल अलग अलग है, तो एक दूसरे को कपल होंगे। अगर कपल होंगे तो जेमिनल कपलिंग होता है 1215 तक, 12 to 15। must be distereotopic. You might have studied distereotopic property of hydrogens in stereochemistry. तो अगर एक को किसी अलग ग्रुप से रिप्लेस करते हैं तो एक मॉलिक्यूल बनेगा, दूसरे को अगर रिप्लेस करते हैं तो दूसरा बनेगा, और दोनों एक दूसरे के डाइस्टीरियोमर होंगे, इसलिए उन्हें डाइस्टेरियोटोपिक हाइड्रोजन्स कहा जाता है। And in such a situation, they couple each other, they have different signals, they couple each other, and the J value would be 12 to 15. Okay, ये है एंटी पेरीप्लेनर, एक दूसरे को एंटी पेरीप्लेनर है, पैरेलल है एक दूसरे को। पैरेलल होने की वजह से इनके स्पिन पैरेलल है तो इनका कपलिंग बहुत ज्यादा होता है, और ये हाईएस्ट कपलिंग होता है 12 to 18। Okay, J value will be 12 to 18 because they are parallel to each other. These are syn periplanar but not parallel, so J value will be little lower, 7 to 12. Geminal coupling जैसे यहाँ पे था जेमिनल, यहाँ पे भी जेमिनल है, बट ये यहाँ पे क्या हो जाता है, बॉन्ड एंगल चेंज होने की वजह से इनका इंटरैक्शन थोड़ा कम हो जाता है, सो इट बिकम 0.5 to 3। जे वैल्यू कम हो जाता है इनका एक दूसरे को कपल करते समय। इसका 3 to 11, एंड अगेन डिपेंड्स अपॉन डायहेड्रल एंगल। इसका इसके साथ डायहेड्रल एंगल क्या है, अगर वो फिक्स्ड है, अगर ये सर्कुलेटिंग है तो अलग होगा, so it depends, so it ranges from 3 to 11। Okay, fine. Next structure is this Long range coupling will be lower J value, 2 to 3. This is W coupling. If you have W coupling, for para it is 0 to 1. Para बहुत दूर का कपलिंग है, ये नहीं होता है कपल, कभी कभी हो भी जाए तो बहुत स्मॉल J वैल्यू रहेगा. मेटा कपलिंग दैट इज W कपलिंग, यहाँ पे आएगा W, W बड़ा सा W आपने सुना होगा, राइट. तो ये अगर प्रोटॉन यहाँ पे है और ये मैग्नेटिकली डिफरेंट है, तो ये दूसरे एक दूसरे को कपल करेंगे एंड द कपलिंग कांस्टेंट वुड बी 1 to 3, दैट इज W कपलिंग. एंड ऑर्थो कपलिंग, यहाँ पे जो प्रोटॉन है ये इसके साथ अगर कपल करता है तो दैट इज 6 to 9. जैसे जैसे यहाँ पे डिस्टेंस कम हो जा रहा है, 1 2 3 बॉन्ड कपलिंग, 1 2 3 4 बॉन्ड कपलिंग, 1 2 3 4 5 बॉन्ड कपलिंग, तो ये J वैल्यू कम होते जाता है बिकॉज ऑफ द इंक्रीज इन द डिस्टेंस बिटवीन द हाइड्रोजन्स व्हिच आर कपलिंग टुगेदर. Am I clear with this?
In case of that, you said long range coupling, that one, second last right side. Can these hydrogens couple because they're not present on the adjacent carbon? No?
Sometimes it observed that this coupling happens, but many times, many molecules, this coupling is not strong, so you do not get coupling in this case. But in some situations, it is found that this proton and this proton they get coupled, and J value would be around 2 to 3. कभी कभी कपल होते हैं, ये कभी कपल नहीं होते हैं. मेनी सिचुएशंस द कपलिंग डज नॉट ऑकर, बट कुछ एग्जांपल्स ऐसे हैं जिसमें कपलिंग पाया गया है.
Okay, sir.
Okay. What is coupling constant? This is, all theoretical part. This is the distance between two peaks in simple multiplet, right? Called as J. And expressed in hertz, it is expressed in hertz. Constant nature of coupling constant can be observed in all instrument with different frequencies. अलग अलग फ्रीक्वेंसी है, लेकिन कपलिंग कांस्टेंट हर्ट्ज में होने की वजह से वो उतना ही है. एंड इसीलिए अगर आपके पास से फॉर एग्जांपल 800 मेगाहर्ट्ज का इंस्ट्रूमेंट है, तो उसमें जो सिग्नल्स है वो क्लियर दिखेंगे आपको, और 100 मेगाहर्ट्ज 60 मेगाहर्ट्ज में है और सिग्नल्स आर क्लोजर टू ईच अदर, तो फिर कपलिंग घुस जाएगी एक दूसरे के अंदर, तो आपको कंफ्यूजन हो जाएगा कि ये क्या मल्टीप्लेट है, क्वार्टेट है, ट्रिपलेट है, पता नहीं चल रहा है. दैट सिग्नल्स वुड बी सेपरेटेड इन हायर फ्रीक्वेंसी इंस्ट्रूमेंट्स. देखिए यहाँ पे एग्जांपल दिया गया है, सेम इन 60 मेगाहर्ट्ज, सेम मॉलिक्यूल इन 100 मेगाहर्ट्ज, डेल वैल्यू सेम रहेगा, बट J वैल्यू भी सेम रहेगा. अगर J वैल्यू सेम रहता है और सिग्नल्स अगर करीब है तो ये एक दूसरे के पास आते हैं. अगर सिग्नल्स दूर है, अगर हायर मेगाहर्ट्ज में आप ऑपरेटिंग फ्रीक्वेंसी में कर रहे हो, तो ये जो है ये कॉम्प्रेस हो जाएगा और आपको क्लियर सिग्नल्स दिखाई देते हैं. 60 मेगाहर्ट्ज में देखिए, ये है 60 मेगाहर्ट्ज वाला सिचुएशन, ये है बी वाला 300 मेगाहर्ट्ज, सेम मॉलिक्यूल. Okay. Coupling constant of the groups of the protons that split one another must be identical, और वो identical होता है. A प्रोटॉन ने B को स्प्लिट किया और B ने A को स्प्लिट किया, तो दोनों का J वैल्यू सेम है. और ऐसे सिचुएशन जहां पे बहुत सारे कपल्ड है एक दूसरे को, तो उसमें ये जो ऊपर दिया गया स्टेटमेंट है वो very useful in interpreting the spectrum that may have several multiplets. ईच विथ डिफरेंट कपलिंग कांस्टेंट। तो डिफरेंट कपलिंग कांस्टेंट है तो समझ में आएगा कौन किसे कपल कर रहा है। So can you find out which triplet is associated with the quartet? यहाँ पे ये क्वार्टेट है, बी ट्रिपलेट है, सी ट्रिपलेट है और डी ट्रिपलेट है। तो ये 3 ट्रिपलेट्स है, इसमें से एक ट्रिपलेट जो है मतलब CH3 वाला सिचुएशन कंसीडर करते हैं, ये एक CH3 किसी CH2 के साथ लिंक्ड है। तो कौन सा सिग्नल किसके साथ एसोसिएट है बता सकते हैं आप?
एसोसिएटेड है क्योंकि
Only
A and C.
associated
सेम
with
कपलिंग
ये
B
हाँ
is
ए के साथ
associated with D.
एन सी
एंड बी डी के साथ एसोसिएट है। तो ये जो
Yes,
बी
sir.
और डी है ये क्या सीन रहेगा? बी और डी रहेगा CH2
जी।
बराबर, और ए और सी रहेगा CH3 कुछ गलत तो नहीं बोल दिया मैंने? ए और सी जो सिचुएशन है इसमें स्प्लिटिंग पैटर्न देख के हम बता सकते हैं कि CH2 CH3 वाला सिचुएशन है और बी और डी एक दूसरे को कपल कर रहा है, इसका मतलब वो CH2 सेपरेट सेगमेंट है। Am I right?
राइट
Yes.
Yes. Yes.
So the coupling between the CH2 will be less, coupling constant. 5 hertz.
Yes. It depends upon the environment of those protons, right?
Yes.
Okay. Some useful coupling constant. सिंपल सिचुएशन, 2 कार्बन एक दूसरे को ज्वाइंट है और 2 प्रोटॉन्स है, तो 6 to 8 नॉर्मल जो जे वैल्यू है वो रहेगा 6 to 8। ये एंटी पेरिप्लेनर जब होते हैं इसको हम क्या कहते हैं? ट्रांस प्रोटॉन्स, एक दूसरे को ट्रांस है तो हायर जे वैल्यू रहता है 11 to 18। सिस प्रोटॉन्स का 6 to 15 ये जे वैल्यू कम है, ये ज्यादा है। क्यों? क्योंकि ये दोनों के स्पिन पैरेलल है एक दूसरे को, इसलिए अच्छे से ये कपल कर पाते हैं। ये स्पिन्स पैरेलल नहीं है लेकिन क्लोज है, इसलिए ये कपल तो अच्छे से करेंगे पर इतना नहीं, तो वैल्यू 6 to 15 आ जाता है। ठीक है, इस सिचुएशन में 4 to 10 और कम हो गया। ठीक है, and if ortho coupling is there, 6 to 10 again, ortho coupling 6 to 10, 8 to 11 if it is not a benzene, cyclic ring, double bond, but not a benzene, so it is 8 to 11 J value। यहाँ पे डिफरेंट सिचुएशंस है। J जो है 8 to 14, AE, EE मतलब एक्सियल 8 to 14, ये साइक्लोहेक्सेन है। अगर चेयर कंफर्मेशन कंसीडर करते हैं हम लोग इसका, तो एक्सियल 2 प्रोटॉन्स एक्सियल है तो 8 to 14, एक्सियल इक्वेटोरियल है तो कभी कपल भी नहीं करेगा तो कभी 7 तक 0 to 7 हो सकता है, और इक्वेटोरियल है तो 0 to 5, तो सबसे कम इक्वेटोरियल में होता है। इक्वेटोरियल दे आर नॉट पैरेलल टू ईच अदर, बट एक्सियल दे आर एंटी पेरिप्लेनर जैसा सिचुएशन होता है, दे आर पैरेलल स्पिन्स टू ईच अदर, सो सबसे ज्यादा एक्सियल एक दूसरे को कपल करते हैं और दैट इज 8 to 14। ओके, cis coupling is 6 to 12, trans coupling is 4 to 8 in strained rings. In strained rings, situation little bit different than the aliphatic trans and cis hydrogens. And these are again different situations having cis and trans and different J values. What is multiplex skewing? Skewing means thoda झुक जाना, है ना। तो अगर स्पेक्ट्रम में आप ऑब्जर्व कर रहे हो और ये स्पेक्ट्रम इस तरीके से बन रहा है, तो देखिए अगर ये पीक इसके साथ कपल है तो ये स्कीविंग हमें ऑब्जर्व होती है नॉर्मली। जो स्पेक्ट्रम हम देखते हैं ना, उसमें ये स्कीविंग देखने से मतलब ये जो छोटा है ये थोड़ा सा बड़ा है, 1:2, ये सिचुएशन में एक जो है थोड़ा सा छोटा है और ये बड़ा वाला है। तो जो बड़ा है उसके साइड में ही उसका जो दूसरा सिग्नल है उसको कपल कर रहा है। ये पता नहीं कैसे आ जाता है स्पेक्ट्रम में, पर ये ऐसे ऑब्जर्वेशन है कि ऐसा होता है। डबलेट है तो दोनों का हाइट सेम चाहिए, लेकिन जो सिग्नल अगर लेफ्ट में है तो लेफ्ट वाला थोड़ा सा हाइटेड होता है। ये सिग्नल, ये स्प्लिटेड सिग्नल थोड़ा सा हाइटेड होता है राइट हैंड साइड से। दैट इज कॉल्ड एज मल्टीप्लेट स्कीविंग। ओके, इसका थ्योरी पता नहीं कैसे आ जाता है, मुझे भी नहीं पता कि ये ऐसे सिचुएशन क्यों हो जाता है, एक दूसरे को कपल करते हैं और स्पेक्ट्रम में स्कीविंग हो जाती है। ठीक है। या तो मे बी मेरा स्टडी कम है जिसकी वजह से मुझे अभी तक इसका रीजन पता नहीं व्हाई स्केलिंग हैपेंस, बट इट इज ऑब्जर्व्ड। Okay, proton on carbon carbon double bonds often give characteristic splitting patterns, which is gemin hydrogens, then cis hydrogens, trans hydrogens. तो हम अगर कोई आइसोमर आपके पास है और आपने एनएमआर उसका लिया है, तो उससे आपको स्पेसिफिक स्ट्रक्चर अगर पता करना है तो ये जे वैल्यूज बहुत ही इसेंशियल पार्ट बन जाते हैं आपके एनएमआर का। उसके हिसाब से आप आपको पता चलता है वेदर द हाइड्रोजन्स आर जेमिनल, वेदर द हाइड्रोजन्स आर सिस इन द कंपाउंड, और वेदर द हाइड्रोजन्स आर ट्रांस टू ईच अदर एंड द ट्रांस कंपाउंड एग्जिस्ट। ये सारे अगर आइसोमर्स है एक दूसरे के और सेम मॉलिक्यूलर फार्मूला है, आपने एनएमआर ले लिया, आपको झट से पता चल गया जे वैल्यू अगर 5 to 10 के बीच में है तो यू विल से द कंपाउंड इज सिस। अगर वो 11 to 18 है तो आप कहोगे कि वो कंपाउंड ट्रांस है। सो दिस इज द यूटिलिटी ऑफ एनएमआर जे वैल्यूज टू आइडेंटिफाई आइसो। अगेन स्प्लिटिंग पैटर्न पे और भी स्टेप्स है मेरे पास। यहाँ पे जो है E3 chloropropionic acid, the HA and HB are trans to each other, and coupling constant you can see 14 hertz, right? Hello, hello. Are you saturated or super saturated?
No, sir, it is okay.
It's fine.
Okay, fine. Okay, fine. I'll just wind up in 1 or 2 minutes. Okay, fine. Yes, how many slides? Oh, ho, ho. Okay, fine, no issues. We'll go little faster. ये सिचुएशंस यहाँ पे दिखाई गई है कि अलग अलग अगर स्प्लिटिंग है तो कैसे, हमने देखा है, ये पहले भी देखा है कि कैसे सिंगलेट को ट्रिपलेट कन्वर्ट हुआ, फिर ट्रिपलेट, एवरी ट्रिपलेट इज कन्वर्टेड टू अगेन ट्रिपलेट, सो ट्रिपलेट ऑफ ट्रिपलेट इज हैपनिंग ओवर हियर एंड कॉम्प्लेक्स स्प्लिटिंग पैटर्न यहाँ पे दिख जाता है आपको। JAB and JBC, if they are not equal, then it happens. Okay, similar situation. ये कुछ सिचुएशन है जिसमें ये क्वार्टेट है, मिथाइलिन क्वार्टेट और मिथिल ट्रिपलेट CH3 CH2 जो है। हमेशा अगर आपको ट्रिपलेट और क्वार्टेट मिल जाता है, ट्रिपलेट और क्वार्टेट, तो ये CH3 है, ये CH2 है। ऐसा एक सिंपल लॉजिक होता है कि ट्रिपलेट क्वार्टेट होने की वजह से हम कहते हैं कि वहां पे एक सेगमेंट है या एक फ्रैगमेंट है जिसमें CH3 CH2 है। ओके, सिंगलेट, चारों के चारों प्रोटॉन सिंगलेट एंड 3.73 बिकॉज दे आर सिमेट्रिक। ओके, कंपाउंड इज सिमेट्रिक। नाउ इफ क्लोरीन दूसरे कार्बन पे है तो ऑलटुगेदर स्पेक्ट्रम चेंज हो जाएगा. These are the different examples of situations of different protons. कीटो इनॉल प्रोटोमेरिज्म. अगर इनॉल फॉर्म, मैंने बोला था आपको, अगर इनॉल फॉर्म स्टेबल है कीटो से अगर इनॉल फॉर्म स्टेबल है तो उसमें आपको एक सिग्नल मिल जाता है आउट ऑफ रेंज 12 से भी ऊपर 15 तक. ओके, सो दिस इज द मॉलिक्यूल. इसका अगर आपने एनएमआर लिया तो इसमें एक सिचुएशन होता है डेल 14.5 पे एक सिग्नल मिल जाता है आपको. ठीक है ना. तो ये सिग्नल है इनॉलिक ओएच का. या तो ये स्टेबल रहेगा या तो ऐसी सिचुएशन है जिसमें स्टक हो जाता है. या तो स्टेबिलिटी से बनता है इनॉल, या फिर नहीं तो कीटो फॉर्म ज्यादा स्टेबल है उसकी तरफ वो चला जाता है. कुछ एग्जांपल्स ऐसे जिसमें इनॉल जो है स्टेबल पाया जाता है तो उसमें ये सिग्नल मिल जाता है आपको. ओके, सो these are the different molecules with the different spectral. See, spin splitting, non equivalent coupling, यहाँ पे जो है रियल एग्जाम्पल है, ये रियल सिचुएशन है. तो इसको अगर आप एक्सपांड करते हैं तो दैट इज डबलेट. अगेन ईच ईच splitted signal gets split into two. So doublet of doublet ऐसे दिखता है एक्चुअली. ये भी HB का डबलेट ऑफ डबलेट है देखो. और ये भी डबलेट ऑफ डबलेट है. HB का भी क्या है, डबलेट. HB का भी डबलेट ऑफ डबलेट है. HB का भी डबलेट ऑफ डबलेट है. HC का भी डबलेट ऑफ डबलेट है. और HA किसी के साथ कपल नहीं कर रहा है इसलिए इसका HA का सिंगलेट है. So this in this way we read spectrum, we prepare different molecules, we take NMR and we try to match our NMR with our structure which is expected one. ठीक है जी. This is another situation. There are so many spectrum I have loaded in this presentation, but due to little saturation, बिकॉज पहला भी एक आपने सेशन, बड़ा वाला सेशन आपने अटेंड किया है इस सेशन के पहले, और सभी लोगों को अभी भूख लग चुकी होगी इतना सारा सुन के. तो आई अंडरस्टैंड द सिचुएशन और मैं यहाँ पे स्टॉप करता हूँ. ओके, shall we stop here? एनएमआर में जो पीक हाइट के यहाँ से हम लोग नंबर ऑफ कार्बन, सॉरी नंबर ऑफ हाइड्रोजन कैलकुलेट करते हैं ना, वो बड़ा मजेदार एक्सपीरियंस है. उसमें क्या होता है कि पीक हाइट को सारे के सारे ऐड करके एक नंबर मिल जाएगा आपको, और मॉलिक्यूलर फार्मूला में जितने हाइड्रोजन है उससे आप उसको डिवाइड कर दो तो एक हाइड्रोजन के लिए कितना पीक हाइट रहेगा वो पता चलता है. और हर सिग्नल में अलग अलग आपके पास पीक हाइट दिया होता है. तो हर पीक हाइट को उस नंबर से डिवाइड कर दो तो नंबर ऑफ हाइड्रोजन पता चल जाते हैं. तो सिग्नल से आपको वो भी पता चलेगा, और इंटरप्रिटेशन ऑफ 1H इज बिकम्स मोर इजी, और उससे स्ट्रक्चर ड्रॉ करना इजी हो जाता है. ओके, सो मुझे लगता है 5-10 मिनट से पहले ही मैंने सारा क्लोज कर दिया है. Any questions? The topic is open for discussion.
Sir, thank you for your presentation over 2 days. Very nice presentation from basics to NMR. So it will be great if you can share the slides with us.
Yes, sir. Thank you, sir. So organizers are not there or what?
Yes, Prashant sir.
Okay. Hello,
Is there
ma'am.
any questions, participants? I think there was lots of interaction.
Yes. The audience is really amazing. They are continuously, concentrating on both the sessions and they
Good.
are active. It was a nice experience.
Every time it is used to have that the participant will give the feedback, but now this is, I think, first time that the resource person is giving good feedback about the participants.
Yes,
So
yes.
I must
All-
congratulate all of you, all the participants.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Ma'am.
Thank you, ma'am.
Thank you,
So,
ma'am.
okay.
Thank you, ma'am.
Welcome. The permission of the resource person.
Hare
I conclude. Yes, Dr. Prashant.
Yes, yes, ma'am. Please go ahead.
Okay.
नहीं पड़ी ना ये
So whose turn it is to
कपड़ों में
propose
छोड़
vote of
दिया यार
thanks?
कल ही मैंने लाकर तुम्हारा इतने खेलने लग गई थी ये
Okay, sir. Deshmukh sir, Dr. Deshmukh sir.
Yes, ma'am.
Please, sir.
Good
कपड़े
afternoon to
कपड़े
all.
निकाले
I am Dr. Ramchandran Anand Deshmukh from
लो
Bharati Vidyapeeth Matosri Bayabai Sripatrao Kadam Mahavidyalaya Kadegaon Sangli. It's my honor and privilege to propose the vote of thanks on behalf of Malviya Mission Teachers Training Center and Sant Gadge Baba University Amravati Department of Chemistry, all organizing committee of refresher course and all participants. I would like to express our deepest gratitude and appreciation to our esteemed resource person, Dr. Prashant Ghorpade sir. Sir, we are truly grateful for your insightful and enriching live session on the basics of NMR spectroscopy. Sir, in his speech on basics of NMR spectroscopy, explained in a very much simple manner chemical shifts, shielding and de-shielding, interpretation of the data, hybridization effects, hydrogen bonding, magnetic anisotropy, 1H NMRs, 13C NMR spectrum, spin splitting with examples, also coupling constant. Sir, for researchers, particularly in organic synthesis, knowledge of NMR is very essential and Sir has explained all aspects of NMR spectroscopy. Thank you very much, sir, for sharing your knowledge with us, and it will be very helpful to us in our future research. Thank you very much, sir. I am
Thank
very
you,
much
sir.
thankful to respected Dr. Manisha Korpe madam, and I express my thanks also to respected Dr. Ankit Thakur sir. Lastly, I am thankful to all participants for making this session live and interactive by asking your queries and doubts. Thank you, all of you. Have a nice day. Over to you, ma'am. Thank you.
Shall I leave, ma'am?
Yes, Prashant sir.
Okay, thank you, ma'am. Thank you for
Okay.
the
Now the
opportunity.
next session will be start on 2:30 p.m. And I hope you got the message from the resource person, the last lecture, where those who are having laptops or PCs, they can install some softwares.
Yes, ma'am.
The link has been already shared in the WhatsApp group.
Yes, ma'am.
Okay. See you then. हाँ पिंगळे सर. Hello.
Hello. Hi. Yes,
Yes,
ma'am.
sir. Namaskar, sir.
Namaskar. Namaskar.
How are you, sir?
Yeah, fine. I'm fine.
Sir, shall we start the session, sir?
Yes, yes, please.
Okay. So I think it's very happy to see you, sir. I mean,
Yeah, thank you. Thank you, madam.
um, I think it's a turn. Dr. Dar, sir, is going to
Yes,
introduce.
yes, ma'am. I'm here. I'm here.
Oh, okay, sir. Okay.
Thank you. Thank you very much.
Please, sir.
Good afternoon, one and all. Myself, Dr. Riaz Ahmed Dar. I'm working as an assistant professor in the Department of Chemistry, Maharashtra College, University of Mumbai. I take this opportunity and it gives me an immense pleasure to introduce today's distinguished speaker and their source person, Professor Subhash S. Pingale sir. I sincerely thank the organizing committee for giving me this opportunity. Professor Subhash S. Pingale sir is a professor in the Department of Chemistry at Savitribai Phule Pune University, Pune, where he also serves as the sectional head of the medicinal chemistry. Professor Subhash secured the first rank in MSc in physical chemistry from the same university in 1994 and subsequently earned his PhD degree in theoretical and computational chemistry from the University of Pune. Professor Pingali is a recipient of one of Japan's most prestigious international scholarship, Moon Bosho, which is awarded to outstanding researchers, and postdoctoral fellowship awarded by Japan Society for the Promotion of Science, Government of Japan. He carried out his postdoctoral research at Nagoya University, Japan from 1998 to 2004. He has authored more than 40 research publications in international journals of repute, including Journal of American Chemical Society, Journal of Physical Chemistry, Chemical Communications, Physical Chemistry, Chemical Abstracts, Organic Electronics, Chem Photochem, Dyes and Pigments, and Journal of Molecular Liquids. His research interests include molecular electronic structure calculations, applications of molecular electron density and electrostatic potential in understanding weak intra and intermolecular interactions, cation binding, pi electron delocalization, and the design and development of novel organic materials for optoelectronic and molecular electronic devices. So with this brief introduction, it is my privilege to extend a warm welcome to Professor Subhash S. Pingale sir on behalf of the Director UGC MMTTC Sangade Baba Amravati University, our course coordinator Professor Manisha Kopade ma'am, our technical coordinator Dr. Ankit Thakur, and all the participants of this 9th day session 3 of the refresher course in chemistry. Today, Professor Pingale delivered and will be delivering an enlightening lecture on the topic computational chemistry and overview. I'm confident that this session will be highly informative and enriching for all of us. So once again, a very warm welcome to you, sir. Sir, I request you to kindly take over the session. Thank you.
Yeah.
Over to
Thank
you,
you
sir.
very much, sir, for your welcome and my introduction. Also, I thank to the organizer for giving me this opportunity to interact with all the participants. Thank you very much. So, am I audible first?
Yes, sir. Yes, sir. You are
Yes,
very
sir.
much.
Yeah, okay,
Yes,
okay.
sir.
Thank you. Thank you.
Sir.
Yeah. And let me upload my slides. So, I hope all of you can see my screen.
Yes, yes, we can see it, sir.
Yeah, yeah. Thank you. Yeah. So hope you can see my slide.
Yes, sir.
Yes, sir. Yes.
Yeah. Okay. Thank you. Thank you very much. And so see, today, as participants are from all the subjects, so I want to give a brief introduction of computational chemistry and how it will be useful for various to understand various aspects of chemistry, how it will useful to help experimentalists. That I'm going to uh, speak in my today's and tomorrow's talk. So computational chemistry. Yeah, this is our university, Savitribai Phule Pune University main building, and we renamed this university name from University of Pune to Savitribai Phule Pune University as to show Savitribai's work, as she has started first women's school in India. So uh, because of that, so all of you are welcome to visit this university place. Okay, so let's start. So in my talk, what I'm going to speak is what is computational chemistry, then how does it work, why is it useful, what are its limits, then type of computational chemistry, and where we can apply this, and then I'll take some examples in my talk. So what is computational chemistry? So computational chemistry is the use of computers to determine the movement, design, electronic effect, and configuration of atoms and molecules. So I request all of you to switch off your audio. So now these days, computers are very fast, and also quantum chemistry knowledge, theoretical chemistry knowledge is very good, and also our programming knowledge, so we can write programs and use that for to understand chemistry. So this is just the example which I am going to take in my talk further for designing a drug, how it will help computational chemistry or understanding the chemical reactions. So how does it work? Computational chemistry is often based on understanding of quantum chemistry. So we know that how atoms are interacting and binding together with chemical bonding by understanding quantum chemistry principles, postulates of quantum mechanics, as we know those, and then we can see that how one atom is interacting with another atom in a molecule, or how molecules are interacting with other molecules, that we can understand. And we can use this for to understand various chemical reactions or chemical aspects in physical, organic, biochemistry, and inorganic, and other like medicinal, nanotechnology. We can use this one. So before 1986, see, we can see here a computational chemist and experimentalist that just a minute. Yeah. So what experimentalist is saying to computational chemist that there must be something wrong with your calculation. Because experiments are saying something and calculation theory result, computational chemistry results are coming something else. So something is wrong. But in 2016, time came. So computational chemists, they were saying that there must be something wrong with your experiments. So computational chemist can predict or say that it's the result of the reaction should be something like this, but we are not getting that. Then if we want to achieve some reaction with some product, but why we are not getting? So something is there. Actually, we should get that. So now time is there to, we have to go hand in hand with computational chemistry and experiments together. So in synergy together. So when two are better than one, so we can take chemistry ahead. So why it is useful? So every chemist wants to use computer to help limit failure in labs, because some reactions are not going, some drugs are not functioning, or maybe not giving us better result. So we want to do that. So for that, it will then assist to experimentalist, and we can also save time as well as money by doing this. I'll come to this with example further. Yeah, actually there are limitations with computational chemistry, because we have to simulate the system, real system. So there are various parameters which are responsible for the actual chemical reaction. So it is very important to put all the parameters together, incorporate all aspects. Then again, bigger systems, large systems is still at high level of accuracy. It's difficult to do with better accuracy. And we need experimental results for test the computational chemistry results. And yeah, so does not look at the whole picture. So we have to take some part of the system and then do simulation or modeling of that. Okay, on the other hand, what's it good for? So computational chemistry is rapidly growing field in chemistry. As I told you, computers are getting faster. If we consider our old generation computers, today's computers are very fast. As our we can see our mobiles are so fast. So really we have to give them work to do, and so computers are we can use these computers for our purpose. Also, algorithms and programs are also matured. As we know that Erwin Schrödinger, he gave a Schrödinger equation, H psi equal to E psi, and got Nobel Prize for solving hydrogen atom problem, giving orbitals their energies. And with potential energy surface, we can see, I will come to that point also, that how one atom is interacting with other atom, that we can model very well with the equations. So that is very important. And so we can study following properties with this, that is equilibrium and transition state structures. Because transition state structure getting transition states is very means those are not stable. So to get their what we can say properties is very difficult with experiments. But with computational chemistry, we can get the structure of transition state, and then we can see what is happening in that. Then dipole moment and quadrupole moments and polarizabilities, which are really responsible for chemical reactions, as we know, those we can calculate. Then vibrational frequencies, IR and Raman. So most of the spectroscopic aspects we can do with computational chemistry. Then NMR, ESR spectra, UV spectroscopy, then reaction rates, and also thermochemical properties. We can study with this. So let's go a little bit basic for computation, how it's computational chemistry works. So Schrodinger equation exactly solvable for one particle, one electron system, and we have seen that we can solve exactly Schrodinger equation for harmonic oscillator, particle in 1D box, hydrogen atom. So but for many electron system, really we cannot solve Schrodinger equation exactly. So that is a problem in computational chemistry, that we cannot solve because electron repulsion part still there is a problem to get exact form of that. But still we will get quite accurate, means what we can say, we can take the results and compare with our experiments and to predict or to give idea about chemical reactions. Those are enough for us. And another thing is that as our system means molecules, let's say 10 molecule system or 20 molecule system, 100 molecule system, 500 molecule system, as system increases, then its cost is also increasing, and also calculations, its accuracy. If we want more accurate, then again computational cost will be more. So it is size based on its size. So by solving Schrodinger equation, as we know in our MSc syllabus, chemical bonding course, we are getting the atomic orbitals here, like this is 1s, 2s, 2p, and the shapes which we have plotted, that S is spherical, P dumbbell shape, and various d orbital structures. So when we plot these atomic orbitals with polar plots, we will get these shapes of this. So we are having atomic orbitals, these atomic orbitals, which is we are getting from exact solution of hydrogen atom or hydrogen-like atom. Hydrogen-like atom means what? Or hydrogen-like system is what? The systems which are having one electron system, so which are exactly solvable. So we have to use Born-Oppenheimer approximation as because size, weight of electron and nuclei. So nuclei are much heavier. So that getting the problem more easier, we have to use Born-Oppenheimer approximation. What is that? We will see very soon. And we have to use also many electron wave function in terms of Slater determinant. And so we can say that as a method. So there are various methods to do this. And we have to also represent the wave function, molecular orbital, which is linear combination of atom orbital, LCAO approximation, as we know in molecular orbital theory. So we have to use these molecular orbitals. And to get these molecular orbitals, we have to use basis set or basis functions, which are functions which we can use for doing or solving the equations. So the Bonhoeffer approximation. So for time independent shorting equation, this is very well known equation. H psi equal to E psi, where H is Hamiltonian, psi is wave function or state function, E is energy, and psi is wave function. So H is energy operator, Hamiltonian operator, and it's made up of this kinetic energy part and potential energy part, T plus V. So kinetic energy and potential energy. So for many electron system or many electron atoms or molecules, the Hamiltonian operator is like this. In that, we have to consider kinetic energy nuclei or kinetic energy of nuclei, this part, then kinetic energy of electron, and nuclear repulsion energy, then nuclear electron attraction and electron repulsion part. So this is complete Hamiltonian. We have to operate and then we will get the energy. This is the when we simply see the Schrodinger equation. And del square operator is del dot del, so which is this part, and kinetic energy part, as we have seen in particle in 1D box, that is minus h cross square upon 2m, where m is mass of the particle, d square by dx square for one dimension. So as I told that protons are much heavier than electrons, so their motion is much different. So we have to use Bonhoeffer number approximation, that we have to keep nuclei are not in comparison of electronic motion, nuclei are not if we take this approximation that nuclei are not moving at all, so our problem will be much simpler, as nuclei are moving very what we can say slower, very much slower than electron. So we can write this, we can separate electron and nuclear motion. That means we can separate two wave functions. So we can take product of them, psi electronic and psi n nuclear is a total. Then by using that, we can write this equation as H electronic is psi electronic, H electronic Hamiltonian is this one, in which there is no kinetic energy of, in this equation, no kinetic energy of nuclei, because nuclei are now fixed, and also, yeah, yes, that factor is not there, and nuclear interaction potential energy, that part we have separated from this also. So that is this one, nuclear repulsion, and then which is a constant because nuclei are not moving now, so that factor is constant. So here we can write H electronic Hamiltonian as this, and then solve the equation. So we will get energy E electronic, and the remaining part, which is constant. When we add a constant in a eigenvalue equation, the in a operator of eigenvalue equation, then the value of that eigenvalue will increase by that additional value. So that's what we have done here, and then we can write electronic and VNN as a energy of that system. So here is the potential energy surface. What is this? This is calculating the energy at fixed nuclei. That means we are increasing the nuclear distance, and as the energy, total energy, maybe we can say, is we can see how it is changing. So at when nuclei are very closer, we can see very highly repulsion between them, and as we go on further, So it will go to its minimum value, and then again it will go up. As there will be repulsion will go on decreasing and attraction will go on increasing. Which attraction? Electron nuclei attraction of the atoms will increase. And after that, as we take them away, then what will happen? This attraction also will get reduced. And finally, it will go to relative energy as a zero. So, this is important to get this minimum value, and which we can do mathematically, as we know that we can use derivative very nicely to get a minimum. And there are many minima on potential energy surface. So for many atomic systems in a molecule, many minima will be there. Minima are there, so we will get that information. And with this, what we are getting is bond distance of this, where the system is more negative. See, negative means what? As kinetic energy and nuclear electron attraction energy, these are stabilizing the system, and electron repulsion part, this part is destabilizing. So negative means more stable. So it is stabilizing. Negative means, so here is a stabilization. Okay, so how two atoms are talking with each other, we can see through this potential energy surface, as where they will be stable at what distance, what angle, what diagonal angle. So we will get structure of the molecule by doing this process. When we can use this, let's say I want to do calculation, computational chemistry calculation for the system, then I can give initial guess with some distance, and then from that, let's say I have given a 7 angstrom distance. This is a GBR system taken as an example. And from here, if this is the place at 7 angstrom, then what will happen? It will go on searching the minimum with various steps, and finally it will reach here. So this process is called as optimization procedure. So we can, given a structure, initial structure, and the method and theory, we can use computational chemistry for optimizing the system to getting the structure. And we can see this optimized structure is quite means getting idea about the actual structure, like maybe X-ray structure or the molecular structure calculated by spectroscopy. So these structures are getting means quite closer. So then we can, the remaining part of, as we excluded the kinetic energy of nucleus, we can add that kinetic energy, and the first part, which is U of R, this one, we can add this part here, so that we will get a, so this is a kinetic energy operator for nuclei, and this one is a potential energy for nuclei. So we can say this is a potential energy surface. Why? Because U of R, which we are plotting, is a potential energy for the nuclear Hamiltonian. And also then by getting the that structure where the minimum is there, so this is this will give us the various properties of that system. So we can use this to get various properties. As I told you earlier in earlier slides, that we will get dipole moment or charges or other parameters to understand chemical aspects of the system. Okay, so now how to solve Schrodinger equation, electronic Schrodinger equation? Because for many electron system, it is not possible to solve Schrodinger equation. Why? Because electron part, this part is we are not getting, still we cannot solve exactly this part. So that is the problem. We have to use approximate methods for this, although we can say those are approximate method, like variational method and perturbation theory. So variational method, we can see that example of variational method is molecular orbital theory, and as all of us know how molecular orbital theory is important in chemistry. So although we can say these are approximate methods, but they are very, 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 very important, very, very useful to understand chemistry. So we have to go ahead to understand chemistry. Okay, so for this we need psi, as we have seen that earlier equation H psi equal to E psi. So we have to use the wave function psi, and then that wave function we can use in the form of Slater determinant. So what is that Slater determinant? Slater determinant of form is here for n electron system, or n, what we can say, yeah, n electron system, we can use this. These are the, like, let's say for 2 electron system H2 molecule, H2 molecule electronic configuration is 1s2. So 2 electrons are there, and 1s1 alpha and 1s1 beta. So these 2 electrons, so we can write 2 by 2 Slater determinant, which is here, and then we can write with n factorial, that is number of this one, what we can say, n is number of electrons in that. In Slater determinant also we can write various expansions. This is, let's say, for ground state. Even for excited state determinants we can write, and we can use that wave function to this to use in the calculation. So why we have to choose Slater determinantal wave function? Because it is antisymmetric in nature, that means obeying Pauli exclusion principle. It is needed when 2 electrons change their position, the wave function should change. Okay, so we know that as we change 2 columns or 2 rows of a determinant, then its value will change. So it's antisymmetric in nature. So we can use Slater determinant given by Slater. Okay, so I will not go into much detail, but let's go with what theory is there behind that. So there is one theory which is called as Hartree-Fock approximation, where we can use a ground state electronic configuration. Let's say for neon atom is this one here, 1s2, 2s2, 2p6. So we throw 10 what we can say electrons, so we'll get 10 by 10 what we can say Slater determinant. We can use that, and then yeah, we can solve that the equation in iterative method, because as I will come to that why iterative method is needed. So we have to, while solving, what we have to do, we have to convert the system, which is many electron system, to 1 electron, what we can say Hamiltonian or 1 electron operator system, and then we can solve that one in very smart way. So here is the equation that we can construct a 1 electron operator, which is called as Fock operator. And this is one equation for this one, and we can solve that to get energy, which are orbital energies. Yeah, here orbital energies and the molecular orbitals we will get. And these molecular orbitals we are taking as a linear combination of atomic orbitals, which atomic orbitals will be represented by various what we can say basis functions, which are two types, which that also I will say, go through that as a Gaussian type orbital and Slater type of functions. Okay, so here one thing is that this Fock operator is based on this is integration of phi mu star f phi nu. So this is what we can say one Fock operator element, and like that when we arrange this in matrix, that will be a Fock matrix. So we can solve these equations by using matrices. That is really important, and on computers we can study matrices very well. We can do calculations with matrices. So that's why computers are very, very important for us to solve such equations for bigger systems, many electron systems. So we are getting such kind of secular equations. So these are the secular equations, and then we can solve these secular equations as to get coefficients. What are these coefficients? These are the contribution of respective atomic orbital in the given molecular orbital. So in the ith molecular orbital, what we can say contribution of this atomic orbital in that particular molecular orbital. So these are the what we can say molecular orbitals, phi 0, phi 1, phi n, and these are the orbital energies, and we will get the respective coefficients for those molecular orbitals. So these coefficients we can calculate with this as well as energies by solving such equations. Actually, to do the calculations, we need also, we can expand this one and here we can write electron correlation as we are getting in with Hartree-Fock energy and exact energy, the difference, because there will be some difference, and that we are saying as a correlation energy, which is the extra energy which we have to add in the Hartree-Fock energy. So this correlation energy we can calculate by taking, as I earlier mentioned, that excited state determinants we can add and we can use for that, so we'll get more accurate results. So I will not go into much detail because I have to give an overview of this. So see, there are for Hartree-Fock theory, let's say this is the example here. Now it's a let's say ground state, and then here it's a one electron, this one we are exciting to the unoccupied molecular orbital. So this is a singly excited, then this is also a singly excited, where this electron is getting excited to this part, from here to that part, then doubly excited, then triply excited, quadruply excited, and so like that n-tuply excited state determinants we can form, and we can use them to form a wave function like this. So this wave function is for Hartree-Fock, and then we can add this excited state determinants in that to get the energy. If we take all the excited state, we can say that as a full CI calculation. And but it's not possible to get all for many electron system because of computational time also and space. So full CI calculations are generally not computationally feasible. So we must cut it into some way. So we can write CISD, means CI with singlet and doublet, like that, or maybe further order we can use as we go on increasing the singlet, doublet, triplet. So computational time will be more, and so it will be very what we can say expensive to do calculation. Another method which we can use, approximate method, that is perturbation theory, where in the variational method, where we can use variational principle, that expectation value, I will give that equation further, that integration of psi star h psi d tau divided by integration of psi star psi d tau. That is the expectation value or average value. If we take any trial wave function, then the energy average value or expectation value is always higher than the or equal to the actual exact energy of that, or if it is a ground state, exact energy of ground state. So that is what we can say. We cannot go below the exact energy for with Hartree-Fock theory. So there we can use as a that is a variation in variational method. We can vary actually atomic orbitals. With there we can fix the atomic orbitals and vary their contribution, as I given here. This one here we can vary coefficients, their amount for forming the molecular orbital. But in perturbation theory, what we are doing, we are actually what we can say perturbing a system, means we are perturbing a Hamiltonian. So for the system which is not solvable exactly, Schrodinger equation, so what we can do, we can divide that system in two parts. One part which is exactly solvable, and another part which is extra to that, we can say that as a perturbation. So we can solve, we can use that bifurcation and then do the calculation with various orders of approximations. I will not go into the details of that, but there will be second order MP2, MP3, molar percent, second order molar percent, third order or fourth order. Again, when we increase the order, calculations will be more and more what we can say costly. Okay, so that because in perturbation theory we have to use also excited state orbital energies. Okay, so these are basically two methods which we can use to go ahead for many electron system and to get the idea. Another one is that we can also do by because as we know that valence orbitals are really active and involved in the chemical bonding or interactions. So inner orbitals we can keep frozen. Inner means what? Core orbitals we can keep frozen. So in oxygen, like 2s and 2p are valence, and then 1s electrons, those are inside one. So those are not be correlated, which are inside one. So only correlated is outer valence 2s and 2p orbitals. And then they have constructed in the programs, or they have constructed the atomic orbitals, basis functions, in the form of basis functions for this frozen, because it will save time. It will reduce the complexity of the calculation. The one more theory, earlier theory which we have seen, the Hartree-Fock theory, where we can use a wave function as a basic unit to do calculations. Another theory which is density functional theory, that is based on electron density. As we know that the wave functions for it's for all the axis there are X, Y, and Z axis for each atom. So if there are n atoms, so 3n parameters are there. So we have to move them for optimization. But here now, electron density, we can take electron density of whole molecule or whole system, and then we can use that for electron density at one point only 3 parameters, X, Y, Z, we can say. So that is to do calculations much, what we can say, time will take less. And also it will, as we have seen in the Hartree-Fock theory, electron correlation is not included, but in some way it is included in density functional theory. So we can, so this density functional theory is very, very good for smaller molecules, organic molecules, and smaller other systems also. So it's very famous theory, density functional theory, where we can use various, what we can say, functions. So this is general, maybe I'll not go into deep. So as I told you, this is the expectation value equation in Hartree-Fock theory, psi h electronic psi, this is integration, and this one is psi, integration of psi star psi d tau or volume element is always greater than electronic, which is true ground state. Here, this is function of density. And in both cases, we will get orbitals, and then we can solve them, and we'll get energies in both the systems. By using a Fock operator, we can construct and we can solve. Okay, so to get atomic orbitals in these systems, the methods, we need basis set, means basis functions, which we can use to construct atomic orbitals. So basis set, as we have seen that we can use molecular orbital as linear combination of atomic orbitals. To get these atomic orbitals, we need basis sets for to represent that particular atomic orbital, basis functions. Okay. So two types of basis functions we can use especially. That is, first one is a Slater type function. The form of this Slater type function is e raised to minus alpha r, so exponential form. And another one is Gaussian type function, e raised to minus alpha r square. So it's a bell shaped, is a Gaussian, and this red one is Slater type function. Actually, if we see this Slater type function is representing the atomic information or represent atom very well. And this Gaussian type, see here, there is a problem because here we can see a cutoff cusp condition that first order derivative is 0 for Gaussian, and for Slater that is non-zero. So that means at the here 0, actually this Gaussian functions are not being. So what they are doing, they are taking a combination of many Gaussians. Why? Because Gaussian function is very easy to Gaussian product theorem. Product of two Gaussian is a Gaussian function. So that is very important. And to do calculations on computers also, it is very easy to go with Gaussian functions. So that's why Gaussian functions are very famous. But Slater type of functions are important to give the actual properties of those atoms or molecules. So that's why we can use combination of Gaussian functions. We can say that as contracted Gaussian for to do calculation. Okay. Now another thing is that we have to also use basis sets. So people have constructed, like Professor John Pople, who won the Nobel Prize in chemistry for his work in quantum chemistry. He's very famous, very, very famous important software is Gaussian software to do calculations in chemistry. So we can use such type of Gaussian functions to construct the basis set or atomic orbital functions. So if we say is a 6-31G means what? It's a 6 primitive Gaussians we can use for what we can say core electrons inside electrons, and for valence electrons we can use 3 and 1, two sets. One set is of 3 Gaussian, another one is 1 Gaussian, and we can construct that one. As like in carbon for 2s 2p we can use 3 and 1 function set. Similarly, we can also add another one more set for what we can say valence orbitals. Then this star means we can add polarization function, because as when these anions or these will interact, then or a unit positive charge will interact, then it will polarize the system. So to get that one in the calculations, or we have to what we can say add the polarization function. Also diffuse functions, to get interaction of longer distance we have to add diffuse function. So this plus means, and 1 star here means addition of polarization function for AV atom, that means other than hydrogen. Similarly, if we put star 631G star means adding polarization function to heavy atoms, means other than hydrogen, and hydrogen also. Similarly, for plus here 631 plus G means what? Adding the diffuse function to heavy atoms. And if I do 631 plus G means adding the basis function, adding the diffuse functions to hydrogen also. So like this we can construct this, and we can, so this one is happening in the calculations. So let's take some example for H2 plus system, which is 1 electron system. We can solve it exactly. But to get the idea about molecular orbital theory, this is a prototypical example we can use for this. And then we can solve the like Hartree-Fock theory or density functional theory and calculate the molecular orbitals by using variational method, molecular orbital theory. So 1s A and 1s B, this is 1s atomic orbital of atom A, and this one is in atom B, as in H2, HA and HB we can write, and then we will get this is a molecular orbital. By solving that we will get molecular orbitals, and the here contribution of 1s A and 1s B is same, that is square root of 0.5. This is plus. Then another molecular orbital which we are getting is 1s A minus 1s B. By solving those secular equations, we have to construct a secular determinant, solve that determinant, get the what we can say orbital energies, use each orbital energy again to the secular determinant, and get the what we can say solve the to get the secular equations, we will get the set of coefficients. So these are the set of coefficients we are getting. So first one, which is having lower energy, is we can say a bonding molecular orbital, and another one is anti-bonding sigma star molecular orbital. As we know that, so this is the what we can say we are getting from solving the molecular orbital theory. Okay, so as we know that for bonding and anti-bonding molecular orbitals, their probability density, sure, we can calculate that, and this probability density, when we calculate, this is the form. And see here 2 5 1s A and 5 1s B is a plus, so it's getting added electron density. When two atoms are coming, two atoms are interacting. So here the electron density is enhancing at the center of two nuclei. And because of that, these electrons will attract the nuclei, both the nuclei, and it will go for more stabilization, so more lower energy. Then the other one, which is negative here, so that negative part we are getting here, and so it will increase the value. So it's something like this. See here, it's given in this picture that this is a one atomic orbital, red. This is another atomic orbital, red one. And when they will add together, they see this, there will be addition of this, and electron density will be like this. So there is enhancement of electron density in between this atom and this atom place, enhanced density. But here we can see that at this one, it is going down at the center. Electron, this density is 0. And then because of that, what is happening? The electron density will be 0. So it's a lesser, so it will increase because nuclear electrons will be lesser than the when we add two atoms without interacting and calculate the density. So it is a destabilizing molecular orbital. This is usual our molecular orbital energy level diagram, and this all of us know that 1s and 1s atomic orbital they are interacting with each other, and here now getting the bonding molecular orbital and anti-bonding molecular orbital. We can say this is a Girard and ungirard. Girard means what we can say even means center of symmetry we can see. So we will get same value from when we go from one side to another side through that center. Here it's we are getting ungirard, means odd value, we will get that. So this is H2, and we can calculate bond order, that is number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital divided by 2. So we will get bond order by using this equation. As we know, this is helium also, we can explain very nicely that why there is no interaction between two helium atoms, because bond order is 0 for that. We can calculate that. So then these are again how they are combining atomic orbitals. Just pictorial representation that how we are getting these molecular orbitals. Let's take one, this one as F2 molecule, and as usual, we can write these bonding and anti-bonding molecular orbitals, Girard and ungirard, we can give them for a homodiatomic molecules. And this is highest occupied molecular orbital, that is HOMO, and this one is lowest unoccupied molecular orbital. These are also very, very important, because as we have to remove the electron from the system, see from this, it's easy to remove from this because energy is higher. The other electrons are core electrons, which are very closer to nuclei, tightly bound to the system, and we can remove electron from here. So ionization potential we can calculate through this. As with the Koopman's theorem, we can see that, or we can actually write that the ionization potential of that particular electron is what we can say negative of the value of that particular molecular orbital. That means if we remove from here, so negative of HOMO is ionization potential for this electron. Similarly, LUMO, when we have to add electron here, then negative of LUMO will be its electron affinity. So like that, we can go for getting the properties of molecular properties, which we can use further. So this is general idea about this, what molecular orbital theory gives. We can see that how we can use these molecular orbitals to fill up. Here for B2 system, we can see two unpaired electrons, which will give us the paramagnetic nature of B2, as well as O2 also has two electrons. When we feel those are unpaired electrons. So these chemical aspects we can understand with molecular orbital theory. So it is very important to get idea about so to go for understanding the chemical nature of molecules, how they are interacting, atoms are interacting, getting the more stable structure, and also the properties which we have. So to get the properties, we need the stable structure, as I explained in my this one, that we have to do optimization of the system, giving the initial geometry, then it will calculate the energy, and then further it will go to get these properties we can use to understand chemistry. So this is the computational chemistry, or another name, molecular modeling, we can say. Again, coming back to after this, what we can say theoretical aspects. Again, I'm coming to competing molecules, or how can we do this one, why. So we will get the electronic structure theory can be used to, which is a very useful tool, and we will get we can solve, or we will get insights to the physicochemical problems. This provides results for those involved in experimental, also this computational chemistry, as I mentioned earlier. Then again, interpret the properties of the novel developed material. So we can see what type of properties will be there for the newly developed material. Then we can also do modeling of biochemical systems, then modeling of intermolecular interactions. So in what we can say computational chemistry, what we can say in one word, computational chemistry is one of the most rapidly advancing and exciting field in the natural science today. As this is given by Delano Chong in 1995, this statement, very nice statement or sentence. Many experimental chemists use various kind of spectroscopy in their research, even though they are not spectroscopists. They're not very thoroughly means deeper in the spectroscopy, but still we can use various spectroscopic aspects to maybe determine structure, like NMR, or for organic system, let's say NMR, or IR, UV, and then we will get the structural information. In a similar manner, more and more scientists are applying computational technique as another weapon in their arsenal. Means, although we don't know, means I'm talking in general, because here in our audience, most of the people are experimentalists. So although we don't know the deeper theories and equations, how can we write these equations or solve these equations, but as like a spectroscopy, as we are giving the sample for NMR, and then although we don't know what NMR machine is doing inside, but whatever NMR spectrum we are getting, we can analyze that and use that one to help to understand chemistry there in that system or in that process. Similarly, here also we can use computational chemistry to similar manner to understand chemical aspects of various organic, inorganic, bio, and various systems. So to what we can say, summarize these methods of computational chemistry, depending on the system size, we have to use smartly what type of computational method we have to use. As we can see towards this left hand side, see, system is very big, as order of, let's say, 10,000. Then we have to use force field, or what we can say, molecular mechanics methods. What is molecular mechanics method? That molecular mechanics method, it is based on Newton's laws of motion and classical mechanics methods. We can use classical mechanics laws to study that. Then some methods, these are okay, there are another method, ab initio method, which we have seen, Hartree-Fock theory, which is in the order of 100 atoms. We can study very well. But as we have seen the perturbation theory method, MP2, see only few atoms, tens of atoms we can study. But for couple cluster and CI, see few atoms only we can do. Semi-empirical methods, we can, these are ab initio based on ab initio method, but we can use some parameters experimentally or highly calculated with ab initio methods. We can use those parameters to do the calculations for these methods, and we can see the what we can say, accuracy and the size. So if we want to do calculations of this size about 1,000, then we can use that. So as we have to go inexpensive methods, then okay, computational power we need much lesser. But for higher calculation methods, we will need increasing time on these methods as well as higher computational power also. So this is the what we can say about general idea, that which method we have to use smartly, which method for which system we have to decide what type of method I should go for biosystems. Now in biosystem, let's take example that suppose one I will come to that maybe. Yeah, biomolecule, maybe we are getting here. So let's take biomolecular system, and we can use this we can study biomolecular systems for to their actually how to study, understand protein folding problem, catalysis, molecular machines, something like that. And we can also predict energetics of various biological processes, ligand association, protein stability, then designing of novel molecules for particular properties like drug and protein engineering. So these are bigger systems. So for that, I told you, as I mentioned, we can use force field methods. That means which are based on molecular mechanics, Newton's laws of motion. On that, we can use the systems. There are various softwares like CHAM, AMBER, and other GROMACS. So we can use these packages for study these systems. Then for biomolecular energetics also we can use we can also certainly use by some quantum mechanics described by quantum mechanics, and it's very costly to do the calculations. Molecular mechanics force fields are classical approximations to the quantum mechanics. So for a bigger molecular system now, the Nobel Prize for in chemistry 2013, Karplus, Warshall and Levitt, for the QMMM type of calculations for studying the biosystems. That means a bigger part size of molecule. See the actual reaction happening in the some pocket of that particular system, and that pocket is smaller part, and outer side is a very big part of that system. So bigger part we can consider with force field methods or molecular mechanics methods, and the central part, which is important, where really atom transfers are happening or electron transfers are happening, we can use that part as a quantum mechanics with the use of quantum mechanical calculations. So this is a QMMM type of calculations, the method which they have shown. So people are using also QMMM method. We can do molecular dynamics, that means with respect to time, by using this kind of equation that we can calculate the force, and force will give us the idea which direction we should move the system, which direction we should move the atoms if to neutralize the that force. So what F we can write as a minus del of E energy. And from that we can calculate force, and from force we will get with the force we will get the position. So with respect to time, at what time that particular atom or system will be, in what form, we can do calculation of this with molecular dynamics. Yeah, there are various, as I told you, systems specifically for biosystems. We can use, see, as I told you, we need initial structure to do calculation, because with initial structure, instead of searching at lot of other possibilities, if we give the better structure, as we know what type of structure will be there for, let's say, for water molecule, tetrahedral structure, or for CH4, a tetrahedral structure, or some other molecule where there will be sp2 hybridization or sp hybridization, as like in HCN or something. The systems we can give the structure, and then it will be easy for the softwares to do calculation with having a so what is the important there? To search that minimum value on potential energy surface. If there are many minima on the potential energy surface, so a global minimum, which is the deepest in all the minima, we have to do calculation. We have to search that one for the stable structure. And for various forms, let's say two molecules are there, one is in cis form, another one is in trans form. So for each form, there is one potential energy surface, and then how one surface will get transferred to another surface through transition state, that we can do such kind of calculations also. This is example C. We can see now a key signaling protein complex. Long back, actually, they have done example of hetero trimeric G protein. Roughly, water molecules there are what we can say. There are total atoms in the system 94,384. So see, we can use this molecular mechanical system to study bigger molecular systems. This is another example, a antiviral carbohydrate binding protein we have studied. Yes, then molecular docking is another area. Takes two molecules and tries to fit them together. Docking means, as in a sea, how a lighthouse is playing important role, blinking light to in night, or that the ships will go to that place. So like that, this docking, this when we put the molecule, particular, let's say drug molecule, to a target, then we can keep that one and do the calculation and find out the what type of interactions are there. We can do the calculation of this. Yeah, like there is one example, with alpha 1 AGP. You can see inside that particular molecule is there, which we are docking to the protein. Then structural similarity. It will help as a very important example, means in pharmaceutical, that drug designing. Suppose we are having a particular drug which is a natural drug, and which is uh, useful for particular disease or active for particular disease. So can we improve the activity of that by modifying that drug? So we can, let's say we are having such modifications, maybe somewhere we put OH group, Cl group, or some other group. And so what we can say, structure activity relationship. As we change the structure, activity of that drug will change. So to bring a particular drug as a general, this one, that it will need 15 years generally, and $1 billion will be the, what we can say, uh, cost for that, for one drug to synthesis, from synthesis, then vivo, vitro, then toxicity, and bringing to the market. But now here, so suppose we have 100 such kind of structures, similar structures, then we will need $100 billion also per drug, 15 years to bring that one in market. So it's very, very difficult. But if we do what we can say structure activity, QSAR, quantitative structure activity relationship, then we can find out best 5 drugs out of those 100. So what will happen? Then we can take these 5 drugs for synthesis and their activity test and other things, which definitely we will get a better drug from out of those 5. So we can save $95 billion, because total cost, if we will not do this, $100 billion. So only we need $5 billion. So it's a, see, we can, it's very useful, such kind of docking and drug designing for this. Yeah, so this is example of drug designing. This is known drug, and we can modify with certain things, and then we can do the QSR study. Even we can do quantitative structure property relationship, which one of my PhD students, she has done that this QNON system from 380 nanometer to 700 nanometer, we have seen its absorption for solar cell applications. So we can do such kind of modifications for getting the activity in materials also. So this is also another a recent story of, he is my senior, doing has done PhD in my group here in Savitribai Phule Pune University under Professor Sridhar Argadre, and he is now a, just a minute, I'm sorry. I'm sorry. Let me, should not disturb. Yeah. So Dr. Kulkarni, he is Vice President of Discovery at Nova Lead Pharma Private Limited in Pune. And he has developed that indigenous drug for diabetic foot ulcer. So from scratch, 0 to this one, this is what we can say, this drug, so this product involves indigenous development from scratch. It's a successful environment screening several drug with a, so this is repurposed drug, and this is for diabetic foot ulcer. This is in, I think this is in this news in August 2024, and we can see what he said in this news. The approval of Noale's drug is significantly because DFU is the leading cause for lower limb amputation globally, with about 1 lakh annual incidences in India alone. So they have to cut their limbs and this one. But his drug is working very nicely by doing computational chemistry, and based on this computational chemistry base, they came up with this drug for this diabetic foot ulcer. Okay, and then also this is passed from CDESCO, reproposed drug. Okay, so then DFU is diabetic foot ulcer, yes. And another area where bioinformatics, we can compare proteins, then their similarities and go for further their use with computational chemistry. This is another example, which is bacterorhodopsin. This is a simple molecular machine prototype where proton transfer is happening. This rhodopsin is very important for our eye vision, and so their proton pump is there, and because of that we can see with this vision. For the vision it is important. So how that mechanism of proton transfer is happening, we can study with computational chemistry. So by you similarly for CA-ATPase pump active in muscle contraction, also we can study with different phases. This is some potassium channel study. So there is another factor, but I think now maybe we'll take this for tomorrow. I think this is 4 o'clock. So I should stop here, and then application and the research, how computational chemistry with examples with my own research we can see tomorrow. So I think I should I'll be means I want to stop here for today. And if you have any question or something, I'll be happy to discuss. Yes. Hello.
Okay, sir.
Yes, sir. Yes.
Yeah, so I should keep some time for maybe some discussion, or maybe tomorrow also at I will start at same time, and maybe at that time also we can. So I again thank to the organizer for giving me this opportunity to give a brief view of computational chemistry, how it is useful, and also tomorrow also I will cover some part from that. Okay, so thank you very much.
Thank you, sir. Participant having any questions or the queries? Either we can conclude. Sir, I think there are no queries. So if you could permit, shall we conclude, sir?
Yeah. So please, then.
So now may I request Dr. Ravi ji to please propose vote of thanks. Dr. Ravi Bansal ji, please.
Yes, sir. Good afternoon to one and all. I, Dr. Ravi Bansal from School of Chemical Science, Devi Ahilya Vishwavidyalaya, Indore, MP. It's my privilege to propose vote of thanks for wonderful sessions. On behalf of MMTT and Sant Gagre Baba in Amravati University, I extend to my heartfelt gratitude, respected sir, for sharing such a valuable thoughts and inspiring words. The lecture was very informative and valuable. We get more knowledge about computation community by this lecture. Once again, thank you for sir for your presence, encouragement, and willingness. We truly appreciate your times and efforts. Also thankful to organizing committee for arrange a nice lecture. Have a nice day, sir. Thank you very much, sir.
Thank you very much. So see you tomorrow.
Thank you, sir.
Yes.
Thank you so much.
Yes, sir.
And
See you,
with
sir.
kind consent of Professor Subhash, sir, I would like to declare that this particular session will be over. Thank you so much, sir.
Thank you, sir. Thank you very much. So I will log out now.
I think we'll move for further session. Dr. Robin sir is there. Dr. Robin Kumarji.
Yes, sir.
So we will take first consent from our expert, Dr. Preeti Patil, madam, and then we will start with the session. Hello, Dr. Preeti Patil, ma'am.
Yes, sir.
Yeah, ma'am. Good afternoon, ma'am.
Yeah, good evening, sir.
Yeah, shall we start with the session, if you could permit, ma'am?
Yeah, yes.
Yeah, so on behalf of Madhya Mission Teacher Training Center and Garge Baba Amravati University, our distinguished course coordinator, Professor Manisha Kodape, madam, and all our learned participants, I extend my sincere gratitude. I extend my heartfelt gratitude and warm welcome to Dr. Preeti Patil, madam, first of all. And now may I request Dr. Robin, sir, to first introduce our guest in brief, and then we will start with the session. Cheers, Dr. Robin, please.
Yes, sir. Good afternoon to the Honorable Course Coordinator, MMTTC, Sant Gadge Baba Amravati University, Course Coordinator, Professor Manisha Kodape, madam, technical team, and esteemed participant faculty members. I, Dr. Robin Kumar, Assistant Professor, Department of Chemistry, University of Delhi, take an absolute privilege to welcome you all to this session of our refresher course. Today, we have the distinct honor of introducing a highly accomplished academician and researcher as our resource person, Dr. Preeti Mangesh Patil. Dr. Patil currently serves as the Assistant Professor and Head of the Department of Bioinformatics at the Rajiv Gandhi Institute of Information Technology and Biotechnology, Bharati Vidyapeeth, deemed to be University in Pune. Dr. Patil boasts an exceptional interdisciplinary academic background and decades of academic service. She holds an MSc in microbiology from Amravati University and advanced diploma in bioinformatics from Bioinformatics Center, University of Pune, and a PhD in biotechnology under the Faculty of Science Biotechnology of Bharati Vidyapeeth, deemed University Pune. She brings a wealth of teaching experience with 17 years dedicated to undergraduate education and 20 years to postgraduate education. Alongside 15 years of active research experience, she has successfully guided 45 MSc students to completion and is currently mentoring 4 MSc and 4 PhD scholars. Her core expertise span across microbiology, bioinformatics, drug designing, metagenomics, and cancer biology. Dr. Patil's contribution to scientific literature and industry innovation is remarkably extensive. She has published 49 international and national research papers in reputed journals and have authored 9 books. Her innovative research has yielded 2 granted patents and 1 copyright alongside the successful completion of 5 research projects. Beyond the classroom, she serves as a member of the Board of Interdisciplinary Studies for the Faculty of Interdisciplinary Science at Bharati Vidyapeeth. She also bridges academia and industry as the scientific advisor for gut microbiome at the Decades Private Limited, Bangalore. Recognized for the pedagogical impact, she was honored with the Best Educator Award by Ramakrishna Education Trust, Bhid district of Maharashtra. She is also a trusted reviewer for several reputed scientific journals. Given her profound expertise at the intersection of biology, computing, and structural science, she is uniquely positioned to address us today. She will be delivering a specialized lecture titled Structural Biology and Proteomics for Chemists. Please join me in extending a warm virtual welcome to Dr. Preeti Mangesh Patil. We are thrilled to have you with us today, ma'am, and the screen is yours. Thank you.
Thank you, Robinson.
Preeti,
Am I audible?
Yes, ma'am.
Yes, ma'am. Audible.
Yeah, okay. Thank you. And I really don't know how much is the level right now for the digestion of the participants. This is 4 o'clock in the evening. So I'll just try to make this particular session more interactive rather than just a lecture. Okay. I forwarded a message to Dr. Manisha that so that the participants will going to install the 2 softwares. So guys, just let me know whether you will be successfully able to download those softwares, because it's just a matter of a time of 1 or 2 seconds.
Yes, madam.
Yes, ma'am.
Yeah, thank you.
Yes,
Thank you so
ma'am.
much. Thank you. So we will be having a practical session. We don't have a lecture type of a session because I don't believe in a lecture type of a session. So it may happen that if you stuck somewhere, if you're not finding it, maybe you'll not get it. So just let me know. Stop me there. I'll explain it again. Fine?
Madam, one more request. Can you please make this presentation in the PowerPoint mode?
Yes, sir. Yeah. Is it now?
Thank you. Yes, ma'am. Now it is visible. Thank you so much, ma'am.
Yeah. Okay, fine. So good evening, everyone. And thank you, organizing committee, for giving me this particular opportunity. So Dr. Robinson has already been given my introduction, and I think that's enough. So let's start with this particular session. Okay, I kept the theme as a structural biology and the proteomics for the chemist. So actually the title is very big, very huge. So I'm just taking the 3 different insights for you right now currently in this particular lecture. Okay, so we will just try to bridge the gap between the chemistry and the structural biology over here. So all of you, I really don't know what is the exact background of the participants over here. I'll imagine that, okay, we do have the interdisciplinary participants, or maybe the maximum of you are from the chemistry backgrounds. So you are more well aware than me about the chemistry of the molecules, right? So the chemists know about the peptide bonds and small molecular structures, or the stereochemistry, spectroscopy. So what part you should go ahead with? Because you are already the masters in the chemistry, and which will be going to be helpful to you is the structural biology. Because there are the thousands of the atoms into the 3D fold, and how we will be able to find out its structure without directly going for the wet lab. Wet lab means actually whatever you are doing into the your labs. Whatever we do in the computational biology, so we do into the dry lab. So we used to call it as a dry lab or the in silico method. And whatever you are doing over there, the chemist or the zoologist, botanist, biotechnologist, so they actually work into the wet lab technique. So what we try to serve here is that we try to reduce your time, energy, and the money, so that we try to take you towards nearest to the accuracy. So we'll be able to narrow down some searches for you. So you'll be able to go for the authentication of those narrow down searches. You need not to start from the scratch over there. So we'll try to bridge this particular gap with the help of the knowledge of a bioinformatics over here. So I'm not going currently for a core bioinformatics. We are just sticking to the structural biology over here. So I'll be going to take some of the part of the PDB. Maybe some of you are already aware. So it is the biggest repository of the structural for the structures of the proteins over here. Then we will try to find out some of the components with the help of a 3D visualization tools, and then we go ahead with the AI predictions of that 3D folds. So we will be going to take care of these 3 particular pillars over here today. So the protein data bank, which will going to give you the information regarding the 3D structures. Then we will go ahead with the visualizing pedagogy with the help of the PyMol and the Chimera. And then we'll go ahead with the AI protein folding analysis. Okay. I'm just taking all the sessions interactive so that you will be able to understand it. Okay. So some of the part we will take syntax based, but it's very, very easy syntax for you. You'll be able to do it. And when we actually able to do it, we feel, okay, yeah, we did it. Otherwise, just listening to the lectures and then going through different types of a command. Like I'm also from, my background is MSc microbiology, and later on I shifted to the bioinformatics. So I know that how biotechnologists think, or how the biology people actually think of the syntax. So we do have a huge fear regarding the syntax. Okay, so I'm just trying to make it very simple for you so that you will be able to do it at your end. Now let's start with the protein data bank. So what is it? So it is a huge repository about for the experimentally driven proteins. It may be driven with the help of X-ray crystallography. It may be driven with the help of the mass spectrometry. It may be driven with the help of the NMR. And there are the certain types of the biomolecules which you will be finding at a predicted biomolecules with the help of the bioinformatics technology. So this is the huge repository for the 3D structural data. We used to call it as a very our source of authentic structural database. Okay, so currently right now we do have the more than lakhs of the records in the PDB. PDB do have the mirror sites, like one in in US, that is the RCSB. This is the Research Collaboration of Structural Biology. Then you do have the PDB in the Europe, and then you do have the mirror image, the PDB in the Japan also. So we'll be going to get the information regarding these wet lab techniques. This is free, and anyone will be able to utilize this PDB. It is the rich source of the information regarding the 3D coordinates. Then it is a research of the information where you will be able to extract the sequence type of data, where you will be able to extract the structure type of data, where you will be able to extract the geometrical type of data. You will be able to get its publications over there. Means each and every aspect, whatever you ask for, you will be able to get in the PDB. But these are what those particular structure which has been deposited by the authors or the researchers who has already been worked on those particular structures. Rather than going to PPT mode, I'll directly take you to PDB. So everyone, please go on the PDB database. In the Google, just type the PDB and you will be going to end up with this homepage. Because whatever I'm doing, you please simultaneously do so that you will be able to understand the stuff more clearly. Is my screen visible to you, guys?
Yes.
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 Yeah. So I'm again starting with the PDB. So this is a PDB homepage. Now, as you will be able to see, so currently these many structures are available. These are the structures from the PDB structural archive. So these are the actually structures which is coming through the wet lab. And these are the predicted structures which are available. We do have these many mirror sites for the PDBs. Okay. Here you will be able to see that you will be able to deposit a structure, search a structure, visualize it, analyze it, download the data regarding it. On the front page, you will be able to see all the announcements from them. Every month, they're going to publish the one of the molecule as the best molecule of this particular month. So we'll be able to see this is the pentavirus or molecules which they are published in this month. So this is the molecule of the month over here. Now here at the search box, you please type any type of a protein in which you are interested. Okay. So I'll just go with, I'm just typing the insulin over here. Okay. This is a small molecular structure. Now, once you will type any type of a protein in which you are interested, so you will be land up with this particular page. Okay. So currently there in the PDB database for the insulin, we do have the 471 structures, as you will be able to visualize this. Now, these 471 structures has been divided. So all the structures has been experimentally driven. Then as per the organism wise, you will be able to find this. This is the hierarchy as per the organism wise, that from the Homo sapiens, we got this much, from the Scrofa, we found this much, from the Bos taurus, we found 40. So likewise, as per the taxonomy, then as per the experimental method. So if you are, you only want data regarding the X-ray crystallography. So just click on the X-ray crystallography, and now from the more than 400 records, we are right now in the 329 records. So these are the all experimental proteins with the help of X-ray crystallographies. So here you do have the many limitations. These are going to be called as the limitations. As much as the specific data you are going to put into the search box, that much specifically you will be able to search. Okay. So these are the all options which you will be able to use while searching the data. Now about this particular search, I'll just go to this very first molecule. This is called as a 1-APH. Now 1-APH is the accession number for this particular ID. This is called as a PDB ID. So it is the unique alphanumeric PDB will going to generate for the each and every molecule. So you will be able to see that this is the PDB ID, and simultaneously you will be able to see that there is the one text file extension also which has been given here. So I'm just clicking on the 1-APH. So as you'll click on the 1-APH, you will be able to get such type of a page. Okay. Here you'll be able to get the information regarding this particular PDB ID, its date of index when it has been submitted. Then the classification. Okay, so currently the insulin, it is a hormone, and the organism, it is coming from the Bos taurus. So mutations, no mutation has been reported for this particular set of a sequence. But in the insulin, we have the many mutations which has been reported for the Homo sapiens. So this is what the old record. It has been deposited in the year 1992, and the data has been released for the public in the year 1993. And these are the authors of this particular, the paper which has been published for this particular structure. So these are the authors. So they have deposited this particular structure to the PDB in the year 1993. Okay. Now this experiment, this is the information regarding the experimental data which you are seeing over here. That the method is X-ray crystallography. Resolution is the 2 Armstrong. So very good. Then this is the data regarding the R value. So if anybody has been done the X-ray diffraction, so you'll be able to understand what is this exactly. So these are the coordinates and the values which they have observed over here. Now for us, the non-chemistry background people over here, so see, you'll be able to get the matrices over here. So this is called as a matrix. And this particular type of a matrix is going to give you the information regarding that how good this particular structure is. Currently, whatever the structure which we are seeing, so how good is it? So we do have the different types of the matrices over here. Just for example, we do have the clash score, we do have the Ramachandran outlier, or we do have the side chain outlier, or RZ outlier. So what are these? These are the different types of matrices on the basis of which they will going to judge the whatever the 3D structure which they have deposited over here. So how good that particular structure is. So actually the structure has been deposited with the help of an X-ray diffraction, and the diffraction has been shown good within the 2 Armstrong unit. But these are the different types of methods with the help of which they will going to judge this structural moiety. So as per the clash score, as you will be able to visualize over here, the red color of a data and the blue color of a data, right? So this pencils, which is of the red color to the blue color, so it is going from the worst to the better. So if you do find the percentile rank towards the blue color, means you will be able to say that you are visualizing a good data. If you are finding that matrices towards the red color, so as per the clash score, as you will be able to visualize over here, that the matrices is within the red zone. So as per the clash score, this is not a good structure. But same time, as per the Ramachandran outlier and as per the side chain outlier, it is one of the very good structure. Okay, so these are the structural validation techniques with the help of which you will be able to identify how good the structure is. Now, if I'm not be able to make you understand the thing. So here you do have the report. If you'll click over here, it will going to generate a complete validation report for this particular structure based on all these matrices. Now, just for your information, for all the structures, we will not be able to find the matrices which has been listed over here. It will be based on that how many matrices has been worked for that particular structure. So those many number of matrices you will be able to visualize. So currently we are able to visualize the 4 matrices. If you will go for the any other type of a structure, you will be able to visualize the different types of matrices over here. So what is this exactly? So these are the structure validation tools. So you know that one technique is a screening technique and another one is a validation technique. So this is what the validation technique for the structure assessment. So we are assessing this techniques, we are assessing the structure based on this particular technique. Now, if you move down, you will be able to get the publication which is related with this particular structure, that who has deposited that particular structure. And again, here it will going to give you the information regarding the macromolecules. So this is what the insulin A chain. So A chain is having the length of 21 amino acid long. It is coming from this particular organism. Currently, no mutation has been reported for this particular A chain over there. Okay. Now, if you'll see that they have given us a link of the UniProt ID. So if you all click over here, it will going to take me to the UniProt database, and the complete flat file of the UniProt will be going to be open in front of you. Okay. Now here, if you will move down here, you will be able to see the sequence. So this is what a sequence of this particular protein. Okay. So this is a chain A, which they are showing over here. So this is a chain A, and you will be able to visualize its sequence. Okay. Now they have given you the one scale which is called as a hydropathy. Now, what is this hydropathy? So you know that there is a hydrophobicity. So there are the certain types of the amino acid which is hydrophobic in the nature, while the certain types of the amino acid which is hydrophilic in the nature. So based on that, that particular scale, they have given you the values. So if I'll take my mouse to this particular region, if you see on the above sides that one pencil will emerge and it will going to tell me what is it. So what is it? The hydropathy value, its hydropathy value and its position. Okay, if I'll click over here, you just see the hydropathy value of this particular amino acid over there, that is a QL and E. So that will be going to tell us that, okay, this is the hydrophilic, while this is the hydrophobic molecules which we are dealing with. Now here you will be able to get that the disorder database is there. Now the disorder database is related with the information which has been enlisted into the disease databases. So if there will be the certain type of a disorder which will be going to be encountered over here, so they have predicted with the help of a disorder databases, okay, at that these particular positions, there are the certain paper which has been enlisted that if there may be the chances of existence of a disorders region. So these regions may get disordered into the certain types of the protein structures. Okay. Now we don't have any data regarding the disordered binding. Here also for this particular protein, we only find this much of the scales. So if you change the protein, you will get a much more scales over there. Now this is again the chain B, and it will again give you the same type of information over there. This is the chain C. Now at the downward, you will get the complete information about the experimental data, then its length, okay, angles, and again the validation technique. Now this is what the very first page, that is called as a summary page. This is the structural summary page of the PDB. So within this page, you will just get a structural summary. Now, if I'll move towards the structure file. So this is what the structure file for the PDB, where it will going to give us the structure of this particular molecule. Now, very sorry that I don't have that particular extension over here for the WebGL, but we will be able to visualize this structure in the other 3D visualization tool. Now, we'll be able to, let's see here, fine. So see, this is what a structure which we are going to see visualize over here. Now the PDB do have the two default structure visualization tools. So one is a WebGL and another is the JSMod. Okay. So if you do have the Java installed in your PC, you will be able to visualize that. And if you have the smart PCs in front of you, you will be able to visualize the structure into the WebGL also, because WebGL do have the what I'll be able to say, that WebGL do have the more advanced types of the options to visualize and analyze that particular structure. So you'll be able to visualize the structure over here. See, okay, you'll be able to change it into the any different types of the forms over here. You'll be able to color it with the help of the secondary structure rainbow methods. Okay. Now the solvent accessibility, you will be able to check its solvent accessibility, and it will going to show us the complete molecule is the solvent accessible. Okay, if you want to find out the cavities that where exactly, so it will going to show you like this. Okay, you do have the many different types of options over here. You will be able to execute those particular options, and you will be able to visualize your molecule accordingly. Okay. Then here there is another page which is called as annotations. Now guys, what do you mean by the annotations? So annotations means classified data. Just imagine in front of you one amino acid sequence data, and I just put that particular sequence in front of you without giving you any information regarding that sequence. So it is just a raw data in front of you. So giving the tags to the raw data is called as an annotation. Means we are giving the meaningful information or the tags to that particular data over here. So that's going to be called as the annotations. Now we are going to visualize the annotations for this particular protein through a different databases. So they have given us the annotations from the scope. Now scope is called as a structural classification of protein. So this is again a structured database, and with the help of this particular database, they have given us the information regarding this particular protein, like that the class which has been identified by this structural database, that is a scope, this is a small protein group, its fold is like this, the superfamily is this, family is this, and domain is this. Now for your kind information, the scope will classify the protein exactly just like as you classify or you have seen the taxonomy of the animals or the plants. So they do have their own tag, they have their own classification system, and as per their classification system, at the higher end it will going to be started with the class, then fold, then superfamily, family, domain, and then the members. So in this way, they are showing us the results in the scope database. Now we move down to the protein family annotation. So this is coming through the UniProt database. This is the complete information. Okay, now this is the data which is coming through the gene ontology. Now gene ontology is again one of the database which will be going to provide you information regarding the annotations of this particular protein, but this is regarding with its respective gene. So what is the polymer, what is its molecular functions, so in which particular biological processes it is involved. So every information they're going to give you over here. Then through the Interpro database. Now Interpro database is the biggest protein ontology database, and through which also they have given us or provided us the information. So you'll be able to visualize over here. You'll be able to get the many number of the accessions number for this particular sequence. So this is what the annotations which are available. Currently, I am not going for the full-fledged annotations for you. I have not opened any particular file because it will going to take much more time, and I need to finish the 3 modules for you today. So this is what the annotations is the complete detailed information regarding that particular protein. Now from here, if we move towards this experimental data, it will going to give us the information regarding the experimental information regarding that particular protein. So this protein is coming through the X-ray crystallography, and this is what the detailed information regarding that X-ray crystallography. Okay, you will be able to visualize the complete information. If you'll move here, we will be able to visualize the sequence for this particular protein, and as you will be able to see that they have not only shown us a sequence over here, but simultaneously they have given us the comparative analysis of that particular sequence through the different databases. Like this is what the sequence, this is a chain A, and this is its ID in the UniProt database. This is what its secondary structure confirmation. So if you just move your mouse toward the secondary structural confirmations, it will going to tell you what is it. So this particular patch of the amino acid will be responsible for formation of a helix. Okay. So this is what another helix from this particular region. So it has been predicted with help of the secondary structure. Then you do have the many other types of the databases through which they have provided us the information. So what exactly these people will going to do is that they will going to take the sequence information, and these are the different types of databases and the tools. So you're going to put those particular sequences into those particular tools or the databases, and these particular tools will be going to analyze the structural information for you, and as per the data which will be going to be extracted out by their algorithm or their prediction system. So as per their prediction system, they are providing us the results over here. So you'll be able to see the results over here with the help of their algorithms. Okay, there are many types of algorithm which has been given over here. The data, one of the data is from the peptide database also, and the scope database. Now from here you will be able to visualize, you will not be able to visualize the genome data because the genome data of that both stores will be available into the genome databases. So currently it's not available here, and they are not given any extension. And here you will be able to visualize the version. Now what do you mean by the version? We are working in silico data, and it is very important for us for the computational biology that the data should be updated. If the data is not updated, it is not useful for us. So it is very much important to get to know the information regarding the versions. Okay, that how many times that particular data has been revised. So here you'll be able to visualize that particular data. See, the last revision is in the year 2024. So you, so it is authentic enough that you will be able to go ahead. If you want to work on any aspect of this particular sequence, you'll be able to take this particular sequence from this database and will be able to work on it. So this is what the PDB. Now, when we have gone here on the home page, structural summary, you will be able to visualize these 2 tabs. That is, one is the display files and one is the download file. Over here, you will be able to display those particular files. And here you will be able to download those particular files. Okay. So this is what the file which you will be able to visualize here. Now, this is called as a PDB flat file. And what are the different types of tags or how you will be able to analyze? So see, this is what the name, this is the title, this is what the molecule type. So as you go on one by one, so within my PPT, I have just given you the information that how you will be able to read this particular file. So that is the flat file of the PDB. I'll show you through the my PPT that how you'll be going to analyze the data with through that particular flat file. Now here under the downloads option, what you will be able to do. Now this is what one type of a protein. You go here, you just if you want to find out its FASTA sequence, means only the sequence you are interested, you can click here in the FASTA sequence and you will be able to download the FASTA format sequence. So what is the FASTA format sequence? The FASTA format sequence is a sequence of the amino acids into the capital letter with its sequence identifiers. Okay, now there are the many types of the files which they have given here for the downloads. Currently, we are interested into the legacy file. So you guys please download the one of the legacy file. So see, legacy PDB file format. So just download that like this. I'm just downloading this particular file. Now the file has been downloaded over here so that we will going to visualize it through the 3D visualization tools. So you just keep it right now over there because we will be able to visualize it through the 3D visualization tool which I'm going to take. So through it, we will be able to download any type of a data which has been provided over here. Okay, you will be able to download the validation data also, this. Then you will be able to download the biological assemblies. And you will be able to download the XML files, the structural factors data also. Guys, right now I'm on this particular page and I could not be able to see you. So could you able to tell me that if you're stuck on any of the terminology over here in the PDB?
Good afternoon, ma'am. Can you say where I find this legacy PDB? Can you please
see, yeah, it's you please go on this download files. You are seeing this tab? Just click on it. Okay.
Okay.
Yeah, and here you will be able to visualize the legacy PDB file format.
Okay, thank you. Find it.
Yeah, well. Okay, guys, then we will go ahead with this. I'll just move to my PPT right now. See. The flat file, if that particular flat file which I have shown you over here, this particular flat file, if you open this particular flat file in front of you, there are the certain terminologies which you encounter over here. Okay, this is the complete information regarding the sequence which we are seeing right now about that particular protein molecule. Okay, so how do you analyze what is the meaning of this particular information over here? I can show you the other molecule also. We will going to start it with the header side and how you'll be able to analyze. So I just prepared this particular PowerPoint presentation for you so that I'll be going to hand over this presentation to the coordinators and they're going to circulate this particular presentation to you. I have made the PPTs in such a way that even if I'm not there and just by visualizing these particular PPTs and following it, you will be able to understand everything. Okay, so this is what our header file, and within that header file, you will be going to encounter a different terminology like what is the atom, what is the hit atom. Okay, so see, is it visible, the PPT? So this is what the anatomy of this .pdb file coordinates. So we will be able to visualize it, that the header. So what is the header? It will be a classification, deposition. It will going to give you the information regarding classification, deposition, date. Okay, now here on the second line, as you will be able to visualize, what is it? This is the atom. So what information exactly it is giving you? This. So the atom is going to provide you the information regarding the coordinates for the standard amino acid or the nucleotides atom. If the amino acids are there, so it will going to show you the amino acids, and if the nucleotides are there, it is going to show you the nucleotides over there. So this is what the atom. Now, this is what atom number 1, which is which has been shown you. Then, if you move down, see, this is what the header file. This is what the atom file. Now after the atom you have encountered this 1. So what is it? It is the unique sequential integer for the each atom in the file. So this 1 which you have encountered, it is the first number atom over there. Now you have encountered the n over there. So what exactly the n is there? So it is the atom names. You will be able to get the abbreviation as the N, Ca or the Cb. So it is the specific chemical identity of the atom. For example, N equal to the backbone nitrogen, Ca will be the alpha carbon and Cb will be the beta carbon. So we'll be able to get the information. This is the N. So after the N, it will be going to give you the information regarding the change, the residue molecule. So what is the residue molecule? This is threonine. Okay. So you will be able to get a 3-letter code over there. Fine. See, this is the 3-letter code over there. Then you will be able to get the chain identifier, because currently we are visualizing the chain A. So, or they are providing you the information regarding the chain A. So the A is there to indicate that this is the molecule from the chain A, that is again at the position number 1. And these 3 atoms which you will be able to visualize for here will be the its XYZ coordinates. See. This is at the position number, this is a chain A, it is in the position number 1, and these are the respective 3 are the XYZ coordinates. Then you will be able to get again the one which is going to tell you about the occupancy, that what is the occupancy of that particular atoms at the particular position. So if it is 100%, means we are working on the good structure over there. So see, these are the 3 XYZ coordinates, then the occupancy is there. And after the occupancy, then you will be encountering a temperature factor. So generally temperature factor, so we used to call it as the R factor. Okay. So the R factor is 13.79. So it will be the measure the thermal mobility of that particular atom. So that they have given you here, and then again this particular information is repeated again. That is the element symbol. So guys, if you do have the flat file in front of you, so you'll be able to coordinate the information which you are reading right now. And I hope you understand what is it exactly. So that is how we will be able to go ahead. Now within that flat file, you will be again going to encounter the one terminology which is called as a het atium. So what is it? Is a coordinates for the amino acid, while this will going to provide you the information regarding the if the ligands are present, cofactors are present, ions or the water molecules are present within that particular structure. Okay, and the rest of the information is exactly same as we have seen. Then you may encounter with the sequence residue. It is called as a sequence residue, SEQRES. So sequence residue means a simple sequence which is there. Just for example, see here. This is the flat file, and do we have a remark? Okay, see here, you'll be able to get the atom information, right? So what is the atom then? Okay, it is a huge file. See, these are the ligand information which they have provided to us. This is the conet information. Acha, we don't have the sequence residue information. It should be there. Let me see. Yeah, see, these are the sequence residue, right? So what is it? It is simple amino acid sequence within that particular chain. This is the chain A. So its amino acid. Then this is what the chain B. Its amino acids. Okay. And then you again got the information regarding the helix or the beta sheet. So it will provide you the information like which amino acid is residing in the helix or which amino acids are responsible for formation of a beta sheets over there. So the secondary structure. Then the conet. So what exactly, as we have seen within this particular flat file, you will be able to visualize the conet, right? See here, this information. So what exactly the conet is giving? It is going to give you the information regarding the non-standard connectivity. Means non-standard connectivity that regarding with the bonding pattern. So that information you will going to get over here under the conet. So this way we have seen the PDB flat file. How you will be able to read the PDB flat file. Are we good? Are you following?
Yes, 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 ma'am.
Okay, fine. So let's move ahead.
Ma'am,
Yes.
it's going too fast. Can you make some slow?
Yeah. Yes. Whenever I'll go for I'll put the syntax, or we will going to give the command. I'll give you time. Okay. Some
Okay,
of
ma'am,
you
okay.
please share the screen with me, so I'll be very happy that I have delivered something to you.
Yeah, ma'am, we are trying. Actually, it's a new field for us, na? So we are just struggling.
No. It's okay. That's why I'm explaining each and everything.
Okay, ma'am.
Because
Okay.
otherwise, if I'll just show you the file and I'll just go ahead that, okay, this is what a flat file. You will not able to understand by seeing this flat file, that what exactly the information it is going to provide to you. So that's why I'm trying to
Right, ma'am.
explain you each and every file which is there. Okay. So
Okay.
right now, as per the
Excuse me, ma'am.
File that we have just downloaded, right?
Pardon?
The file which you are showing is just the file that just been downloaded, right?
That downloaded one, you open that one, ma'am. Yeah.
Yeah, you see.
Yeah, we downloaded and click there.
Yeah, see, if you have downloaded that file and if you open it through the notepad, the same file will be going to be open. I have directly opened that file from here, the display option.
Okay.
So through the display option, you need not to go and download. It will directly open. Okay. If otherwise, if you have gone and you have downloaded this particular structure, see this file. So what I will be able to do, I can go ahead here and I'll ask that open with notepad.
Okay.
The same file will going to open in front of me.
Okay. Thank you.
Okay, so both way you will be able to open. So currently I just fetch the file through display option. This is called as a flat file. And what I have asked you to download is the same file which we will going to open through 3D visualization tool. Okay.
Ma'am, that file what I downloaded, just I open with
Notepad.
PyMall.
Yeah. You will be able to open through the PYM. I'll come to that particular point.
Yeah,
We'll just finish. Yes, sir.
Yes, ma'am. With that I open, but its data is not there. More data, what is just showed us on raw data. So many data is not there in my.
So what you do is, sir, you can go for the any other protein. Open the protein, again download the one PDB legacy file from here, and then that you please open that particular file through the PyMol.
Ma'am, one question just I want to ask.
Yes.
Actually, I'm using Mac OS, Apple laptop. So in that case, in your window, it's a 1APH file name, but in my case, 1A7F. But but everything is same.
Yeah, everything is same, sir. No issues. Your operating system is different. My operating system is different. That's the only difference.
Okay.
Okay.
Okay, ma'am. Okay.
Yeah. So this is what the PDB. If you move ahead with the PDB, see. Now how the workflow will go. So I have shown you that how to open that particular file, how to find out the resolution, experimental method, sequence information regarding it, how we will be able to find out the coordinates. I have explained you that flat file also. Now let's see how we will be able to load that particular flat file through the 3D visualization tools. Okay.
Excuse me, ma'am.
Yeah.
Ma'am, in that file, in sequence RS part, maybe.
That is the sequence residue.
Yes. Maybe I could be incorrect also. In that, I just saw there are chain 1A, chain 2A.
Yeah.
1B, matlab, like, what is the meaning of chain 1A and 2A? Both are included in chain A of insulin only? Or they are like subparts?
Just hold on.
In case of sequence of amino acids of that protein insulin?
Yeah. So generally what happens, chain 1 means first chain. And if we are talking about the one amino acid like the isoleucine, so the first position of isoleucine in that first chain, so it is not necessary that there will be the only one isoleucine, right? There will be the second isoleucine also maybe there at that particular chain. So you will be getting the second isoleucine molecule into chain A. So it is like that. Are you getting?
Okay. So these two chains, chain 1A and chain
Yeah,
2A,
if you
both are like showing two different insulin molecules.
insulin molecule, no, these are the chains within same insulin molecule, two different chain. Insulin is made up of the two
I think
chain.
in
It is
the, in the one line they have within the two line they have the 30 because chain A has 30 amino acid residues.
There are two chains, na? Chain A and chain B. But
yeah,
here,
it is the
here are,
Chain
insulin.
1
So
A
you
and
do
chain
have
2
two
A.
chains over there.
and here we could see this chain 1A and then chain 2A. So 1A and 2A both are having 21. So like
yeah, see, within this particular limit, they are only able to show this much of data. So the same data has been gone into the second line. This is a sequence residue which is present into this one particular chain. So this is what a chain A. These are the residues within the chain, all residue within the chain A. This is the line 2, this is line 3. Are you getting? Nothing else. It is just a sequence which is residing in this chain A, and these are the amino acid in chain A, and these are the amino acid in chain B. That's it. It's very simple. It's the linear equation. That's it.
I think they have put 13 amino acid residues in one line and the rest in the next line. Like
no, sir. Chain A do have a 21 amino acid, and chain B will have a 30 amino acid.
but in the two, when they write 1A, they have 13. Yeah, if I count it, it is just 13, and then here is 8. So addition of these two gives 21.
No,
maybe
actually,
there is limit of 13 and the following are like in the next line. Okay.
I believe maybe that is.
See,
30 similarly, they have 13, 13, 26, and then 4, 30.
Yeah, very simply, the insulin molecule is going to be formed with the help of two polypeptide chain. One polypeptide chain is made up of 21 amino acid, while the second polypeptide chain is made up of 30 amino acid. And about the simple amino acid which they found within those particular chains has been given over here. It is not necessary that they have been enlisted all 21, in the sense these are the amino acid in the chain A, but maybe the glycine may be repeated, or the isoleucine may be repeated, or the valine may be repeated.
Ma'am, thank you so much, ma'am. Thank you.
Okay, fine. So we'll come back to the presentation. So this much we have done, and this information also I have given to you directly through the PDB. So I'm not going to repeat. Is it okay? This is the same information. This is the experimental data information, like if you get the protein structure through X-ray crystallography, or with the cryo-EM, or with the nuclear magnetic resonance. So how, if it is within the 2 Armstrong through the X-ray crystallography, it is a good structure. If it is through, you are going with the cryo-EM, and you will get the information regarding with the 1.5 to the 4 Armstrong data through it. So the resolution is good after 213. Okay. So the data after 213 for this particular type of experimentation is good right now. And then if the people has been done the any type of experiment with the help of NMR. So currently the NMR is based for small protein and capturing the dynamics and the flexibility. But actually every methodology, every wet lab method is good method. Only the thing is that how good resolution you are going to get for that particular protein sequence, because as much as the good resolution you will going to get, so we are going near to the good data. We will be able to say, okay, this is a good structure. Fine. Now, as okay, these are what the quality matrices. So this also I have given the detailed information regarding the quality matrices, which I have shown on the very first page. That is the validation techniques regarding the structure. So this is what the detailed information which I have given for you guys, that what do exactly the R work or R free work will going to represent, or B factor, or the Ramchandran outlier, clash score. What is a good data? So the good data, how you'll be able to analyze, okay, this is a bad data, or this is a good data, or this is a good structure, or this is what is somewhat a bad structure, which currently we are seeing. Okay, so I have given the detailed information regarding those outliers over here within this particular PPT. And now we will go ahead with the coordinates to the chemistry. So by seeing, if you go one by one for the each and every flat file within the PDB, you will be able to understand the bond geometry. You will be able to understand the active site architectures over there. You'll be able to find out the ligand and the cofactor contacts with the help of a 3D visualization tools. We have seen the 3D visualization with the help of a 3D visualization one structure over there. You'll be able to identify the different types of folds and the domains and the orientation of a structure. So what do you mean by the orientation of a structure? Is that whether the structure is alpha, beta, alpha, whether the structure is alpha, alpha, whether the structure is only the formed with the help of the beta sheet. So whether it is a beta barrel, TIM barrel. So different types of the topology will be there, which will going to form the such type of a structure. So we will be able to identify the folds and different types of a domain topologies with the help of these PDB coordinates. And now we will move ahead with the PyMol and the Chimera. Okay, so this is just the basic information. These are the two different platforms which we will going to visualize over here. So these are the visualization tools. So PyMol is generally the command line visualization tool, while the Chimera is the GUI visualization tool. Actually, this is more user friendly as compared to the PyMol, but I find both the visualization tools very interesting. Both have built upon the Python. The background language is the Python over there. This is excellent. The PyMol is excellent for a publication. This is also excellent. The best. It is just that it is the best on the GPU accelerated graphics. Means you should have, if your PC do have the graphics card, inbuilt graphics card, so you'll be able to visualize the structure very clearly. If you don't have the graphics card and the memory is less for your particular device, so it may happen that you will not be able to visualize the structure very clearly over there. Then this is what the best, I think both are very good to teach you. We'll go ahead with it. And both are free of cost. So as it is free of cost, that's why I asked you to download this particular tools. Now we will go ahead for one command. So guys, you please open that particular software in front of you. See, I'm just closing this so that I'll be able to open it once again for you. So if you have downloaded that software, so we'll very firstly just go on the PyMol. You'll be able to visualize that PyMol software over here, right? So just open the PyMol. It will be like this. So are you with me?
Yes, ma'am.
Fine.
Yes,
now,
ma'am.
If you open that PyMol, so just go here, you will be able to find a file. So just go to the file and just load, open. Now I'll go to my desktop where I have put that particular sequence. I'll just, I'm opening this particular file. So it will going to open like this. So you have downloaded the PDB legacy file. So you just open that PDB legacy file like this. Done?
Yes, ma'am.
Okay. Now the same thing, like as I have opened that particular file directly through that this particular tabs, like I have opened the file from here, so I'll be able to open that particular file with the help of by running this particular syntax that is called as fetch 1CRN. So what is the fetch 1CRN? So I'm just opening the new window for you. So when you go, I will just click on this. There will be the this what we will be able to say. Wherever you will be able to put the syntax over there, so that particular window will open in front of you. Are you be able to visualize this PyMol /? See this one where I am clicking here. So just write down fetch, 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 and then the ID of that molecule. So the ID of my molecule is 1CRN. So I just type the fetch 1CRN and I just click on the enter. So the molecule will directly open here with the help of a syntax. Same way.
Madam, what? Fetch? What should you type?
Fetch. FETCH. Fetch space the ID of that molecule.
So, ma'am, first you insert something or open something? Which file can I just missed it?
No, I have shown you that how in a two different way we will be able to open the file. Very firstly, we will be able to open the file directly simply from here. Just take the one molecule and open it. That will going to open. Okay, and the other way I have shown you how we will be able to open the file with the help of a syntax. So I put the syntax, that is a fetch 1CRN. 1CRN is the ID of my molecule. So when I put fetch 1CRN here in this box, are you be able to visualize this box?
No, that is the problem.
No. What you do, sir, you just click over here on this bar, pi mole above. If you click 2 times, that particular window will appear in front of you.
Pi mole, this pi mole.
This above white line, white bar.
Okay.
Title bar. If you click on the title bar, you will be able to visualize that command line.
Yes, I got it. Yes.
Yeah. Now you just type fetch, FETCH space the ID of that molecule.
Okay.
And just press the enter button.
FETCH.
Fetch.
Then enter.
No. FETCH space, then the ID of that molecule, whatever your PDB ID.
Oh.
Like my ID was the 1CRN, right? See, I have shown here. So you just put and then enter. So the molecule will directly open here.
That fetch.
Yes.
Done, guys?
Yes.
Okay.
1CR, your.
No, sir. My molecule name is 1CRN. You must have been downloaded other PDB legacy file. So you just check out that what is the name of your PDB legacy file.
So that
See, this one.
Oh, that raw data one file, huh?
Yeah, which you have downloaded through here, right?
Okay, ma'am. Okay.
So you need to give that name.
So that is in last, ma'am, where we will get.
You must have been downloaded in your downloads. So you don't go in the downloads. It must have been downloaded somewhere. You just open it through here.
Yeah, I opened, but searching where is that part, that 1CR in your case?
No, 1CRN in my case, but what is the ID of your PDB file? So if you have downloaded that PDB file from here.
Yeah, I downloaded, man.
Yeah. So just type this. Don't go and check where it is. No need. It will directly fetch by that software.
Okay.
Okay, you just type with in this particular command line, the command, that is the fetch space and the ID of your molecule. Done? Okay, fine. So now let's go ahead. Once you open, so you will be able to open that particular file in a both way, either by the syntax or either by the directly interactive way. So I just opened this file with the help of this particular syntax. Now I'll give you the another syntax to share. What I'll do, I'll just put this syntax for you in message tab. Fine. Now you just put this particular syntax over there. Okay, hide everything. I'm just putting this particular syntax and I'm just showing you. See, hide everything. I just put it. And now see what happened. After entering, my molecule has been gone. because I have asked it to hide everything regarding that particular molecule. Now, if you want to see that molecule again, so just write here show, and that molecule will open in front of you. Are you guys able to follow me?
Yes, madam. Yes. Ma'am, can you repeat, ma'am, please?
Which one, sir?
This one. Okay.
Yeah, which one? What should I repeat again? See, very firstly, open a file with the help of a fetch
Yes, yes.
CRN. Okay. Afterwards, if you want to hide that particular file, so just type hide space everything. If you type hide space everything, the molecule will go. Now, if you again want to visualize that molecule, just type show. If you put just show and enter, the molecule will again reappear.
Oh.
Okay. Now we will go on the another command, that is show cartoon. Okay. So what exactly I'll do here? I'll be converting this molecule into the, okay, I'm putting it into the meeting, the message tab. Where is the message tab? Yes. Yeah. So this is another command, that is show cartoon. So it should show the model into the cartoon way. So I'll just paste it and right now just see. Now my model is into the cartoon format. Are you guys able to visualize this? See, with the help of your mouse, you will be able to rotate this structure. So right now I am able to visualize it into the cartoon model. Now I'll go for the another command. Now I just want to color it into the sky blue. Which particular thing I want to color it into the sky blue? So secondary structure. Okay. So this is the command. Now I'll just paste that command into the command tab. Press enter and just see that the secondary structure is into the sky blue color, right? Which secondary structure? Helix. SSH stand for secondary structure helix. So helix should be in a sky blue color. So currently my helix in a sky blue color. Are you following me?
Yes, ma'am.
Yes, ma'am.
Okay, thank you, thank you. So this way you will be able to change, or you will be able to color a very specific region. If I just wanted to color this particular beta sheets over here, so I'll be able to put the CSS secondary structure over here, and rather than H, I will be able to put the E. E means extended beta sheet. Okay. Now we will go for the another command. I'll ask it to select a particular residues on that particular platform. Sorry, on that particular protein. So I'm selecting this many residue. Now guys, if you have gone for the any other type of a protein, so just first check that what is the number of amino acids which are present over there. If the number of amino acids are within this range, so you'll be able to select those residue. If the number of amino acids are not within this range, so it will going to show that nothing has been selected. Okay. So I do have this many amino acids, so I'll be able to put it here. I'm just putting that command in the command. Yes. In the command line right now, as you will be able to visualize, and I'll just enter. See, they have only highlighted the residue which is at the position number 11, 21, and 36. See? Are you able to visualize?
Yes, yes, ma'am. Yes.
Very good. Now let's go for the another command. So what this command will going to show you, it will going to convert that side chain into the stick model. Okay. So this is the command, show the sticks, those particular sites which we have selected. So it will show those sites into the stick model. See? Done? First, I selected those residue and later on I convert it into the stick model. Now we will go on the another. I have just taken the few commands for you. Sorry. Now we will going to zoom these particular molecules. So I'll put this particular command here, and now you just see how it will going to zoom. Zoom the site to the 6C. So they have given me that particular visualization, that particular site. It has been zoomed for me. Now what we will be able to do is that we want this particular structure to get published. So how you will be able to put the structure for the publication? So there are the certain types of the ranges that the publication should have the good pixel size, right? To publish. So just put this, it is the publication ready file. I'm just putting this command here and I'm just entering. See, you will get that particular site which I have been highlighted. So that particular site you can consider as an active site. Okay, we have identified the active sites. Okay, active sites are located to this particular region, and you just want to zoom that particular site and want to publish it into the scientific paper. So in this way, you will be able to zoom it out. You will be able to take the picture. Now, this is what the image which you will be able to download, and you will be able to take the, you will be able to use it in your publication. Yes.
Yes, ma'am. I just wanted to ask, whenever you're putting that command zoom site and comma and a number 6. So what is that meaning of 6, 8 or something, anything?
So I had just zoomed that particular region to this, what I will be say, the first scale, second scale, third scale, fourth scale. So you will be able to say the 60% zoom, 40% zoom. So I have given him a scale. If I have given him that 8 scale, it will be again more large.
Okay.
If you are going to give him a 2 scale, it will be little bit small. Are you getting?
Yes.
Yeah. So this is how you will be able to get the image ready for the publication. And these are the very few commands which I have taken for you on the PyMol, that how you will be able to do this thing. Now we will be able to, now I'll show you in a simple way. We will go for an interactive way. Okay, this is what the another molecule which I have opened through the PyMol. Now about this particular molecule, if I want to find, see here on this right hand side of yours, you will be able to visualize the Alt tab, then the name of the molecule. I have opened the 2 molecules in the PyMol, that is one CRN and the one APH. So currently this is what the one APH molecule. Okay. See, so this is what the one APH molecule is. You will be able to visualize this particular tab. So here, what is it? These are the actions which you will be able to do on this particular structure. Because you are not familiar with what I'll be able to say, that you're not finding that commands good. So you'll be able to work interactively. You go here, you zoom it, see. You can take it to the center. You can go for the origin. Now from here, what you will be able to do is that remove the hydrogen, remove the water molecules. So rather than showing you how to remove it from here, I'll show you the another way. You go in this title bar, and where here you will be able to see the display the sequence. Are you guys will be able to display the sequence? See, go here, display. Under the display, go for a sequence. So the sequence will appear in front of you. Is the sequence in front of you?
Yes.
Yes, ma'am.
Sequence. Okay.
Yeah. Now, if I'll just within the red color, whatever the zeros which you will be finding, so these zeros are indicating the water molecules. These are the water molecule. Now, I don't want that particular water molecule, so there are the two way. I directly will be able to remove the water molecules from here. See, remove waters, right? So the water molecule has been removed over there. Okay. Now,
Action. Okay. Action.
Water.
Ma'am, what is
Remove
the option
waters.
in the right that you click for?
Action. Okay.
action A, very first tab,
A.
action. Under the action, you can go and remove the water molecule. Just click on the remove and it will remove the water molecules.
Remove non-polar, remove.
Yeah, so you just remove the water molecules from here and the water molecule will be automatically get removed. Now I'll show the another way that how you will be able to remove the water molecule. I'll again I'll open it. It was APH. Okay, I need to quit. Fine. I'll open the same molecule again for you. Okay, now see the same molecule with the water molecule. What I'll do, I'll display sequence. So once it has been displayed the sequence, this is the red color region. What you will be able to do, you will be able to select these water molecules just with the help of the mouse. Okay, select, then go and just simply remove. So only that much part has been removed. Are you getting, guys?
Yes, ma'am.
Two way we will be able to remove directly from here or whether you will be able to select through it. So right now we have removed the water molecule. Whenever you want to go ahead for the docking purpose, so generally the water molecule are the interacting molecules which will interact with our inhibitors or with our target molecule. So that's why we need to remove it. So very first step is to remove the water molecule. So in this way, within the PyMol, you will be able to remove the water molecule from here. Now see, under the action mode, you will be able to do this many action. Now you go for the another tab, that is a second tab, which will be going to show. The tab is telling you that show this particular water molecule, this structure as a cartoon model. So currently our structure is at a cartoon model. Okay. This is what the ribbon model, see. Show it into the ribbon model. Show it as a spheres. Okay. So you will be able to do anything with the help of this. You just, these are what we will be able to say the trial and the error basis. You will be able to do these things. So there are the many commands which you will be able to utilize under the show, under the shows. Okay. Then you do have the another tab which is going to say hide. So it will going to, if I'll just click here and I just wanted to hide the particular thing. So I'll go and I'll just hide the ribbon. Then show cartoon. From here you will be able to hide and from here you will be able to show it. You will be able to show that particular thing. Okay, just hold on. Just
Yeah, hide and then the ribbon we did.
Okay, so, sorry guys. So there are the different tabs, like this is action tab, this is the show tab, this is the hide tab. You will be able to hide it, whatever the molecules you want to hide over there. Then this is what you'll get another tab over there. That is what a label tab. So you will be able to label the chain. See how many chains are there within my particular structure. So I do have the different chains. Okay, this is chain A, chain B. If you want to label the atom name, so these are all atom names. Now I'm clearing it. See, from here you will be able to label, and from here you will be able to clear it. So you'll be able to label the residues. So these are the residues. See. Then clear. From here, you will be able to color. You will be able to color this particular structure with the help of a chain. Like how many chains are there. So as per the chain, you will be able to color it. So see that we do have only 2 chains. So it has been colored as per the chain. If you want to label it as, color it as per the secondary structure. So we will be able to color it as a secondary structure. So this particular molecule only do have the helix. So helices will only take the red color. So that's what it has taken the red color. If you do have taken the another type of a molecule, it will be going to be colored as per the secondary structural color. Okay, you'll be able to color it into the C. These are the representations of the line into a green color or a blue color or yellow color. So this you will be able to do. Whatever way you want, you will be able to color them. Fine. So what are these? These are the right side tabs, and you will be able to use these right side tabs for this particular structure. Now what I'll be able to do here is that I just shown within while when we have like I have selected some amino acids over there, and you want to select and highlight the active sites of this particular protein. So how you will be able to highlight that I have shown you. Now there is another way also, like within this particular molecule, as you will be able to visualize, you will be able to visualize this particular sequence. So if you are going to select the sequence, you will be able to visualize one amino acid at a time. See. You will just take your mouse and click on the one amino acid, only that particular amino acid will be going to be highlighted. See. Are you getting? I can select and I can deselect that particular amino acids. Now this particular amino acid do have the ligand, and the ligand name is DCE. So after the water molecules, you will be able to visualize if your protein do have the ligand, then only you will be able to visualize over here. After the water molecule, it will be separately indicated. Just for example, I had the another molecule, right? Okay, in APH, in CRN, I don't have any type of the ligands. See, this is the CRN. First is the CRN. Are you be able to visualize this particular part? Huh? This is what the CRN molecule, which is on this side. See. Now the CRN within my very first molecule, this CRN molecule, I don't have any type of a ligand, so I could not be able to highlight that ligand. Okay, but here in the second molecule, that is APH, I do have a ligand and I have highlighted that particular ligand for you. So if you just click and select those particular ligand, you will be able to highlight those particular ligand from here. Okay, now from here under the display settings, are we going for a display settings? Just hold on. Now see, from here you will be under the display. There are the many options within these particular tabs also. See, you will be able to go into the display. You will be able to display the sequence. You will be able to go into that particular display and you will be able to go for the stereo view. You will be able to visualize these particular structures into the two. Just deselect it. Then you will be able to go and we will be able to zoom this particular structure. Like I zoom this particular structure at a 4 Armstrong level. So if we go and again all, so it will going to show you the all particular structures over here. From here you will be able to change the background. Right now our background is black and I want it into the gray. So see, this way you will be able to change the background also over there. Okay, you do have the different type of a color space which is available. Now under the settings, you will be able to have these many different ways to label it. Label, line or the sticks model over there, then the cartoon model, rebuild model. So we have seen those particular things on the right hand sides. So I will not go over here with that. Okay. What you will be able to do is that you'll able to select that particular molecule. See, you can utilize the any different types of tabs which has been given under it, and you will be able to visualize that. Even what you will be able to do here is that even you will be able to make a small movie based on this particular thing. Okay, you can have the 1 second movie, you can have a 2 second movie over here, and that particular movie will appear in front of you. Like that particular movie will be going to be downloaded on your desktop generally, and you will be able to visualize that particular movie. See, there will be the movie. See, this may be the different movie which I must have been downloaded over there. So you'll be able to visualize that movie. You will be able to download it. Okay. So it will going to give you that option also. So in this way, you will be able to utilize the PyMol. Now the same way you will be able to utilize the Chimera. Now let's open the Chimera. Have you downloaded the Chimera?
Yes, ma'am.
Yes, ma'am. Yes.
Yeah, so the same way you will be able to go for a Chimera. Within my PPT, I have given all these commands one by one for you, so that you will be able to follow it and perform those particular tasks. Okay. See, I have given the all commands over there for you. And I'll be going to hand over this PPT to the coordinator. So they'll be going to share this PPT with you. Now we will go on the Chimera. And in the same way as we did here in the PyMol, we will going to execute the some commands over here one by one within the chimera. Okay. Now within this particular chimera, this is what command line based commands which has there, like the open the this particular structure which has been given. Now this structure is I not downloaded this structure, so I'm going to open the another structure. So these are the commands which I have given. One by one, if you will follow those commands, so it will going to execute in the exactly same way as we have executed for the PyMol. Now these are what the interactive way we will be able to go. So I'll show you the interactive way over here. So same way, go on the chimera. Now these are what the molecules which I have already opened. So I'll again open for you. All the molecules data will be available here. So you'll go here, you'll go and open that PDB file. So in this way, the molecule will going to be open in front of you. Are you able to follow it?
Yes, ma'am.
Yes.
Yes, ma'am.
Okay, fine. So after we will open this particular molecule over here. See, within my PPT, I have given you the tabs like go and open. So we have opened this particular molecule over here, PDB ID. Now, how to hide this? So you will be able to visualize this hide section here. See, this is what the molecule which I do have. And this molecule here, you do have an option. Do you get this option, hide, on this side? So I'll just click on it and it will hide that molecule. When I'll click on the show tab, it will open that molecule. This is a hide option. This is the show option. I just sorted out the few tabs for you, few syntax for you over there, where we are not going as per a syntax, we are just going interactive way. Now what you do, you go to the action tab, then cartoon, and show that molecule into the cartoon way. Okay. See, you need to go to the action tab, then you need to go to the cartoon and show. So actually my molecule is into the cartoon format. So if your molecule is not into the cartoon format, so it will going to show you it into the cartoon format. Okay. Done?
Yes, ma'am.
Now if we'll move ahead over here, so what you will be able to do, you will be able to color that chains with the different protein chains way. So how you will be able to go and color that particular chain? So you will be able to go into this particular tab, like go into the action tab, then go for a color and then color by chain. See, go into the action tab, then go into the color and then go for, see here you will be getting the all options. Just click on that option. When you go on, click on that option, here you will be getting the complete options. So here you do have the option like the color by the heteroatom. Generally the heteroatoms are the ligands which are present for that particular molecule, by the element, by nucleotide type, or by the chain. So right now I have colored it by the chain. See, so as within my molecule I do have the 2 chains. So it has been colored with the help of a 2 chains. Done? You'll be able to color by 2 chains. You'll be able to color by the elements. See, now I don't have any nucleotides, so it will not going to take. So this way you will be able to color that particular molecule. Then we will be able to go ahead. And now why I am going as per my PPT, because I want to show you how we'll be able to see the opaque structure. So now go into the select tab, then select the structure and then select the ligand. If within your molecule, if you do have a ligand, then only the ligand will be going to be selected. So guys, go into the select tab. Sorry. Go here into the select tab, then go into the structure and then select the, sorry. So I need to close this first. I not closed it. Now I'll go into the select tab. I will go for a structure and then I'll go into select the ligand. So see, this is my ligand molecule, which has been highlighted over here. If you do have the ligand within your molecule, then it will be going to be highlighted with that particular command. See, within this molecule, which I have selected previously, I do have the 2 different ligands. So it has been shown likewise. So you'll be able to visualize that. Then how you'll be able to go ahead with it? So you'll be able to go into the action tab. Then you will be able to select the atom molecules. Okay, and you will be able to change the style for that particular atom. So you will be able to go into the action tab. Then the atom molecules. Okay, I need to change that background to see you. Okay, so you please follow this particular sequence. You can go into the action tab, then the atoms and the bond. Within that, you can go for the atom style and change the atom style over there. Just follow these steps. Are you able to do it?
Yes, ma'am.
Yes.
Yes, ma'am.
See, it has been changed, this particular ligand. Now, if we will go ahead, I'll just take 2 or 3 slides for you. We again do have, like, go into the action tab, go for a surface and then show. We will go into the action tab, go for a surface and then show. See? You got it?
Yes, ma'am.
Fine. I'll just try to do it because I just selected that particular thing. It's not taking my command one way. Okay, you see, you can open that particular, okay, I have shown you that how you will be able to visualize that particular ligand. So you just want to highlight that ligand, you will be able to highlight that particular ligand. Now, if you want to see this particular structure into the opaque format, so just open this particular structure, go for its hydrophobic nature, and then you will be having a transparency model. Transparent. Okay, here you will be getting a transparency. Now you want to find out the structure into this transparent way. So you will be able to do like this. See, you will be able to visualize the secondary structures, and simultaneously you will be able to visualize the complete van der Waals forces around it into the opaque format. Could you be able to follow it? See guys, you need to go into the action. Very firstly, you take a structure, just convert it into the hydrophobic format. Okay, because on the rest of the format, it is not taking the transparency model. So just take it into the hydrophobic format, then go into the action way, go into the surface. Under the surface, you do have a transparency tab. Now, how much transparency do you want? So just click on the transparency and you will be able to get the structure like this. Done?
How I got that opaque structure and the hydrophobic structure, then please can you repeat, please?
Yeah, you first take the structure, make it hydrophobic with the help of this particular tab. Under the molecular display, there is an option hydrophobic.
Yes.
Now once you made it hydrophobic.
Yes.
Yeah. Now you go into the action tab, this tab. Go to the surface.
Okay.
Under the surface, you do have a transparency. And now whatever the transparency you want, you just click on it. This is the 60% transparency. Okay. So you'll be able to visualize the structure like this. So this is very simple tool. You do have the many options over here only. You will be able to do or you will be
So
able to...
here I get the secondary structure as well as the space filling type model, right?
Right. Exactly. You will be able to visualize the structures with that much of a transparency. See. And as I highlighted before, that is 2 ligands. So you'll be able to visualize that ligands also over here, right? And see, you have these many tabs also over here. Like as I have gone through here and then I did it, they have given you the tabs options over here also.